let's take a look at our list of things here we wanted to kind of do here. So why don't we try doing something with the Zener diodes. So let's build a circuit that's basically a Zener regulator, all right? And let's take a look again. So let's go back to the big screen. Let's go back to the big drawing board there and draw real quick what we're going to do. Okay, so all we're going to do is remember the Zener regulator circuit we talked about, regulator. All right, so we're going to have a V in here. We're going to have a resistor here, and then an output here, and then we're going to put a Zener right here, okay, like this, to ground, and then this is R, and then this is V in, and then this is V out, and then we're going to have a load here, which we just connect to V out like this to ground, and this is our load, and this is our Zener, Zener 1. And then remember, whatever the voltage, the Zener voltage is, whether it's 5 volts or 3.9 volts or whatever, let's say that it's a 5.1 volt Zener, that is what voltage is going to be here, as long as we maintain enough current to maintain the Zener regulation. So we can call that like, I Zener. And then the remaining current will go through here, and we could call this current right here, we could call this IL going through this branch. So anyway, this is the circuit that we're going to build right now, and we'll put a couple different Zeners and see if that maintains that regulation. So let's go do that right now. Okay, so we're back here on the bench, and what we're going to do is we're going to build the circuit that we just looked at. So I've got all my components and whatnot as usual. So let me go ahead and let me zoom in here so you can see what I'm doing. All right, so the first thing is what we're going to do is we're going to find our Zener. And here is the 1N751. Let me show you the zoomed camera. So here's the 1N751, and let me rotate this around. There it is, 1N751. All right, and this is a 5.1 volt Zener. Okay, and remember there's the cathode right there, the line. Okay, all right, so we come back here and let's get a resistor that we're going to use. So we're going to use this red, brown. So that's a 220 ohms. This is going to set up our maximum current. So this is our current limiter. So we're going to put this right here. Matter of fact, let's put it right here. Okay, so there's our resistor. And then to ground, we're going to put our Zener. But we got to be careful of the orientation that we put the Zener. We put the cathode up. All right, so the cathode's going to go up towards this node right here. All right, so that's what we want right there. We want that situation. All right, then we're going to put our input in, and let's just put a wire here to kind of separate these things a little bit so they're clean. All right, and then the output is right there. So put another wire. There's our output. Okay, so this is what we have now. All right, and then now, so that's it. So this will create a Zener regulator. Now, we've got our output right here, so let's start off with, we're going to put no load on here. We're just going to have this resistor and the Zener, and then let's put some probes here so we can kind of measure things. So we'll put that one there, and then we'll put another one on the input. And in this case, we are going to not use the oscilloscope. We're going to use a meter to kind of see what's going on here. All right. And so we got those there. And so now what we need is we need an input here. We need a power input. So we're not going to use the signal generator. We're going to use a DC supply. So I'm going to go over here to my DC supply, and I'm going to bring it over. All right, so got the DC supply, and I'm going to connect the two leads, ground and +5. So there they are. We got the ground and the +5 lead. And I'm going to set the DC supply right now. I'm going to set it for, as a matter of fact, for fun, let's put it all the way down to 0. So it's all the way down to 0. We don't need to look at that this time. Let's get a meter out. So we're going to get a meter out. All right, and we're going to take the meter, and I'll tell you what the, as a matter, you know what, let's go ahead, let's do 2 meters. Let's do 2 meters. Let's do 2 meters for fun here. Let's see what we got here that we can fit on the screen good. How about this one? All right, let's do 2 meters. All right, So what we're going to do is 1 meter on the left is going to show the voltage coming in, and 1 meter on the right is going to show the voltage out. All right. Okay. So let me get this all situated for you here. All right. That's good. All right. So we got 1 meter right here. Okay. We got a lot of room. We got 1 meter right there, and we're going to have another meter right here. All right. So the one on the left, put that at 40 volts. The one on the left will be the voltage in. The one on the right will be the voltage out. Okay, so now what we need is we need a couple probes, connectors to get these voltages, right? And again, this is all about fabrication. So we're going to connect these clips here. All right, so I'll connect this clip here to this output. All right, that'll be our output voltage. And then I'll connect this clip here. And this will be our input voltage. And then we need a couple ground wires to ground these so that we have them grounded for reference. All right, so here's this one right here. And again, I could build these things and just video it, right? But I'd like you to see the process. So you see me make mistakes. You see my the thinking process, the thought process, and all that. It's important because when you start doing this, you're gonna just kind of be lost at first when you start building circuits because you just haven't done it. And so it's really good to see someone make a lot of mistakes in front of you so you can kind of see what not to do also. All right, good. So we have everything hooked up. So we got our power, everything's grounded. So now all I'm going to do is connect the left meter to this one and the right meter to this one in voltage mode here. So let me get these cables. So here they go. And I'm connecting this up. Good to go. All right, and then the right meter, which is the output. And there's never enough room on your desk, so that's one thing. Get a really big area to work on or you're going to get real frustrated. I know I do. All right, so there's our meters. Okay, and let me zoom in just a teeny tiny bit more. All right, so everything's good. Don't worry that the meters are showing some random numbers on them right now. It's just noise. Okay, so now the system is off. I'm going to turn it on, and the Zener should start regulating and letting this, forcing this to be 5.1 volts at some point. So I'm going to turn on the DC power supply. The DC power supply is on, and right now I'm going to put it up to 3 volts. All right, so it's at 3 volts, and okay, the first thing that we notice is we see nothing on the input here. So let's see what's happening here. We got a good connection here. We've got this on voltage. Oh, we are not seeing it. So we're seeing, so there's 3 volts on the output, which is what should happen, but we're not seeing the input. So it's possible these leads are bad. So let me fix this. Okay, so there was actually something wrong with the leads. They weren't engaging this meter all the way, so I had to change the leads out. So now these leads are good, and we've got a good connection right there. So now we're seeing the input and output. All right, so what is going on here? So I've got the power supply set at 3 volts. We're seeing 3 volts in and 3 volts out. And the reason why is because we haven't reached the minimum Zener regulation. So we're seeing no regulation. We're just seeing the input and output match each other. All right, so let's bring it up. 4 volts. There's 4 volts. All right. And let's bring it up to 5 volts. All right, 5 volts, give it a second. Okay, so now we see we've got 5 volts on the input, but on the output we've got 4.5. All right, so now we're starting to see this Zener regulation occur. Now let's put this up to 6 volts. So 6 volts. So we've got 6 volts on the input, as you see, and then now we've got this 4.7. All right, now let's put it up higher. 7 volts. 8 volts, 9 volts, drop it back down to 9 volts. Okay, 9 volts. And now you can see we've got almost a perfect 5 volts out of here. So again, depending on how much current, remember we looked at what was called the Zener current, right, and the Zener resistance. It's not exactly 5.1 volts, right, is the Zener voltage. That's only at one specific current, right, and until we hit that current, we're not going to see that. But we're going around that range. So here's the point. So right now, with no load on this, as we vary the voltage from, so let's drop this back down. So here is, there's 6 volts. So 6 volts, we've got about 4.8 volts out of our regulator. At 6 volts, we got 4.8. Now we go all the way up to 10 volts and some change, 10.5, and look, we got 5 volts out. So this is staying very close to 5 volts, right? Which is exactly what we want. Let's bring it a little bit higher. There's 12 volts, 13 volts, 14 volts, and again, it's staying right at 5 volts, and you can see it's about to hit 5.1 volts, right? So we need to get enough Zener current for it to hit that 5.1 sweet spot if we want it to. But even at lower voltages and lower currents, it's about 4.6, 4.8 volts and so forth. All right, now, so that's showing you the line regulation, right? So as we change the power coming into the system, we see that the output voltage is varying, but not a whole lot. Now let's play with the load regulation, all right? So right now, let's just set this at a voltage that we might get out of a wall wart. All right, so we'll set it at about 10. Say we had if you had a 9 volt wall wart, right, it'd be about 9, 10, 11, 12 volts actually would come out of it unloaded. So you can see we've got 5 volts out of our regulator. Okay, this is cool. So now all I'm going to do is I'm going to put a load in here that we can switch in and switch out. So I'm just going to move these down and give myself some room. I'm going to turn the power off because we don't want to damage anything. All right, so now let's go ahead and let's find our load. So this time, let's do something a little bit more interesting. So let's take the output. Let's take the output here, so you can see this. And let me zoom in while I do this work. All right, so what we're going to do is we're going to take the output here. And the output is right here. And what I'm going to do is I'm going to switch in 2 different values. So I'm going to switch in a 1K and a 10K and where's our 100? There's 1K, there's 10K, and let's see, where'd our 100 go? Where'd our 100 ohm go? There it is. All right, so we're going to have 3 different loads here. So we're going to have 3 different loads, and we're going to switch them in based on some little buttons, all right? And then we'll look at what the load regulation is as we do that, all right? So that'll be cool. So let's just pop this out for now so I can kind of see what I'm doing here. All right, so we're just popping that out. And in fact, what we're going to do is we're just going to move it. I'm just going to move it right here. So we will put this voltage meter right there on that node, all right, when we get to that. So here's the output right here on this wire right here, all right? So here's the output right here. So now what we're going to do is let's get 3 different loads going to ground, all right? So first let's get our largest value, which will be our smallest load. All right, so we'll get our largest value, which will be our smallest load, and that's going to be the 10K. So there's the 10K resistor. And then let's take, here's our 1K resistor, and we'll put the 1K resistor over here, give ourselves some room to work. Okay, there's our 1K resistor. All right, and then here is our 100 ohm resistor, the smallest resistor, but the largest load, right? Okay, so we got all that set up. Then what we're going to do is we're going to see if we can find 3 of these little push button switches, which I have many, many of them. Okay, so I found 3 of the little switches, and then all I'm going to do is I'm going to take these switches and I'm going to put them right next to, we could put them across, but I'm going to put them right next to each one of these resistors, and then they'll be able to switch in the values if we connect a wire to the other side. All right, so here we go. All right, so now, so take a look at, what we have here. All right, so now we're going to hook a wire to the other side of the switch, each one of them to power. All right, each one to power, so we need 3 little wires, no problem. All right, 3 little wires. Here we go. All right, so this one, so here's 1, Let's move this so I don't impale myself, which I already did. I don't know if you can see, but my thumb's got, I can split it. All right, here is the next one right there for our 1K, and then we need one more wire, a little bit longer, a little bit longer. I can use this one. Okay, all right, so there's our circuit. All right, so we've got a Zener regulator right here. We got a Zener regulation circuit. We got this 220 ohm. Then we've got a 10K, a 1K, and a 100 ohm. And we are going to look at the voltage, the Zener voltage out, as we go from no load, right? Just this thing just running. And then we're going to add the 10K load by pressing the button. Then we'll put the 1K load, and then we'll put the 100 load. And this is load regulation we're looking at. We want to see how does the voltage vary as we change the load. All right, that is the experiment, just to get a feel for this. All right, so here we go. So I'm going to push these back into view. Let me open up the zoom here. All right, let's get it all nice and neat. Okay, so the power supply is off. All right, so let's go ahead and let's turn the power supply on. It's at let's put it at 9 volts. All right, 9 volts, good enough, and there it is, and it's on. So on the left side here, we see, let's get this exactly, 9 volts. There we go. All right, so we got 9 volts, and now we want to look at our output, right? So we're just going to put our probe back in here, and we've got a little spot for it right there. There we go. And now look, we've got 5 volts out. How perfect is that? That's awesome. So this is a no load system. We've just got the Zener diode in there. We got 9 volts in, we got 5 volts out. So here's our little poor man's voltage regulator. Okay, let's go ahead and let's say we add a 10K load. So if we add a 10K load, where's our calculator? Someone compute what would be the current. That would be 5 volts divided by 10K, right? Which would be 500 microamps. So right now we're going to kind of draw about 500 microamps, and then the question is, how does the voltage vary? Ready? Here we go. All right. Wow, look at that. Nothing. Barely. See that? See that 0.01 volt variance? So that's pretty cool. So at 500 microamps, or half a milliamp, right, we don't see any voltage variance at all. So we've got very good load regulation. Okay. Let's put the 1K in. Let's do the 1K. With the 1K, instead of 500 or 0.5 milliamps, we're going to have 5 milliamps, right? Let's do it on the calculator. 5 divided by 1K, right, equals 5 milliamps, right? So now we're going to go 5 milliamps, or 10 times as much current. So let's see, can we maintain regulation? So we're at 5 volts here, almost perfectly, 4.99. Here we go. And look at that. How awesome is that? So we only lost, like, 0.05 volts, and we increased the current 10 times. So now we're doing 5 milliamps of current. So right now, this little poor man's Zener regulator is definitely good to 5 milliamps, no problem, right? But let's do the 100 ohm. So now, instead of 5 milliamps, we're going to draw 50 milliamps out of it, all right? So we're going to draw 50 milliamps. The problem is going to be we're going to draw a lot of the Zener current away, right, to maintain that regulation. Now, through this 220 ohm resistor, right, we've got 9 volts. So we got 9 divided by 220. So that means that at most only 40 milliamps can flow through this current limiting resistor. So when we try to draw this current with this 100 ohm, watch what happens. 2.7, because we've lost Zener regulation. So either we need more voltage coming in, or we need more current so that we can maintain Zener regulation and supply the current we need to our load. So let's go ahead and double that current. All right, so we got 220, so let's make that a 100. We'll make that a 100. All right, if we make it a 100, then we'll have 90 milliamps of current to supply to the system. So I'm going to turn off the power supply for a second, and we're going to find a 100 ohm resistor. Okay, I've got my 100 ohm resistor. I'm going to replace this 220. Now this is going to get a little bit hot, so I'd prefer to have a higher wattage resistor, but we're not going to do it for very long. We're just going to press the button. Okay, so let's go ahead and let's turn the circuit on. So I've applied power. There we go. We see our 9 volts on the left. We're back at our 5 volts, but notice we're a little bit higher voltage than our normal no load voltage of 4.99. The reason why is because the the new current limiting resistor here is letting a lot more current, so we're getting more Zener regulation there, and that it's able to maintain that voltage a little bit higher. All right, so I'm just trying to get it to 9 volts perfectly, which is probably a waste of time. All right, so we've got 9 volts coming in. We got about 5.1, the exact Zener voltage that we should. All right, let's go ahead. Let's do our 10K again. All right, notice doesn't even touch it. The output voltage is still 5 as I put the 10K in. All right, I put the 1K in. We drop 0.02, 0.01, 0.02, and now here we go. Here's the big question. So we know we can get 5 milliamps. The question is, can we get 50 milliamps out of this thing? And if so, how bad does the regulation drop down to? Ready? Here we go. Boom. Not bad, not bad. So we lost, 600 millivolts. We lost 0.6 volts. So that's not bad. So if you draw 50 milliamps out of this thing, that's quite a bit. It's 4.43. So if this is a digital system, it would continue to work. It would continue to work. All right. Now, what's something else we could do here? Well, we can also put a capacitor on the output of the voltage regulator, right, to smooth it out so that when we draw this current, it doesn't draw it very quickly, right? It doesn't change it very quickly. The capacitor will smooth it, and we can pull from the capacitor. So let's try that. Let's throw back in. Where did our 4,700 microfarad giant capacitor go? 4,700 microfarad. Where did it go? Where did it go? Ah, here it is over here. Okay, so let's go ahead. Let's turn the power off. So see how cool this is? All right, so now what we're going to do is we're going to put this big capacitor in the output, and this is going to smooth the voltage. So now what's going to happen is as this capacitor charges up to the 5 volts, it'll be charged. So then when we drag the current out with this big load, instead of it instantaneously dropping down to 4.5 or 4.6 volts, first it's going to pull charge off of this big capacitor, and this capacitor will discharge, and as it discharges, it'll maintain that voltage better. So this is a smoothing capacitor. So we're going to put it directly on the output to ground. All right, so let me do that right now. Let me move this out of the way. We're going to put it to the output to ground. And let me give myself some room here. All right, so here's our output right here, and we're going to put it straight to ground. Okay, and there we go. Okay, all right, so that's what we have now. So at the output of the Zener regulator, we've put this capacitor, and now this is going to smooth things out for us. Okay, so this is going to be cool. All right, so let me get these cables up here. Here we go. All right, so I'm going to turn the power back on. Power's on. All right, notice we're at our 5.07 volts. We're at our 9 volts on the input. Everybody is happy. Now let's go ahead and let's switch in our 10K load. Ready? 1, 2, 3. Notice the voltage doesn't even flinch. All right. Doesn't even flinch. My finger's off it. It's 5.8, 0.08, 0.09. It's just kind of flubbling around there. Now let's put the 1K load in there. Ready? Pushing. So there we go, 0.07. So we, dropped 0.01, 0.02, very, very little. All right, and then here is the big one. So now, again, we're not going to get anything for free. This capacitor is going to discharge, but it's going to take it a little bit to discharge, and we could figure it out because we know what this resistor is, we know what the capacitor is charged to, we know what the value of the capacitor is. We could figure that out, but it's not going to be 0 time. It's going to be some time, all right? And hopefully it's semi-slow, so we get a minute to look at this. All right, so we're at 5.09. Let's put in the 100 ohm load, which is going to try and draw about 50 milliamps. Ready? And go. And then look, see? So we got some time. So instead of that instantaneous pulling down, it goes down, slower. All right. Now, the meter is not a really good view of this because we're looking at something that's changing as a function of time. What we really want to do is look at this on the oscilloscope to see this DC kind of go decrease smoothly. All right. So let's go hook this up to the oscilloscope, just the output, and let's take a look at what that looks like. All right. So give me a minute and let's do that. Okay, we've got our oscilloscope hooked up to the circuit here, right? So we've got the lead, the channel 1 right to the output of the Zener, and then we've got a ground here kind of weaseled around, right? So, there's never enough room to do anything here, of course, so that's always a problem, all right? And so now let's go ahead and let's turn the power back on, and then we'll go take a look at the oscilloscope, right? So I'm going to turn the power back on. So we're going to get our 9 volts in, and we got our 5 volts out. And again, when I hit the button here, we're seeing the drain. All right. So now what I'd like to do is, so now let's go look at the oscilloscope. All right. So the yellow line is channel 1, all right? And right now we're at 2 volts per division and we're putting out 5 volts. So let's put it to 1 volt per division so you can see a lot of change. I'm going to slide the channel down all the way to the bottom here, all right? And so we've got 1, 2, 3, 4, 5 volts. So it's exactly correct. Let's turn measure on here. We'll turn measure on. And you can see that the average voltage, the mean here is 5.16 volts. So everything is as it should be, all right? So now what I'm going to do is I am going to, and keep your eye on this mean, all right? I'm going to press the 1K button, 1K button, and notice it drops down just a hair, all right? But you can't even see it, okay? And now I'm going to press the 100 ohm, and we're going to draw 50 milliamps. And notice how it changes. It drops down as a function of time. We can actually see this event. All right, so now if we change the sweep rate, all right, so I'm slowing it down. Now watch this. As I press it, oh, did you see that? Did you see that curve? Let me do it again. I'll lower it even more, all right, and watch this. There we go. And let it charge back up. And now, look at that. See that curve? And again, I'll do it. So what does that look like? That is a RC discharge curve. There it is. All right, so as I hit the button, there's the discharge, I let go, there's the charge. There's the discharge, there's the charge. So it's regulating, but that big capacitor is acting like an RC circuit, which is good. It's giving us a smoother transition so we don't just jerk down, right? And we can scale this some more if we want. I can put this at 500 millivolts, and then I can scale. There we go, right there. Okay, so now when I hit it, there we go. Isn't that cool? And then we'll let it up. There, charge, discharge, charge, discharge, charge, discharge. Could do that all day. So that's cool. Now, if we had a bigger capacitor, we would, again, discharge slower. So if we had a bigger capacitor, we would discharge much slower, all right? And we would have more time. So as long as our load, so we'll come back to our project board here. As long as our load is not too big, as long as our load is not too big, we could tolerate pulses of 50 milliamps because this capacitor could supply it. If we wanted to, hold that 50 milliamps for a long time, obviously we can't, right? The second we do this, very quickly we drop down to 4.5. But if we only needed to hold it for a couple hundred milliseconds, we could because that capacitor is used as a charge source, okay? So now we're learning more about power supply stuff here. So we're learning you can use the Zener to create a Zener voltage, then we can smooth it out with a capacitor, and then depending on what the load is, we've got a small load at the 10K, nothing happens. We got a bigger load at the 1K, right, 5 milliamps, not too much, but at the 100 ohm, we start dropping this voltage, but that capacitor offsets the damage done, all right? And so that's it. So again, that's a good use of the Zener diode. It clamps the voltage, or it can be used as a voltage regulator, which is what we did here. Okay, so let's move on. Let's go back to the screen, back to the blackboard, and let's draw what we're going to do next, which is real quick, we're going to do the logic gate for the we're going to use Schottky diodes. We're going to make a little OR gate, all right? So that'll be fun. So that'll be what the next part of this ongoing lecture is, all right? All right, welcome back. We are just continuing with the diode bench work here and building things. I just thought I'd come back here to the computer screen, and now we're going to do the Schottky diode kind of experiment. And remember the Schottky diode, it has a symbol over here to the right, which is just the triangle and kind of the upside down U and the U. That's what it looks like when you want to draw it. And remember, it's got a very small forward voltage because it's one PN junction, just P or N, and metal. All right. So let's go to our drawing program and kind of figure out something we're going to do. So we said we're going to do a digital OR gate or an attempt at a digital OR gate, right? So, so I'm thinking let's do something like this. So Schottky diode experiment. So we are going to put a Schottky diode here, like this. We'll put another one here, like so. And then we tie their output together. So this is the whole idea of what's called the the wired OR kind of. You're just tying these two things together. But because of the diodes, this will work. All right, and then let's go ahead and let's take a resistor, and then we'll go to the anode of an LED. And LEDs, the symbol for the LED is kind of a standard silicon diode, then a couple of arrows emanating out, which means light. All right, and we'll set this to something like 200 to 300 ohms, and this is an LED. All right, and then that's basically about it. And the Schottky diodes are going to use for those ST parts, and we need to now be able to apply a voltage to these two diodes. So we can do this in a lot of ways. So let's just say that we're using a 5-volt system. So we can just kind of run a wire. So if we have 5 volts and then we have ground, say that this is ground here, and then let's say that this is 5 volt here, we could just run, take a wire and kind of touch it like that, or touch it like that. But instead, let's try and add some switches here. So let's do something along these lines. So what I'm going to do is I want to kind of draw kind of a little bit of an abstraction here. So let's say that this is the top, we're going to call this the top rail, the top power rail, and that goes to 5 volts, all right? It just represents a wire, all right? Then we're going to have a bottom rail like this, and it just goes to ground. It just represents ground. Again, it's just a wire, all right? So now we're going to put a couple switches in here, and so what we're going to do is this. We're going to do something that looks like this. So we're going to have one switch like this, and we're going to connect it to this guy, and then we're going to have another switch. As a matter of fact, we'll do momentary switches. Okay, so the momentary switch symbol is that. We're going to connect that like that. Then we're going to have another momentary switch here, all right, and we're going to connect that there. Now in one case, we're going to connect one momentary switch to ground, and then we're going to connect the other momentary switch up to +5. And then we're going to replicate this circuit again. So we're going to have a momentary switch. We're going to connect it to this input, and then we're going to connect this one high, like that. All right, so that gets us that. And then we're going to add another momentary switch here. And now this one's got to go down to the low bus bar, right, or the low rail, the ground rail. So we just kind of indicate that like that, all right? And I'm just showing you that as just a way to draw schematics, right? When you can have these rails, and then you can kind of mimic this in the actual hardware. So now, as we press these buttons, what's going to happen is we're going to get, in one case, we're going to get to 5 volts or 0 volts, 5 volts or 0 volts. And we're mapping, 5 volts equals a digital 1, and 0 volts equals a digital 0. And as we do this, we're going to turn on these two diodes, right? Turn them on, turn them off, and we're going to get them to forward conduct. And they're going to drop a voltage over them, which is going to be about 0.3 volts, 0.2 to 0.3 volts in both cases, right? And then so here at this node, we're going to be seeing about, 4.7, 4.8 volts each time when this thing turns on. So it's an OR gate, right? And then it'll turn on this LED because we'll forward bias this LED plus to minus, and the LED will turn on. Why don't we make that green to represent 1? Green equals 1, and then off equals 0. So this is the circuit that we're going to build, all right? And then we'll play with this with some other things. So it's complicated enough where I wanted to draw it for you so you kind of had an idea, all right? So let's go over to the bench and let's build it. Okay, so we're here at the bench, and I've got all my parts kind of strewn about. You can't see them all, but they're all here, so I've got everything that I need. So let's go ahead and let's zoom in so you can kind of see what I'm doing better. All right, so here we go. So the first thing is we've got these two Schottky diodes. All right, and if you remember, these were, what were these? These were the STPS2L60 Schottky diodes from ST Microelectronics. Just the real good Schottky diode that I like, through hole. All right, so let's just start. Let's just start right in here and get this done. And let's give ourselves, you know what? Let's give ourselves a good amount of room, a little bit more room, because we have to put all those switches, those momentary switches in there. All right, so there's our two diodes. We're going to put them right there. Now let's tie their outputs together. All right, that we know we have to do, so we'll tie the outputs together. And let's fix this up. Take the time to straighten out these wires. It's a pain, but otherwise they just get all crinkled after a while, and they won't go in well, and then plus you'll end up poking one into your finger, I guarantee it. All right, there. All right, so that's nice. Okay, and then let's take that output and we'll put it right here. Okay, so there's our output. Good. All right, let's put a resistor on that. Let's put about 220 ohm. So that's going to be red, brown, 220 ohm, red, brown. So there's one right there. All right, and then let's put a green LED going to ground. So here's our green LED, and then you can see on the left, you can see that big flat part of the internal construction. That in this case is the cathode. And then also remember, the other rule is whichever side is flat, and let me see if you can see that here, whichever is the flat side. Now let me go to the zoomed in camera. So on the zoomed in camera, the flat side, and we're trying to get this camera to, there we go. And okay, there, can you see that right there? Can you see the flat? There you go, you can see the flat side. And it's to that big pedestal. That's negative in this case. The flat side is always negative, but the big pedestal is usually negative. Sometimes it's not, and I've talked about that before. All right, so I'm going to put ground to ground and the positive side to the output of the resistor. So when we get a high here, this is going to turn on. So this will work right now. This will work right now. So where I've got power here, I've got +5 and ground, +5 and ground on the red and the blue rail, and that's why that whole concept of rail. And then I've taken that and I put it up here on these rails. So now, if we just take a couple wires and we plug things in, we can actually get this circuit to work, all right? So one other thing I want to do though is I want you to see what the voltage is on the output here. Now we're putting a load on it, so that's going to play with it a little bit, but let's get the voltage. So let's do this so that we can kind of see what we're doing here. I'm going to take a fairly long wire right here, and I'm going to plug it in right there. All right, and then I'm going to put one of our little probes in here, our little connectors, so we can plug our meter into it and put it there. And then I'm going to put the other end to ground. Okay, and then I'm going to connect this to a meter. Right there, there's our meter. So I'm going to connect that to it, and let's hope that we get good cables and stuff this time. Always check your wires. I mean, it's surprising, but a lot of times stuff is broken. It just not working. All right, so let's zoom out a little bit here, just enough so we can see the whole situation. All right, I'm going to turn this meter on to a voltage and 20 volt scale. So you can still see everything, so that's good. Okay, so now we're getting 0 voltage out, the LED is not lighting, and we're not doing anything to these Schottky diodes. So all I'm going to do is just do this old school. I'm just going to put a couple wires in here. Super old school. So I got these wires just floating in the air, and I'm going to put them both to ground. Both to ground. All right. So we got a 0 and a 0. We should get a 0 out, and we're getting a 0 volts out, and nothing is happening to the LED. Now, if we just put one of these to 5 volts, just one of these things to 5 volts, right? Okay, and I just forgot to turn the power on, so that little red LED is telling us power's on. But anyway, nothing has changed. So we've got 0 volts, nothing is happening, the LED is off, not going to turn on. All right, so now let's put one of these high, which will be 5 volts. So I'm just going to move this down this red rail, and then sure enough, see that LED popped on? All right, and then of course our meter is not showing any voltage here as usual. Something is amiss. It's probably these cables. I've been having trouble with cables because I keep moving them from meter to meter. So I'm just going to switch meters out, and this one always works. All right, and what happens is inside of these cables, these connectors at the end of the cable here, right, you can see that there is where the contact is, and if it's too deep, if this is too long, the sheathing, it won't bite in when you put it into the meter. Now, meters typically come with really bad cables if they're a low-cost meter, because cables are very expensive. So I buy a bunch of new cables that are all really high quality, but a lot of times they don't all fit each meter, so you got to kind of fit one that goes in the right meter, and then as you switch these cables out, sometimes they don't work. Okay, so now we've got the meter plugged in, and okay, so we've got a 0 volts and 0 volts on the two inputs to the two different Zener diodes. I've actually had to switch the meter, which I thought was bad, and switch the connector, which I thought was bad. Then I figured out that this wire, the ground wire to the connector, was actually bad. This piece of wire is internally broken. So there's a break in it. There's no continuity in this wire, driving me crazy. So again, even the simplest things will break, and you got to check them. So sometimes when something doesn't work, it's really frustrating. Like, is the meter wrong? Is this wrong? Is that wrong? But it was just the wire actually broke internally because it's been bent so many times. These are solid wires, and they will break after a period of time internally inside of that insulation. Okay, so now we're back to what we were trying to do. So now we've got a 0 and a 0. We've got the LED off. We've got 0 volts out on the meter. So now let's just put either of these high. And sure enough, the LED turns on, and we see we've got 4.71 volts out, which means over this branch right here, we just dropped 0.3 volts roughly over that diode. We've got 5 volts coming into the system. Now, so that's an OR gate. Now, let's turn the other input to a 1. Let's put another 1 on that input, and we still got a 1 out. And then let's put a 0 back to the first one, and we still got a 1 out. So we got 1, 1, 1, 0, 0, 1. We always get 1. If we put them both high, then we notice we get a slightly higher voltage, and the reason why is because we're getting a little bit more current through both of these. Now we have both of them in the system, a little bit more current. Because we're getting that little bit more current, then we can drive the circuit a little bit higher. All right, so now what we want to do is we want to add our switches, and so that we can just press buttons instead of doing this by just moving these wires here. All right, so we're really not going to add much more features to it. We're just going to add some buttons so we can see what that looks like. All right, so let me do that right now. Switches are connected to the ground rail, and then both switches outputs are tied together, and they're tied to the top and the bottom Schottky diode respectively. So basically we can put a 1 and a 0 inside of the circuit here, apply a 1 and 0, which is 0 volts and 5 volts, and then we can see what happens. All right, now one thing you notice is this meter is going crazy with millivolts and this and that. What's happening is right now the circuit is completely open. There's no paths for current right now to get to this meter. So it's picking up basically electrostatic charge and this and that, and that's why it's running all over the place. We're going to address that in a minute, and the reason why is because there's no stable voltage anywhere. All right. So now let's go ahead and let's put a 0, 0 on both of the inputs. 0, 0 on both the inputs. So I'm going to press both of these white buttons simultaneously. All right. So as I press them both simultaneously, we see that the output on the multimeter stabilizes because now there's some there's a voltage being applied to those diodes, all right? And so even though they're reverse biased, there is a 0 voltage on the left side of them, all right? And the LED is off as we expect, all right? Now, I'm going to turn on one of the circuits, one of the Schottky diodes. I'm going to forward bias. I'm going to press the button, and there you go. And we get 4.71 volts out, 4.7 roughly, 0.3 dropped over that top diode right there, right? Right there, we drop 0.3 over that. Now I'm going to do it to the bottom one. I'm going to turn it on. There we go, 4.7 from our 5-volt rails. I'm going to press them both. 4.74, a little bit more. Okay, now how can we get rid of this jiggling all over the place? All right, there's a few ways we can do this. So one thing that we can do is we can, and this is where pull-up resistors and pull-down resistors come. So when you have a digital circuit that has an open input, you can put a pull-up or a pull-down on it, and that'll kind of give it a stable 1 or a 0, a very light one, so that when you actually apply a 1 or a 0, you can change it, but if there's no input on that pin, it has something there, and it's not just floating statically and you're picking up static, all right, which is what's happening here. So now, because this isn't a digital circuit, it's just a couple diodes, we can do this in a couple different places. If we want, what we could do is on the output itself, we could put a very, very weak high or a very, very weak low, meaning a resistor up to the top rail or the bottom rail. So let's start there. So for fun, let's get a really big resistor. All right, so we're going to get a really big resistor, 100K, and what I'm going to do is I'm going to tie this to ground on the output. All right, so this is one way to do this. I'm going to tie it to ground. So here's our output, and I'm going to tie it to ground. All right, so there we go. So I've added this resistor, it's tied to ground. Now look what happened to our meter. Now it's stabilized because now there's a 0 volts there. So there's something there, not a lot of current, right? 5 volts divided by that 100K would be the most current that could flow through that. But now we've stabilized it and it's not all over the place because now we've asserted a voltage. Now we can put our 1 and we get our 4.7, we put our other one, we get our other 4.7, put 1 if we want, and then we can formally assert zeros by pressing those 2 buttons right there, right? Formally assert zeros. Now, what's another thing we could do? Since when these switches are not down, both of these things are floating, right? So we could put pull-down resistors on these inputs also. We could put 100K pull-downs, and then if we did that, if we put the 100K pull-downs, we could get rid of these 0 switches, right? So let's just do that. So let's get rid of the 0 switch. All right, so we're going to get rid of those. In both cases, we're going to leave the wires there. All right, just going to leave the wires there, and we're going to get 2 more 100K. 2 more 100K. We've got lots of 100K. All right, so I've got 2 more 100K resistors here, which is brown, black, yellow. Brown, black, yellow. All right, you can figure out that color code if you like. Brown, black, yellow. Is 100K. Cutting these leads now. Okay, so now what we're going to do is we're just going to tie these low. The blue is the low rail. There's the top blue rail. Where'd our other 100K go? Right there. And here's the bottom blue rail. All right, so there we go. So now we've basically got the circuit real stable. All right, so we've got zeros, very light zeros on the input. We've got a 0 pull down on the output. And now we can put a 1. And you can see we can put a 1. We can put 2 1s. All right, and now since the inputs have something on there and they're not floating, we can get rid of this output if we want, right? And the circuit still stays stable. All right, and these pull-ups and pull-downs, they stabilize the circuit. They give you a signal when there's no signal on the input, but they burn current, right? Now, another problem, which you may or may not have caught or thought about, is when we had those 2 switches, one for high and one for low, what if we pressed both at the same time? We would have shorted the power lines out, right? So you would have done a short. So what you could have done is you could have had the low button there and the high, and instead of connecting them directly to the rails, you could connect them through a 100 ohm resistor. So for all intent purposes, 100 ohms is going to give you a ton of current in a digital type circuit. So you'll get enough current, but you won't burn the system out if you were to tie them both together. So if we had a 100 to the top rail and we had a 100 ohm to the bottom rail with two switches, and we press both of those switches, there'd be 200 ohms of resistance between the two, between the final path, so we couldn't short them together and short power to ground, which we wouldn't want to do. All right, so anyway, there is our circuit. All right, we've got our one each time. All right, popping out. And just for fun, let's do one other little thing here. Let's go put, and I'm just kind of having some fun here for 1 minute. Where did our, here we go. Here's our 4700 microfarad capacitor. What if I put this on the output, right, to this LED? Well, what's going to happen is, as we fire a 1 out, right, it's going to remember the 1 like memory, and then it's going to slowly discharge it as I let go of the asserted 1, right? So let's give that a try. So let's turn the power off. All right, so here's the output right here. So we're going to take the output, make sure to do the polarity right, and we're going to take that capacitor right there. All right, so we got the capacitor, and it's polarized, 4700 microfarad. There it is. All right, so let's turn the power back on. All right, so now when I turn the circuit, when I assert a 1 on either rail here, all right, we got the voltage out. Now when I let go, look at that. It stays on and then slowly dissipates. Stays on, then slowly dissipates. So this is fun and cool, but why am I showing this to you? I'm showing this to you because this is important for digital circuits. And the reason why it's important is this. As you have digital signals running around in a circuit, every time they meet up with a capacitor, they charge the capacitor. And those nice square waves are going to charge the capacitor, and then they're going to, the capacitor is going to discharge. That signal is going to get slowed down, or what's called the slew rate. The slew rate is how fast that edge is moving. Normally a square wave has a perfect edge, but as we add capacitance, it doesn't have a perfect edge. We see that capacitive charging and discharging, right? So if we were to take our oscilloscope here, right? So let's take our oscilloscope, and what we're going to do is we're going to monitor the voltage on the output here and see if I can get a probe in here. I'm just trying to look what a good spot is. Okay, there we go. So what I'm going to do is I'm going to actually take a wire here, and I'm just going to connect the probe up to that. So let me get channel 1 here, get this hooked up. So I want you to see this and what happens here. And as we talk about digital circuits more, and when we get to that, this is kind of a phenomena that's going to happen, and that's why you don't want a lot of capacitance in your digital circuits. All right, so we've got the oscilloscope probe there, and notice there's still 1.5 volts on that big capacitor, right? It's still discharging, except it's not enough forward voltage to turn on that LED. All right, so as I turn it on again, so I just turn it on, all right, and then we can see there's that voltage going all the way up to 4.3, then I let it go, and then it starts decreasing. Then here's the interesting thing. As that diode becomes not forward biased, there's no more current flowing through that diode and through this resistor, so there's nowhere for the charge to go. There's nowhere for the charge to go anymore, so it just kind of sits on the capacitor in this position. If we were to move the capacitor over, right, to a different position, right, then we would change the circuit, but we're just going to leave it right here. So there's nowhere for that charge to go. Now, the diode, which is the light emitting diode, is turned off, so it can't get out, it can't go anywhere. So it's just slowly discharging through the leakage current of the diode and then back through the leakage of the Schottky diode. So that's kind of interesting. So now let me get the oscilloscope cooperating with us. Okay, so on the oscilloscope, if you take a look, we see we've got this trace running here. Here is 0 volts right here. There's the base of the channel, and we're at 1 volt. We're at 1 volt on the per division is what it's set at. And see, we're sitting there at about 2 volts. See, the mean is 1.68 volts. And if you look back, see 1.63 volts. And the reason why is because there's no place for that big capacitor to discharge, right? So we can fix that in a second, but let's just keep playing with this. Now, what I'm going to do is I'm going to assert a 1, All right, so this is what I'm going to do. So look back at the development board here. So I'm just going to assert a 1, and then we're going to get this 4 volts instantaneously, this 4.7 volts, and then let go of it, and then it slowly discharges. The diode, the light emitting diode, is forward biased, so it keeps allowing current to flow until it becomes not forward biased, and then the charge kind of sits on the capacitor. Now I'm going to do this with you looking at the oscilloscope, all right? So here we go, look at the oscilloscope. Now I'm going to press the button, look at that, and now I'm going to let go of the button. Whoa, how cool is that? I'm going to press the button, and I'm going to let go of the button. All right, let's let it reset out. As a matter of fact, let's do this a little bit. We can do this a little bit quicker. There we go. All right, and boom, 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 boom. All right, maybe a little bit slower. And then there we go, and then I let go. All right, and then notice every time it's always discharging down to this point right here, right? It's not discharging any more than that right there. All right, and the reason why is because there's no path to discharge the capacitor. Can we add a path to discharge the capacitor? Sure. So looking back at our circuit here, so let's go ahead and let's turn the power off. So what we need now, just in this case, and again, we're just engineering for fun here, we need a bleeder capacitor. All right, so we're going to add a bleeder resistor. Okay, so we need a bleeder resistor on this capacitor if we want to have the behavior where we can let that voltage drop all the way down to 0 volts. Again, that diode, this light emitting diode, once it becomes not forward biased, then no more current flows and the capacitor can't discharge. It has nowhere to discharge to. So let's take a look back on the computer blackboard of exactly what we're going to do to fix this. All right, so let's go over there. Okay, so we're here on the blackboard, and what we're going to do is first it's kind of draw in what circuitry we have here. So we added that capacitor. So we added that capacitor, and we just added it right here. All right, and so that was what, 4,700 microfarads? Not a small capacitor, pretty big. All right, so then what's going on here? So now what's happening is this. Once we assert either one of these 5-volt switches, these momentary switches, either this one or this one, then we're going to get 5 volts on the left, and on the right we're going to get about 4.7 volts, right? 4.7 volts, just basically the 5 volts minus the forward drop of the Schottky diode, all right? What that is going to cause is current to flow into this capacitor. So current's going to flow into the capacitor, it's going to charge it up, and it's going to charge it up to 4.7 volts and just sit there as we hold down one of these buttons and get out a digital one, which in this case is 4.7 volts. Additionally, there's going to be current flowing down here through this resistor and through this light emitting diode and turn on this LED. All right, so that's just going to continue. Now, the second we let go of these buttons and then we don't assert the 5 volts anymore, then what's going to happen is this capacitor, right, is charged. It's going to want to discharge. Well, the capacitor cannot discharge in this direction, so it's going to discharge through the resistor and through the LED. The problem is as it discharges, what we're seeing on the graph is something like this. We're seeing this thing starts off at 4.7 volts, right? And then it discharges, and then it plateaus and flattens out. And this value that it flattens out at, all right, is 2.1 volts, something like that. Let's go take a look and make sure of that. Yeah, so it's turning off at about, it's holding at about 1.8, 2.0 volts. The reason why that it's sitting there at 2 volts, 1.8 volts, is that the forward voltage drop to get this diode, this light emitting diode to conduct, is about 1.8 to 2.0 volts. So it requires at least that much voltage to turn this thing on, and then once it starts conducting, it starts emitting light, and then you can put more current through it, drive more current through it, but at least 1.8 to 2.0. So what's happening is as that capacitor discharges through that LED, at some point it hits this point where it's no longer forward biasing this LED, like 1.8 volts. And I'm looking at it right now, and it's discharging, and now it's at about 1.7. So it's probably 1.7 volts, 1.8 volts. and then there's just no more appreciable current through this LED, so the capacitor, for all intent purposes, just sits charged. So from the capacitor's point of view, it basically looks like an open circuit now, because the impedance, the path through this resistor and through this LED, is a very large impedance, right? It's probably 100K, 500K, a megohm, something like that. So it's very hard for it to flow any current. So what we need is a bleeder, and let's put that in a different color, a bleeder resistor. And we need basically to put a resistor right over the capacitor. So anywhere on this node will do. Anywhere on this node will do. So what we'll do is we'll just, from here, straight down, put a resistor, and R, all right? And this is going to be our bleeder resistor. All right, and why don't we set the bleeder resistor? We'll start it off at 1K, which is a pretty good value. So this is a very large capacitor, so at 1K it's going to still discharge pretty slow, but we don't want it too small so that it instantaneously discharges. So we'll change it, but let's start off with 1K. So this is all we're going to do. We're just going to add this resistor. So let's go back to the bench and do it. Okay, so we're back here on the bench. We've got our capacitor, and you know, let's take this thing out. Let's take this capacitor out so that we can. Now it's still charged. A couple volts on it. That's all. All right, we're going to get our 1K resistor, and we're just going to put that straight to ground, just like that, and kind of bend it over, give us a little bit of room. We're going to take our capacitor and put it right back. And be very careful playing with charged capacitors, because if you short them or if you put them to a different voltage, sparks will fly. But there's only a couple volts, so it's okay. All right, so we got it back. Let's go ahead and let's turn the circuit back on. Turning on the 5 volts. Got our little indicator light there, which is always helpful to let you know that power's on. All right, and so let's take a look at the oscilloscope. So we can see that we've got 0 voltage here on the output because we haven't even charged this thing up one time. So now what I'm going to do is I'm going to assert a 1. All right, so take a look over here. We're going to assert a 1 with either one of these, and then we're going to watch what happens on the oscilloscope. So first, when I assert the 1, notice the LED turns on and it slowly discharges. And now, once that hit about 1.7 to 1.8 volts, the LED wouldn't be forward biased and the capacitor would just sit, but now that capacitor can discharge past that, all right? So this time I'm going to do it, but we're going to be looking at the oscilloscope. So looking at the oscilloscope, and here we go. Ready, and assert and deassert. Look at that. So now there it goes, and now before it plateaued and just kind of stood there, but now notice that that line, that voltage is dropping down. All right, now it's not the fastest thing on earth because we've got, 1K in this 4700, but notice it's almost down to 0 now. All right, and there we go, assert, deassert, assert, deassert, assert, deassert. So that is what a capacitive resistive kind of pulse looks like when you put a square wave through there. That's kind of what happens to it. All right, and then it takes it time to go back to ground. Now, let's change that 1K and let's make it a 100 ohm, so it should be able to discharge much, much faster. Or we could just use a smaller capacitor, but let's just use a 100 ohm for fun. So what I'm going to do is I'm going to pull this out in real time, so take a look. All right, so, careful doing that. Again, we're dealing with low voltage circuits, so we're fairly safe here. We're not going to shock ourselves. We might get a spark once in a while or trigger the short overload protection inside of the power supply. So I've now put the 100 ohm brown, black, brown and replaced it. All right, so again, now when I push the button, we still get the same discharge, see it discharge, but it's faster. All right, now let's go take a look at the oscilloscope. So looking at the oscilloscope there, let it calm down. All right, so now I'll wait for it to get to the next screen, and then I'm going to assert it. There we go. Deassert, assert it, deassert. So much quicker it goes down. So the whole point here is that if you have a digital circuit with square waves running around, right, and you have capacitance and resistance, you're going to have RC time constants, and you're going to have charging and discharging. You're going to have charging and discharging, charging and discharging. So of course this is all happening at a scale. We're talking about megahertz or gigahertz or terahertz these days, right? But it still matters. And even more so because even a little bit of capacitance and a little bit of resistance can cause this kind of charging and discharging, this RC problem that happens. Now, on the other hand, this can be very useful if you want to slow something down. You want something, basically you want a pulse and then you want to slowly ramp it down. That is exactly what you would use a capacitor and a resistor for, to slow that process down. All right. So anyway, we're done here. And so we've done the Zeners, the normal diodes, the bridge rectifier, we did the full wave, we did the half wave, we've experimented, done Schottky diodes, done a little logic circuit. So now we're going to talk about, I think, either transistors or we're going to talk about uh, power supplies next. But we're going to talk about both of those. Not sure which one I'm going to do first. All right. So I will see you in the next lecture. You did good. This is another, long part, very long part, but a lot of fun. We're building things, So this is what happens. All right. So I'll see you in the next lecture. Bye. Fire, we couldn't use it, right? Because we're assuming DC. So if you want to be really robust, you can always put a bridge rectifier, and that allows people to put any kind of wall wart in the power supply. So that's kind of cool. All right. So anyway, so there's our bridge rectifier, and then we have our smoothing capacitor again, that big 20,000 microfarad, 4,700, 10,000, 20,000. You can put that to smooth that DC. All right, so this is kind of stage one. So bridge rectification and smoothing, and this is assuming we're having an AC source, worst case and best case a DC source. All right, out of this we get plus and minus DC, and it's smooth DC. All right, now let's see here. All right, so now this is where things start getting interesting. So this is kind of a representation of a voltage regulator. So it's a black box. And these are 3-terminal voltage regulators, and these could not be simpler. So basically you have an input, which is your input voltage, and typically this is not varying. So this is not AC, it's DC, but it's not regulated. It's fairly stable DC. It's not all over the place, but it can be. That's the purpose of the regulator, is it's going to regulate this voltage and put out a constant voltage, all right? But typically it's just unregulated DC. Then there's ground, which is common to both the input and to the output. So there's a ground line. So we've got V in, ground, and V out, and that's it. So you get one of these little guys and you hook it up. Now, what do these things look like? There's lots of different packages, and we're going to get to those in a second. As a matter of fact, let me skip down here. So there's different packages, this TO220, this TO3, and TO92, and then of course there's surface mount packages, all right? So these are kind of the bigger ones for higher currents for linear regulators, all right? So, and I'll get to what linear regulators are. But anyway, so that's what they look like, and let me grab one here. So take a look at it under the zoom camera here. So right here, we've got, and let's get this camera to cooperate with us. So you can see right there, and you can see the part numbers right on there. All right, and let me get a little bit closer for you maybe. There we go. So it's a UA 78M33C. So this is a 3.3 volt regulator. All right, and then let's see if I got another one here. And then, it's sometimes really hard to read this writing. You got to get things at kind of the right angle and get the right lighting. But I believe this one is let's zoom in a little bit here and see if we can get that lighting for you. Yeah, so this one is 7805, right? So this is a 5-volt regulator. And again, this is that TO220 package. And then here is another small one. This is a 7805, and this is that TO92 package. All right. So when we go to the bench, we're going to look at a lot more of these. So I just wanted you to see those. Okay. So scrolling down here, so we've got this stage 2, which is the regulation, and a regulator is just represented like that. Now, if you take a look at part B here, there's a capacitor on the input and on the output. So when you look at these regulator data sheets, part of the application note will say you need an input capacitor and an output capacitor, bare minimum, so these things will work. Now, when you actually design power supplies, you're going to probably put a lot more than just one capacitor on the input and output. This is like the bare minimum. And these data sheets, so there's some marketing to them. The whole idea is you buy this regulator, the regulator's $1, it's 50 cents, whatever. And they want to say with just these 2 parts, this thing will work. And it will, but it won't work as good as it could work, right? If there are more components, more capacitors, inductors, some other components. And that's why we add to this. And this is a problem because most of these power supply designs that you see on internet are just copied right out of the data sheet, which is the bare minimum. And bare minimum is not good when it comes to electronics. But you cannot run a regulator without an input and output capacitor, as in part A of this figure. You have to have an input output capacitor at very least. And the capacitors smooth out the power, for one thing. And then also, because the regulator is a closed loop system, it needs this capacitor as part of the feedback loop to maintain stability. And so without that capacitor, the feedback loop can become unstable and the regulator can burn itself out. All right, so those are what those capacitors are for. So they're for filtering, they're for noise, and they're for stability. All right, so we'll get to that as we get in more deeper. All right, so again, here are the packages, and typically you're going to see this package right here, or this small package, or a surface mount package. If you have many amps of linear regulation, you'll see this package right here. Now, you heard me say the word linear a couple times here. There are different kinds of voltage regulators, all right? So there are basically three main classes of voltage regulators. Really two classes and then a subclass. So linear regulators mean that ultimately these regulators use resistance internally to burn off the extra voltage. So say you want a target voltage of 5 volts. If you put 9 volts into this voltage regulator at that in pin, so you got V in at 9 volts, you got V out at 5 volts, how it regulates down that 5 volts is it burns it off as heat, so resistively. So it basically switches in resistive elements, and there's a number of components inside that electronically switch it in, and it burns off that voltage so that you end up with a 5-volt output. So whatever current you're running at, say that you're running at 100 milliamperes. So I got 100 milliamperes of current, and I got 9 volts in. All right. So I want 5 volts out. So what do I have to put in the resistance in line with this regulator to make that happen? So let's take a quick look at that. It's a good exercise. So let's go to our drawing program here. All right. So the linear regulator. So the linear regulator is a linear because it basically is nothing but a network inside that switches in a resistive load to drop voltage. All right, so this is V in here, this is V out here, and this is our ground. So ground is common to both input and output. Okay, so let's say that we come in here and we put in 9 volts DC. All right, and let's say that on our output we would like 5 volts. So we go get a linear 5-volt regulator, and there are thousands of them. One of the most popular ones you'll see is the 7805. Now, I won't ever use the 7805 in an actual product, but it's a good representation of a regulator. It's from the 70s. Now they have modern versions of it, but they all are kind of the same, and they're very inefficient. Linear regulators are very inefficient. All right, because they burn things off in heat. So this is a 5-volt regulator. We got 9 volts in, we got a 7805, it's going to put out 5 volts. What are we missing? Let's put our little capacitors in here that we get from the data sheet. So here's C1, and here's C2, all right? And this, the data sheet might say you can get away with a 1 microfarad here and maybe a 10 microfarad there, right? Okay, so now this thing is working, and so it's putting out 5 volts, great. And now we put this thing on a load. All right, so here's a load, and we're going to call this RL, or how about R load? Okay, we got 5 volts, and let's say that this load is 1 k ohm is the resistance of the load. Okay, so the first question that I have is what is the current? What is the current flowing out of here? So I want to know what is I. All right, and remember, there's no current going down this branch. Once that capacitor charges, there's no current, right? So it just stays charged. So basically, the capacitor, some current flows initially, and then it's going to be charged plus to minus, right? So that's going to be kind of a current reservoir, charge reservoir that can be pulled from if need be. All right, so we've got 5 volts, we got 1 K. Let's do some Ohm's law, right? So over here we got V equals I times R. So what do we have? We have V equals 5 volts. We're looking for I. We know R, it's 1K. Divide both by 1K. We have I equals 5 volts over 1K. And remember, volts divided by K are milliamps, but we'll do it anyway. So 5 divided by 1 K ohm equals 5 milliamps. Equals 5 milliamps. All right, so that we know that this current right here coming through here like that is 5 milliamps. All right, so we've got 5 milliamps of current going through there. All right, and we've got 5 volts out here. All right, and we got 9 volts here. So here is the situation. Inside of here, there's this network, this feedback loop that kind of has this virtual resistance, and it's very complicated. It's not a resistor, but we can model it as a resistor for a minute here. And we're going to call this, we'll call this R for R regulator. All right, and so we know that this has to drop 4 volts, right? Because if we got 9, we got 5, 9 minus 5 is 4, it's 4, and what do we know the current is? 5 milliamps, right? So we've got, again, V equals I times R, or R equals V over I. So what's our V? 4 volts. And what's our what's our I? 5 milliamps. And this is going to be our RR. So 4 divided by 5 milliamps, somehow the calculator had the last number in there. So 4 volts divided by 5 milliamps should be 800 ohms. Okay, that's better. 800 ohms. Okay, so this resistor right here virtually is 800 ohms. So the linear regulator kind of generates this 800 ohm resistor electronically, burns it off, so now we've got heat, right? So now what's going on here is this thing puts off heat. That's why these things get hot. So this is, heat, right? And what is the power burned, right? Remember, power is I squared R, or it's V times I, right? It's a lot of different, you can write it all in versions of Ohm's law here, but it's I squared R. So we can figure this out right here. So it's just I squared times R, right? So that's 5 milliamps squared times our 800. All right, so that's 0.02, let's put it in milliwatts. So 20 milliwatts, so approximately 20 milliwatts. All right, so here's the problem with linear regulators. We're burning current, we're burning power just to maintain regulation. And we're burning 20 milliwatts right here, just inside the regulator. To maintain this regulation. So then as we change what this load is, and say we go from 1K to say 100 ohms, right? If we change this load, our load, and instead of 1K, we make it 100 ohms, right? 100 ohms. Then we're going to get 10 times as much current, right? So if we get 10 times as much current, right, this is going to go to 50 milliamps, right? 50 milliamps. We still need to drop 4 volts over this resistor right here, except now we got 50 milliamps. So now we compute this RR. It's 4 volts, but now it's over 50 milliamps, right? Let's do that. 4 divided by 50, and of course, obviously, it's just, 4 divided by 50 milliamps. It's just 1/10 the resistance. So instead of 800, obviously, it's 80 ohms. Right, if we're going to have 10 times more current. Now, what's the power? This is where things get scary. So let's do this I squared R again. So now we've got 50 squared times the 80. So we got 50 milliamps, right, squared times 80 ohms. Now we've got 0.2 watts. So instead of 20 milliwatts, right, or we could say how many milliwatts do we have? We have 200 milliwatts. So, so this is really bad. So this thing's burning all this current, all right? And it's creating a lot of heat. So linear regulators do that. They generate heat and they change this internal resistor. It went from 800 ohms down to 80 ohms through a network of electronics and transistors and so forth. And we're going to look inside of a regulator here in a second, all right? Okay, so that's how the linear regulator works. And like I said, we'll take a look at the inside of one in a second. And then we have what are called switching regulators. Now we're not going to talk about these or do any experiments because they're fairly complex and advanced. But what a switching regulator does is instead of taking the power in from the source, the wall adapter, whatever, the DC source, and just running it through the regulator and then trying to put a resistance in the regulator to compensate for the output voltage that you want and burning it all off as heat, the switching regulator samples the power. So it samples the power at a very high speed, and then using an inductor, it can either boost the voltage up or buck the voltage down. So you can get a higher voltage or a lower voltage, all right? And so switching regulators are very, very efficient. So they only use as much power as they need. So they're up at like 95% efficiency, whereas linear regulators are like 50, 60, 70% efficient if you're lucky, right? Which is a big deal. So if your house is $1,000 a month, right, to power your electricity, say you live in a really hot place, you have the air conditioning on, you don't want regulators that are wasting 30, 40, 50% of the energy, right? You want really efficient, same thing with computers and wearable devices that are powered on batteries. So they're all going to have little switching regulators in it. And an interesting piece of trivia is the Apple computer, the Apple I computer, was one of the first computers to have a switching power supply. So they designed a switching power supply, and that was one of the big cool things about it because it had to be small and quiet and fanless. All right, so those are switching regulators. All right, and then there's also what are called charge pumps. They're similar to switching regulators, but switching regulators typically use an inductor. They use an inductor and a FET and a switching circuit where they run a current through this inductor. The inductor generates a magnetic field, and then the magnetic field collapses, and as the field collapses, current flows, and what they do is they use switches, FET switches, field effect transistor switches, to then drive that current out into a capacitor. So basically you have this little sawtooth wave of this switching circuit generating the voltage. So say here's 5 volts, here's 6 volts, here's 7 volts. Let's do it down here, 5 volts, 6 volts, 7 volts. The switching regulator kind of goes, there's the 5 volts and it just hangs right there. And if you wanted 6 volts out, it jumps up there and hangs around the 6 volts and so forth. The charge pump is a little bit different. These work on capacitors, and they do the same thing. They sample, and then they dump it into a capacitor. So, here's an interesting thing. Let's take a look at the drawing program here, and let me show you something that's kind of interesting. All right, let's get rid of this. So for example, let's say that we had a power source, all right, and a battery, and let's just say that we charged up this capacitor C1 to 5 volts. Okay, so this capacitor is charged. Let's say it's plus to minus, and let's use a different color here. Let's say it's plus to minus, and it's got 5 volts on it. All right, so let's say we had a 5 volt power supply over here. So I got a 5 volt power supply right there. All right, no magic. 5 volts. There's plus and minus. Plus 5 up there, and then this is down here. This is the ground, right? So there's the ground. Let's draw that a little bit better. All right. And so through some switching, electronic switching, we charge up this capacitor C1 to 5 volts. All right. What if at the same time we also charged up this capacitor, all right, to 5 volts? All right, and call this C2. All right, so for example, what we could do is when we just start this thing off, we could put these things in parallel, right? And then I can connect this here, and then I could connect this side here, right? Just like that. And then in some amount of time, based on the impedance of these wires, these two capacitors would charge up. Oh, and we've got it backwards. So you guys, thanks for keeping an eye out on me. Let me make mistakes here. There we go. So that would go to plus, and then this would go to minus. Okay. So we charge these things up. They both have 5 volts on them. All right, great. Now what we do is we electronically break this open like this. We electronically break this open. All right, so there's switches in here like FET switches. All right. And now what we do is check this out. Now this is cool. And now we connect these two like this, and we connect this to ground, and then this becomes, guess what, 10 volts out. How cool is that? So we've got two capacitors, they're both charged to 5 volts, right? So then all of a sudden we got 10 volts right here, I guarantee it, right? So if you take two capacitors, charge them up, do exactly what I just said, tie the capacitors in this way, right? Don't make a closed circuit yet. Don't put any load here yet. Don't do that yet, all right? Do this and you will have 10 volts. All right, so now we got 10 volts. So now we go put a load on here. So let's go put a 10K load. All right, so we got 10K. This system is sitting at 5 volts, right? So here's 5, 4, 3, 2, 1, and 0 volts right here. Here's time here. All right, and then here's voltage here, voltage and time. All right, so this thing starts off and it's at 5 volts right here. All right, so we add this load to it. Now what starts happening here? Well, what do we know? We start to slowly discharge into the load, right? And it's this exponential discharge. And we know that for a capacitor circuit, so this is a R and a C, we know, remember the whole thing, this tau equals RC, and remember this 5 RC time constants. So if you have 5 RC, that's basically going to mean it's totally charged or totally discharged, right? What's RC equal? First, we need to know what are the C's here. So let's just make something up. So let's just say that, let's say these are pretty big. Let's say that they're, 100 microfarad. So they're pretty big capacitors, 100 microfarad. So we know this thing will be totally charged up or totally discharged in 5 RC times, right? So let's figure out what RC equals. So we got R, and that's 10K, times C, which is 100 microfarad. And, oops, let's do that again. 10K times 100 microfarad. All right, that's better. It's 1. So 5 times 1 is 5 seconds. So 5 RC in this case is going to be 1 times 5 times 1 equals 5 seconds. So that's kind of interesting. It'll take this thing 5 seconds to discharge. It'll also, now depending on what the resistance is when the charge, it could take it 5 seconds to charge. But if we have very little resistance, like 0.01 ohms, right, just direct wires going to the battery, it'll charge up instantly. So if it charges up instantly, we can almost charge this thing instantly. Then what we do, after we charge it, we electronically switch the circuit so it looks like this. Then this goes into this output here and then powers the load. So as far as the load's concerned, it's always seeing this 10 volts, right? And then if the load becomes smaller and draws more current, right, then we have to do the switching faster because we got to charge these capacitors up so that we can give it current, we can give this load current quicker. So this is how a charge pump, and again, you can see it's got the switching process. So you basically charge these things up, electronically switch the wires around, and then you dump it into the load. And so from the load's point of view, it just thinks it's got a DC supply of 10 volts in this case, all right? And no one said you have to make the voltage higher. It could be lower. It could be the same as the input, whatever, all right? So that is how a charge pump works, okay? So now there's also another kind of a regulator, which I'm going to show you down here. It's a class of linear regulators, but it's called a load dropout regulator. And so what I'd like to do now is I would like to take a look at an actual data sheet, and I want to show you a problem. All right, so let's go here and look for a data sheet. So we're just going to get a 7805 regulator here. All right, and so I'm on DigiKey. I put in 7805. There's a bazillion of them, and we find a manufacturer we like. So I like Texas Instruments, and I like Fairchild for this kind of stuff, ST as well. So let's also look for in stock, lead-free, RoHS compliant, and RoHS, remember, is a restriction against hazardous substances so that electronics are not too toxic. All right, and then we scroll down here and we've got these parts. There's 9 results, and I'll scroll down and let's find there. Now see, here's some surface mount parts, right? Some bigger surface mount parts, and then there's that TO220 package. And then if you look over here, here is the currents that this thing can output. So 1.5 amp, 1.5 amp, and the output voltage here. So we're looking for 7805, this one here. And these are all positive and fixed, and somehow a 15 volt got slipped in there. That happens sometimes with a search engine. But anyway, all of these, if you look at them, more or less they're the same. And this one right here, for example, this package, It says it's positive fixed, it's 5 volts. You can it can output 1.5 amps of current. It's got 2 volts at 1 amp for the dropout. Let's get back to that in 1 second. That's what I want to bring your attention to. And the voltage input is 7.5 volts to 35. Now, so you see this 7.5 volts? You see this dropout right here? These are related. So what this means is this. If you want to use this as a 5-volt regulator, so we want to use this as a 5-volt regulator, you have to put at least 7 volts into it because it's got a dropout of 2 volts. And what that means is at 1 amp of current, if this thing puts out 1 amp of current, whatever your input voltage is, it's going to require to drop it by 2 volts. So if I put in 12 volts, it's going to end up dropping it down to 10 volts. If I put in 7 volts, it's going to drop it down to 5 volts. If I put in 6 volts, it's going to drop it down to 4 volts and not maintain regulation. So that's why the dropout is really important. And this means you have to have, this is the extra voltage you need to have to be able to regulate. So here it is. So our regulator is regulating at 5 volts. We have to have at least 5 volts in to get 5-volt regulation. So we have to be up here. How much do you have to be above the voltage you're trying to regulate at? That's the dropout voltage. In this case, it's 2 volts. So we have to be at least at 7, and then the voltage spec says, in some of these columns, look, it says 7 volts or 7.5 volts, right? So it's saying, hey, in this case, give me a little bit extra. I even want you to be 7.5 volts higher. And then it says what's the highest you can put in is 35 volts, 25 volts, etc. Anything over that, you're going to burn the thing up. You're going to blow it up, right? Okay, so that's what dropout is. So at 1 amp, there's 2 volts of dropout. That's really actually bad. So that's why switching regulators are so cool, because you can have a switching regulator with the same voltage, a lower voltage, a higher voltage, and you can generate artificially a higher voltage, a lower voltage. So there's no dropout at all. But if you want to use a linear regulator, then they're what are called low dropout regulators, or LDOs. And an LDO is a type of linear regulator, except it's designed so that the voltage that you're trying to regulate, let's say that this is a regulation voltage, say 5 volts, the input voltage only needs to be slightly higher than that for it to maintain regulation. So it's a very efficient design. So let's take a quick look at LDOs. Let's just type in LDO into DigiKey here. Type in LDO and pray that it, yep, good. So voltage regulator is linear, see, and it comes under linear. All right. Now, let's see here. We've got to kind of scroll through here, and let's first, let's say everything in stock, lead-free, RoHS compliant. We got 19,000 components. All right. And then voltage output, let's just say we want fixed 5 volts. So if we can find fixed 5 volts, you can see there's countless voltage regulators. All right, so let's get down here to 5 volts. And of course, when you're doing electronics now, the most typical digital voltage is like 3.3 volts. 5 volts is now kind of done, out to pasture. All right, and we want active parts. All right, so let's put that. And then we're going to say cut tape, which just means kind of loose, or bulk, which means loose. And then how much current do I want? Let's say that we want 1 amp to 2 amps. All right. Okay, and now here's these dropouts. So we can select what dropouts we want. Now look at some of these dropouts. So at 1 amp, there's only 0.19 volts of dropout, right? So these are incredible. So we don't want these 2 volt dropouts. We want really, 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 really low. So we want like a 1.5 amp regulator here. So we got to find one that's at 1.5 and with a really low dropout. So we're gonna start kind of highlighting these in here in this area. All right, we're gonna highlight some of these here, and okay, let's try that again. So that one, that one, that one, that one. Use the control key on DigiKey, that'll get it for you. All right, and that one's got 0.5 volts. That's a little bit high. All right, we'll apply filters. All right, and we look through here and we say, hey, we really like ST Electronics this week. And we look at what ST's got, and they've got these components right here. So as a matter of fact, I got one of these right here over on the bench, and we're going to work with that shortly. So the part number is this LD29150. Let's go take a look at that. All right, so it looks like that. This is a surface mount component. It's called a D-Pack. There's a D-Pack and a D-Pack 2. But this is an LDO. And so what's amazing about this is it puts out 5 volts. We can get 1.5 amps out of it. But instead of like the 7805 that had a dropout of 2 volts at 1 amp, right, or 1.5 amps, this only has a dropout of 0.4 volts. So what does this mean? This means this. First, we can have a smaller power supply. So instead of having like so the typical power supplies are like 5 volt, 6 volt, 9 volt, 12 volt. There's nothing really that's 7 volts, right? You could find one, I'm sure. But so you get these DC wall warts, and the problem is if we want a 5 volt voltage and we've got a dropout of 2 volts or 2.5, that means we need like a 7.5 volt wall wart, right? Well, the closest thing to it is a 9 volt. So we got to put 9 volts into the regulator. And we want 5 volts out. What does that mean? We're burning the 9 volts. We're burning 4 volts all the time to get out our 5 volts. But with an LDO, we could put a much lower wall wart input voltage and still get our 5 volts regulated. So we could put a 6 volt wall wart in there, maintain our dropout voltage of 0.4 above the voltage we're trying to regulate at, and we get 2 things. One, we burn less energy, right, because we're only at 6 volts input, and then 2, the transformer is typically cheaper. So this thing is cheaper if it's 6 volts rather than 9 volts or 12 volts, right? Okay, so you get this double plus. Let's take a look at the data sheet real quick. Let's zoom in here a little bit. Okay, so again, very low dropout, 0.4 at 1.5. That's actually very good. All right, and then you kind of scroll through here. Here, and so now let's take a look at this circuit diagram. So here's a block diagram, and there are probably hundreds of transistors and components inside of this, but just in general, these are the blocks, and it's showing you these blocks. So this right here is a op-amp, an operational amplifier, or an amplifier symbol. Thermal protection, that could be a sensor and some transistors. Current limit, startup, dump protection, voltage reference. So a lot, and this is the adjustable version, a lot of components in each one of these blocks represents dozens or hundreds of components, right? Okay, so that's kind of what I was saying. These things have a lot of components in it. And then showing you the pinouts. But what I want you to really see here, and here's your typical application notes. So again, it's saying, hey, you can use, now they've got 2 different versions here. They've got a fixed version and an adjustable version. So this is something let's talk about real quick. The fixed version just means they build it with an internal voltage reference so that the voltage is fixed 3.3, 1.8 volts, 5 volts, whatever, right? That's this version. And it's super simple. There's 3 inputs here. There's your input voltage, put a capacitor. They're saying 0.33 microfarads will do, ground, and then put a 10 microfarad on the output. Okay, and then there's this other line right here, which is the inhibit line. And what this does is, say you're building a complex system that has multiple power supplies internally, and maybe you don't need that 3.3 volt or 1.8 volt power supply on. So right now, so you can send a digital signal to turn it on or off with this inhibit line. So when this inhibit is high, it turns this on and then starts working. Because remember, even when you're not pulling any current from it, it's going to burn power, right? Okay, that's what these inhibit lines are for, or enable lines. Now, here is the adjustable version. This is really cool because you just simply put 2 resistors here. And these 2 resistors create a feedback loop to this adjust pin. So this one's got 2 extra pins. It's got the inhibit and this adjust pin, different from ground. And you put these 2 resistors here. And then this little equation says V out equals Vref times 1 plus R1 over R2. The arrow on R1 means you can make that the adjustable one, but we suggest, as the manufacturer, you make R2 fixed and you adjust R1 if you want to do that, and they'll probably tell us what R2 should be. This Vref is something else they're going to tell us, and it's usually like 1.25 volts. It's usually a voltage generated by what's called a precision reference. Now, because you're doing an adjustable voltage regulator, these resistors need to be precision resistors. So they're usually going to be 1% or 0.1% resistors. And we would like these things to not change their resistance when they get hot or cold. Okay, so there are resistors that are basically, as they get hot, their resistance would change, so they compensate themselves so they stay stable. They're more expensive, all right? So those are the kind of resistors you want to use there. So again, if you scroll down here a little bit, then we go through, some of the data sheet stuff, and then the one thing that I wanted you to see is this. So this little thing is this V drop, and so this is the dropout voltage. So it's saying at a current of 250 milliamps, the dropout is only 0.1 volts, meaning you could have 5.1 volts on the input, and I can maintain 5 volts at 250 milliamps in this temperature range. That's awesome. All right, so now if you wanted 750 milliamps or 0.75 amps, I'll go up to 0.2 volts as a dropout. 1.5 amps is 0.4. All right, and the max is 0.7. So that is really, really wonderful. So bottom line is, if you just have a 6-volt wall wart to power your 5-volt supply, as long as you use an LDO regulator, you're good to go. All right, and they're not more expensive by any means. All right, so if you see here, there's one for 84 cents, and at 100 they're 58 cents. Okay, and then if we go to that 7805 again, we'll go to 7805. Right, go to the 7805, and just quickly we'll just go to the 1.5. We'll go to here. We'll go here, and we'll say in stock, lead-free, RoHS, go like that. All right, and we'll kind of find one that we're looking at. Let's just go look at this one right here. Now this is another ST part, which is really good. Let's look at a Texas Instrument version. So actually, let's go here and say Texas Instrument. All right, and do we have the TO220 package? Yes, right there. All right, and now you look at this right here. So at 500, it's 30 cents. It's a teeny tiny bit cheaper. And so just for 10 or 15 cents more, we get the LDO version, which is way better, way better. So you want the LDO version. Okay, let's go back to our text. Now what we're going to look at here is example power supply designs. So this is I don't want to rush through this, even though we're just kind of going through the text before we get to building things. I don't want to rush through this. I want to talk about this a little bit. So let's stop this lecture right here. This is a good stopping point. Let's start back up on example power supply designs. Okay, so I'll see you back in just a minute, and we'll talk about this. All right, bye. All right, welcome back, and we are continuing with the coverage of the power supply designs in this lecture. And what we're going to do is we're just going to look at the material in the book on paper here and just kind of peruse and skim through some of these designs to kind of see where we're going. And then we're going to get on the drawing program and go work over on the bench. Probably in the next lecture, we'll actually start building stuff. But in this one, we're going to still cover some more material in the book here, chapter 3, and this is a 3.8 example power supply designs. Now these are just some examples, so I want you to read the book, but there's a million ways to do this stuff. So the whole idea is just showing some general ways of designing power supplies and just some ideas, but we're going to augment this with some drawing and work on the blackboard. Okay, so let's get started. So previously, we looked at the different voltage regulators and whatnot, and so now we kind of have that information, and so we're going to go through some of these power supply designs. So we talked about the 7800 series regulators and the 7805, for example. And here's just an excerpt from one data sheet. I believe this is, Texas Instruments. So if you go on to DigiKey, you could look at this data sheet and showing the various packages and so forth. All right, so what I want to do here is I want to just kind of look at some of these designs that I have here inside of the book, and they're real general and real simple, and we're going to kind of add to them and so forth as we discuss this, and then we're going to build them. All right, so let's just get right into it. Okay, so in this example, we see a 7805, for example. So we're doing a 5-volt supply, and we've got a VIN of 9 to 12 volts DC. So we're assuming there's DC, so notice there's no bridge rectifier in this design. Okay, and then on the input here, in this particular example, it shows 0.1 to 1 microfarad ceramic capacitor, And then on the output, there's a 1 microfarad tantalum and a 0.1 microfarad ceramic. So in this case, and then we've got V in, V out, and ground, 3-terminal voltage regulator, very simple linear regulator. So on this input, so these are the bare minimum requirements, right, to get this power supply to work. So on this input, we might actually want to make this a 1 microfarad, right, and then maybe also put in parallel a 0.1 microfarad. Same thing on the output, we've got a 1 microfarad and then we've got it in parallel with a 0.1 microfarad. So by having the different capacitors, so remember capacitors add up in parallel. So the question is, well, Andre, why not just have one capacitor that's 1.1 microfarad, right? Something like that. Well, the reason why is each one of these capacitors is a different path and a different impedance. So what we're trying to do here is we're doing two things. We're giving noise a low impedance path to ground so it doesn't get out our power supply rails. And then the larger capacitor is also for a source, all right? So when the load over here wants a lot of current, normally it has to go all the way back to the power supply, and then it's got to pull the current from the power supply, and the power supply has got to react, and it's got a finite reaction time. So as it's trying to react to give more current out, the voltage isn't going to stay at 5 volts, and it's going to adjust, and then it's going to give it the current, then it's going to adjust back to 5 volts, and it's going to stabilize. While all that's happening, we're not getting really clean power. But if we've got a big capacitor here, then when we pull that at 5 volts, we pull that current from the load transiently, we can get the current from that capacitor, that storage capacitor. All right. So typically, what you want here is larger capacitors. So you might want on the input here, you might want a 10 to a 22 microfarad capacitor along with a filtering capacitor of 0.1 microfarad. Same thing with the output. You might want a 10 to 22 microfarad capacitor and then another 0.1 for filtering. Now, if you're going to have really big current surges, like say motors, inductive loads, things like that, you might want a much bigger capacitor like 100 microfarad, and then we'll put a capacitor at the load also, and I'm going to show you that. So all right, so that's just one simple design. So what we're trying to say here is, hey, have a capacitor on the input, a couple capacitors on the output. One is large, which is a storage capacitor. One is small, which is more of a filtering capacitor. All right, because remember, capacitors pass AC, so they like high frequency, so high frequency noise goes to ground, all right, and then this is a storage capacitor, and then not drawn here, we might have another capacitor and make this a big one, like a 1, 10, 22 microfarad, and then have a smaller 0.1 or 0.01 microfarad, and we usually do things in orders of 10, all right, 1 microfarad, 0.1, 100, 0.01 microfarad, and so forth. All right, so let's go and see what the next little design is here. All right, now, most modern linear regulators or LDOs have a lot of protection on them these days. But if it's a really, really cheap part, it won't have certain kinds of protection. So in this design, we see we've got our 1 microfarad here, fine. We've got our DC coming in here on the left. Then we've got a 1 microfarad output and a 0.1 microfarad in parallel here, all right? But then, and we've got our 5 volts, and we got a 7805. But we see these two diodes. So if you read down here, what these two diodes do, they're for this purpose. Let's say, for example, that this, say we've got 9 volts right here, right? And so that's 9. And this output is usually 5 volts, right? So this diode right here is reverse bias. We got 9 and we got 5 on the right. Well, now let's say that somehow we inject 12 volts on this output. Something happens and there's 12 volts put on that output. What's going to happen is that 12 volts is going to be applied to this V out, and it could damage the regulator, right? Because the regulator is doing the output, but if you drive current into here at a higher voltage, you could damage it. So that's what this reverse voltage protection is for. So if somehow this becomes very highly positive, instead of current going through the regulator, it will shunt around the regulator through this diode. Now, most modern regulators have this feature, reverse voltage protection or shunting, built into them now, but if they don't, you can put this diode there and be safe. Now, this diode, this D2, if you read here, D2 is for output polarity reversal. What this is for, so we've got plus here and we've got minus here. Again, let's say that somehow something is attached to plus and minus and it reverses this polarity. In other words, it makes minus much more positive than this positive. So what's going to happen there is that's going to potentially damage the regulator also. So if this becomes very positive and this becomes very negative, what it's going to do is it's going to forward bias D2. Then D2 becomes a shunt, and the current shunts around the regulator going through D2. So these are just protection ideas, all right? Just a couple protection ideas, all right? Okay, let's move on. Okay, so this is a big important subject. So we're not going to talk about doing thermal calculations in as much as when you're doing a kind of a circuit design and components and computing power, you can actually model the circuit components and you can compute heat flowing around the circuit. So heat is analogous to current and voltage. So you can actually, there's analogies to resistance and current and voltage where you use heat. All right. So there's what's called thermal resistance and various factors like that, so that we can compute how much heat can flow out of a component. So, but we're not going to it's a little bit too complicated. I don't want to talk about it. But the bottom line is when you look at a component, it'll say how many watts this thing can dissipate. So it can dissipate 1 watt or 2 watts or 3 watts or 0.1 watt or whatever. And then it'll say to ambient air. So if you've got a component and it's just got ambient air around it, it could dissipate, say, 1 watt. If you put more current through this thing, say 2 watts, then it won't be able to dissipate and it's going to start heating up, all right, and overheat possibly and burn up and damage itself. So what we can do if we think we're going to run things hot is we can put heat sinks on them, all right? And so here's some pictures of some heat sinks, and these just go right on top of that TO220 package, right? So so let's go take a look at some of these heat sinks up on the zoomed in screen, and so you can see what I'm talking about here. They're pretty cool. So let's go over there. Okay, so here is the TO220 package, and let's see if we can see that one. This is a 78M33, so it's a 3.3 volt linear regulator, all right? And here's another one here. Let's see what this one is. This one is a, zoom it in there. This one's a 78 MO5. All right, so we got a 5 volt, which is kind of the gray one, and then we got a 3.3 volt. And the point is they both are in the same package here, okay? Both in the same package. Now, so now let me show you this. This is some of my goodies right here. So these are heat sinks. And what I'm going to do is I'm just going to pour them out for you so you can see some of them. So lots of different kinds of heat sinks here. Kind of fun. I always like heat sinks. So here's a bunch of different heat sinks. And you can see some of these are going to be good for processor chips that are more rectangular, and then some are for these devices themselves. So for example, right, and most of these are made out of, they're usually made out of aluminum. They have adhesive on the back. This adhesive, it's been pulled away, so that adhesive is still there. Here's another one right here, same thing. You can see that metallic adhesive, all right? And so this, for example, hooks on specifically to one of these. And how it does it is like this. So it goes just like that, and then there's a screw, so you would take a screw and nut, and you would put it right through the back there, all right? And as you did that, then now this thing has this heat sink on it. And then you would place this inside of your circuit board, and you could also place it flat. You could bend these leads and place it flat. But the point is that this makes a larger surface area to dissipate heat, so this thing will not get so hot. So here's the rule of thumb, and I want you to remember this. If you cannot put your finger on a component on a circuit board, it is too hot. If you cannot hold your finger on there, it's too hot. If it's uncomfortable, that's one thing, but if it's too hot to hold, it's too hot. So you don't want to run things that hot. Now, a lot of times the specs will say it can run at very high temperatures. Do not do that though, because I think the statistic is every 10 degrees Celsius things will fail 50% more. You don't want things running hot. All right. So again, let's look at some of these other heat sinks here. Here's a good one. Where is it? This one here. And this is another kind, and this is a snap-on. So you can see inside there's kind of a little guide, and then you push this in, and then it snaps just like that, and then there you go. So this one does not require the screw and nut. All right, so that's another, and then you just kind of pull it open and get it out. All right, and then there's some other interesting, and then here's a bigger one, for example. So say we need more heat dissipation, so we use the one on the left instead of the one on the right, but again, it's still for this device. Put it right in there. And with heat sinks, you know, you can use them for different things. I mean, if I really, really, really wanted to, what I could do is say I really needed to cool this thing down, right? What I could do is I could cut this. I could go get a saw, right? And I could cut right through this, and I could cut off a piece of it, a little rectangle of it, and I could mount it right on the back of that with a adhesive, all right, with a silicone, usually silicone RTV adhesive. Now, here's another kind of heat sink, and again, you know, you can use these where you want. I mean, you could if you really wanted to. Say this was mounted on a PCB and you wanted to, and you wanted to do something. You could do that if you wanted, right? Nothing wrong with doing something like that. You know, you could do like that, and again, use an adhesive, a silicone adhesive that's conductive, heat conductive, to mount it. All right. Now, let's see if we've got some, and then again, you can see it's all about surface area. So these, let me pull this away if I can. Stuck on there. So this one you can see is really flat, so we might want something flat, and then this one is a little bit, and of course, you know, hairs and carpet get all over things. There's no way around that with adhesive. So you can see that's flat, and that one is thicker. All right, and then this one I believe is even thicker. See? All right, so some heat sinks there. Now there's some other ones that I have here that I want to show you while we're doing this. So for example, here's a little package of them. And then if we look at the part numbers here, let's see what these part numbers are. You could look this up. This is a DigiKey part 3451101-ND heatsink BGA PGA. So these are for rectangular, you know, processing chips or rectangular ICs. But doesn't mean we can't use them on, you know, anything we want, really. All right. But they're really, really neat because, so they're real small like that. And again, you know, we could, if we really wanted to, if we really needed a lot of heat sinking, we could put that, after we mount this on our PCB, we could put that right on there with adhesive. There's adhesive on this, but we could put it right on there, and we could surely cut it up into pieces. All right. Now, there's another one, and these are cool. I want to show you these. These are for ICs. These are for small ICs. So let me show you this. I just want you to get an idea. You get, you know, heat sink things. Nothing wrong with heat sinking things, especially if they're going to get hot or you think they're going to get hot, because it's simply going to make it last a lot longer. And plus, when things don't change too much from ambient temperature, then you don't have to worry about their values, their speed, their resistance, and all that changing. So ultimately, we'd like things never to change temperature, because then there's going to be no variance. That's what we want. We want things to stay the same. So let me find a chip here. Let me find an IC. All right, so I'm going to find an IC. I just grabbed some random IC, and I do not know what it is. Let's look at it. This is an MCP 3204. 3204. I think it's an op amp. I can't remember. So you could Google that right now while I'm talking, MCP, but this is a microchip part, 3204. Maybe it's an op amp. We'll look at it after. All right. But what I want you to see here is, so let's say say this is a driver chip, right? Say it's a driver IC, something that's going to get hot, right? It's driving a motor maybe. It's inside the printed circuit board, and we're just like, this is getting too hot. Well, check this out. See this? We just put some silicone RTV, some silicone on there, and then we would then glue this on, just like that. Obviously let it dry, and then there you go. And then now we've got that heat sinked. So that's what we want to do, is heat sink things if we need to. Now, another thing, let me show you something else. So we're going to be talking about transformers some more as we do these designs. Here's a transformer, right? And these things will get very, very, very hot. Now, this is a big iron core, right? Typically an iron core, and with these coils inside of here for the transformer. So this will get really hot, but you notice there's no fins on it, because that costs more money, right? So say this is getting just too hot, and we're like concerned about its heat, it's going to melt something or whatever. So what we can do is, and I've done this many times, is these are really nice because they go just perfectly on there. So what we can do is we can just glue some of these on wherever we want, and we can heat sink this, or we can take one of these big guys right here, and if you want to get really fancy, we could cut a hole out, we could shape it right, and we could put it right on there and heat sink this whole thing. So you can heat sink the transformer also. All right, and a lot of times that's a good idea. So I want you, when you design power supplies, Test it. If it gets hot, if it's too hot to touch, it is too hot, and I want you to heat sink it. And just do that as a rule of thumb. So get in the habit of using heat sinks. They're your friend. They're a little bit expensive. This is aluminum. It's anodized. It's machined. It's, you know, they're expensive. These things are probably, I don't know, 25, 50 cents each for these little ones. And then, you know, this is probably like $2, $3, $4. It depends. So not cheap, but you know, they're very important and very useful. So definitely add them to everything. So I'm not going to add any heat sinks usually to what we're going to be doing right now because they're going to get in the way of our work. But I want you to know that I'll just say, you know, hey, and you should add a heat sink. You'll know what we're talking about. Okay. All right. So let's go back to the blackboard and let's keep going. Okay. So we've talked about heat sinks here. And so now this is a design that's using a 7812. It's exactly the same as a 7805, except that it's a 12 volt regulator. So again, we take the same design and it's almost identical. We've got 1 microfarad, 1 microfarad, 0.1, and then we've got our 2 protection diodes. Again, we're just assuming a very crude 7812 instead of kind of a modern 7812 or 7805 that has these protections built in. And then, but now since we're regulating down to 12, this is saying 18 to 24 volts. The reason why it's saying 18 to 24 volts is because typically when you have these wall warts, there's no such thing as like a, well, there's not no such thing. There's anything you want if you really want it. But common voltages are 6 volts, 12 volts, 9 volts, 18 volts, 24 volts for the wall warts. And so probably the smallest that we can find that's greater than 12 that's got a dropout or it's got a voltage high enough to maintain the dropout of the 7812 is like an 18 volt to 24 volt wall wart. And then we would use that and then we would get our 12 volts out. Now, again, if we were going to build this in reality, we wouldn't use a linear 7812. We would use a LDO version. So it's a low dropout version, remember that, so that we can have just something barely over 12 volts. So we could find a, if we were lucky, if we could find a 14 volt or 16 volt, but still kind of difficult wall wart, then we could power it from that. But we always like LDOs, all right, because they can maintain the output regulation invariant or when even when the input is just barely above that same voltage, right? A couple hundred millivolts. Okay, now in this case, because we're talking about 12 volts, definitely these capacitors here, again, if you look at the reference design, they'll show you these really tiny capacitors and say, oh, it'll work like this. Again, that's marketing. All right, that's the bare minimum. So, and that's what I'm showing here. But we want bigger capacitors. So me, again, if I were to do this, I would say, hey, let's make this a 10 to 22 microfarad, maybe even 47 microfarad. Same thing here, make it 10 to 22 microfarad, maybe 47 or 100 microfarad if we've got some big currents getting pulled out of here. And then I'd put a 0.1 microfarad in parallel for noise and another 0.1 on the input also for noise. And then I'm going to show you some extra stuff that we're going to add to these too. These are just, you know, references here inside the book, but we're going to even make these better. And again, we don't have a bridge rectifier on there. All right. Now, this is just an example showing a 3.3 volt regulator. So now, you know, obviously nowadays voltages are smaller, which reduce the power. And so the voltages that you're going to see common in digital electronics these days are the 3.3 volt level. So if you're playing with Arduinos, most of the Arduinos run at 5 volts. And 5 volts and 3.3 volt systems can sometimes be tolerant of each other. In other words, a 3.3 volt can usually drive a 5 volt system because in digital, a 1 is typically a little bit over 2 volts. So if you have anything over 2 volts, 2.5 volts, then that's going to register as a 1. That's okay. But if you take the 5 volt and drive it back into a 3.3 volt input, you can damage it. And so whenever you're working with an IC, it'll say it's tolerant of 5 volt inputs, even if it's a 3.3 volt system. And again, we haven't gone into digital, so we don't really know too much about what I'm talking about right now. But there's 1.2 volts, 1.5, 1.8. 3.0, 3.3, and 5 volt systems are now kind of all the different ranges of voltages. The most typical we're going to work with are 5 and 3.3, and sometimes you'll see 1.8 in the core of something, but you're not going to work with it in I/O usually. All right, so this is just a 3.3 volt regulator. It's a low dropout, but it's very low power, 100 milliamps. Just a random one that I picked. There's thousands of them, as you know, and you could just look this up on DigiKey if you wanted to. We'll just copy that real quick. We'll go to DigiKey over here. We'll type it in, copy and paste it, and there it is. And the reason I wanted to show you this, though, is because it's this little teeny tiny package, right? So this package right here is called an SOT235. And the reason it's called an SOT235, 2 pins, 3 pins, total of 5 pins, SOT235. It's surface mount, very small. Now, this one only can put out 100 milliamps, but there are, you know, different versions, thousands of these ICs that are still small SOTs like this that can put out half an amp, maybe even an amp, amp and a half if you really wanted to look for it, all right? Now take a look here though. This is a positive fix, 3.3 volts. The voltage input is up to 10 volts and the dropout is right here. So at 100 milliamps, if you're putting out 100 milliamps, the dropout is barely 0.1 volts, so 100 millivolts. So that's pretty good, 100 millivolts when this thing's at its full current. So basically, as long as you keep the voltage at about 3.4 or greater, then it'll continue regulation. So this is really good is to use, say, with a lithium-ion battery, right? Lithium-ion batteries tend to start off at about 4 to 4.2 volts, and as you discharge them, they go down to about 3.7, 3.5, 3.4. If they get down to like 3.3, they're usually dead. So you can just take a lithium-ion battery, connect it directly to this, and this will regulate it down for you, which is nice. Let's take a look at the data sheet, the full data sheet. All right. Now, one thing I want to bring to your attention here is that when you look up these data sheets, we just clicked on one data sheet and we're like, what's going on here? We've got like 14 different data sheets because it's a class of regulators. So there's 1, 2, 3, 4, 8 of them here, 8 of them. So there's 8 of them that it talks about in this data sheet because they're all similar and they have different features. And their features may be different voltages, right? You can see here's all the different voltages, 1.2, 1.5, 1.8, 2.5, 2.7, etc. All right, and then some of these pins may do different things. So in this case, here's the output, and here's ground. Here's an enable pin. And then this one right here is either no connect or FB, and FB means feedback for the adjustable version. So if we scroll down here, all right, scroll down. Again, here's one of our block diagrams. And remember, there's dozens or hundreds of components that we don't see, but these are just kind of block diagrams. Here showing, let's take a look at, here we go. So this right here, here's something. So see this little table right here, the dissipation rating table. So this is talking about that heat dissipation. So it's saying, this right here is, it's saying what is the board made out of, a low K or a high K, and that's the thermal conductivity, K, the constant. And then it's saying what the package is, this DBV package, and that's just a package from TI, and it means that SOT package. And then this is resistance, the junction resistance, all right? And these are these values I was telling you about. It's like an electrical circuit. So see this resistance value from junction to ambient, J to A, that's what this means, junction to ambient, is 259 degrees Celsius per watt, all right? Forget about this derating thing. And then it's showing at different temperatures. So if here is what ambient is, T ambient, T ambient, T ambient. So if we're at like 25C, right, which is kind of, you know, room temperature-ish, this thing can basically boil off 386 milliwatts or 555 milliwatts, depending on the board. So if you've got a really low K, meaning if the board has poor thermal conductivity, it's only going to be able to burn off 386 milliwatts because this IC is going to be soldered on to the board. It's going to be soldered onto the board, right? But if it's got a high K, if it's got a higher thermal conductivity, then we're going to be able to burn more off. So we'll be able to burn off half a watt, right? Now, if we put a heat sink on there, we'll be able to burn off even more and keep it cooler, okay? But anyway, you can read about doing these thermal calculations and what these values mean and how to do this stuff. But I've confused you enough with electrical circuits, and I don't want to do thermal circuits. Maybe that's another class, all right? Okay, so anyway, and it's just showing for all the different components. And then what I wanted to show you was if there was a reference design. There, yeah. So device operation, so here's the input, there's our enable. So this is enable, see the bar over it means low. and then it's active low. And again, we haven't really got to digital electronics, so whenever you have a signal with a bar over it, it means it's asserted low or active low. And then this goes to ground, so that's always enabled. Then 2 is ground. Here's the output. Pin 4 is unused in this particular case. And then it's saying 1 microfarad here on C1, and then it's saying, go ahead and put a 4.7 microfarad. And then what this is saying is that all the capacitors, basically they have resistance in them, right? Remember we talked about that, there's resistance in capacitors. So this is the equivalent series resistance, and it's saying a 4.7 microfarad with an equivalent series resistance of 0.2 ohms. So why this is important, you've got to be careful with some of these regulators, and you have to read about this, is it's saying that it needs to have this or this thing will start to oscillate potentially. So you got to be careful, you got to read about it. And then if it's very specific about what the input and output capacitors have to be, then you follow its direction. If it's just giving generalities, then you're okay. But it might say that it has to have an ESR of 0.2 or less or 0.2 or greater, and you would read this. Then when you pick your capacitor, you make sure that it has that series resistance of 0.2 less or greater in this particular case, right? Okay, and then it's showing you these requirements, although not required, a 0.047 microfarad or larger ceramic input bypass capacitor between in and ground is recommended for transient response. Now, although not required, it is required, or it'll just have horrible performance. So what they're trying to do there is, again, it's not absolutely required, but it just is not going to work as well when you have transient response or noise, and of course we want it to work well in those cases. So this is kind of these data sheets getting into marketing speak and saying, oh, it'll be okay, but it'll probably be better with this, but they want to say it uses the least amount of parts. So be very, very careful reading these data sheets. Now, like all low dropout regulators, the TPS 769 requires an output capacitor connected to out and ground for the internal control loop. And the minimum recommended capacitance is 4.7. The ESR of the capacitor should be between 0.2 and 10 to ensure stability. Capacitor values larger than 4.7 are acceptable and allow the use of smaller ESR. Capacitance less are not recommended because they require careful selection of the ESR. So the point here is, I'm going to use a much bigger capacitor, like a 10 to 22, all right, and then it'll have a smaller ESR, all right. And then typically you can use either tantalum capacitors because they have a low ESR, or you can use ceramic, but you got to be careful. Ceramic capacitors have a very small ESR, and if the ESR isn't what it needs to be, then that will cause a problem potentially in that output loop, because remember, this is a control loop that maintains the voltage. And then this is the equation for the variable or adjustable version, right? And they all look the same. They're all a V reference of some kind times usually 1 plus R1 over R2. And this is basically a feedback loop. And whenever you do these feedback loops and these amplifiers and whatnot, this math always kind of comes out of it. And then you got to look, what's this VREF? Oh, it's 1.224. And this is an internal reference voltage. And this is typically from what's called a precision reference, which is usually based on a diode, something like that, that always creates 1.224. And they use that no matter what the voltage is in the system. I've always got 1.224, no matter what the current is going through it. And remember, diodes have that property. Their voltage doesn't change that much over a wide current, and we can use it as a stake in the ground as a reference point to guide ourselves, because we really don't know what voltage we're at unless we have something that we always know the voltage no matter what the current, no matter what the voltage of the system. Okay? All right, so anyway, so that's that. Let's go back. All right, and so again, low dropout regulators are what you're going to prefer to use. Don't use just straight linear regulators. They have too high of a dropout. They're too inefficient. They don't have really cool features, and they're just kind of old school. So use LDOs for anything if you're going to use a linear regulator. They're going to be a little bit more expensive, the LDO, but it's totally worth it. All right, one thing, kind of a sidebar, is when you start working with components, modern components, back in the 70s and 80s, 90s, everything was in a DIP package, a dual inline plastic package, right? Like the one that we just looked at, and we put that little heat sink on, right? Like this. And I can never tell if this is focusing, but anyway, that's a DIP package. It's made out of plastic. It's dual inline because there's 2 rows of it, and these come in all kinds of different sizes, all right? And the problem is when we get to surface mount components, as a matter of fact, let's go to the zoomed in screen. So here on the zoomed in screen, let's take a look here. And these are obviously surface mount components. These are actually regulators. And I'm just going to take one out for you. And just to give you an idea of how small these things are, right? These things are tiny. This is huge compared to some of the components I work with. So let me zoom in there. So look at that. And then you can see there's some markings on there, right? And let me turn it over. And let me try and orient this a little bit. And this is not easy to do looking through the camera lens and stuff. So let me get this around here for you. All right, let me get it to lock in. And let's go ahead and zoom it a little bit. See if we can get it. Yeah, 86SS or maybe 5598, right? If it's the other way around. Yeah, I think so. Yeah. So it's S59, and I can't see that through the camera, but it looks like a 6. Anyway, whatever it is. So now that now here's another problem, everybody. And this is an important little detail. So I've got this little thing right here full of these chips. I have no idea what this is anymore. This marking means nothing. That's a manufacturer marking, and if you have the manufacturer's data sheet, it'll say that marking means this version of the chip and so forth. So the point is that try and keep the packaging with everything or you'll lose them. All right, now, so we got this teeny tiny little guy, and you can see how easy that is to lose. I mean, this is tiny, and like I said, this is actually big. All right. Now, how on earth do we mount this, right? It's not a dip package, so we got to mount it somehow. So what we end up doing is we mount things on these little surface mount boards. Let me see if I can get that to focus. So here's a little board, and see how this is a surface mount part, but then it converts it to have pins so I can plug it into one of the solderless breadboards that we've been working with. So this is basically a surface mount to through-hole converter board, and there's all kinds of them. And let me show you let me show you a few of them. Let me put this back real quick. I've got a little tub here. I've got hundreds and hundreds of these and boards full of them. Let me kind of show them to you here. They'll zoom in. All right, so these are little surface mount adapters, all right? And they come in hundreds of different shapes. So these are for passive components. So those would be like capacitors and resistors right there. And that would be for an IC. So that would be like for a TSOP. It says TSOP 8 or an SOIC. And we would solder it there, and then we would put pins through there so we could put it in a board. And they come like this because they're so tiny, right? They just make the boards like this, and then they score them, and then we can break them apart like that. See that? All right, and then use these and then mount things on these. So basically, if we wanted to mount that little chip that we just had, we would go through all these and try and find. Now these are mostly for ICs, so these aren't kind of what we want. But the whole point would be we'd have to go through and find what we want, and then solder it on there and get it going. And you can see, here's another one with something soldered on it, right? And some pins. These are all regulators we're going to play with later, all right? And then here is another regulator, and this is a TPM010, TPPM. I believe this is a 3.3 and 5 volt hybrid. So this puts out both. So now this one though, so we want to mount it. So like maybe something like this might work, right? So we'd have to go through our parts and match what kind of footprint this is in this, and then solder it on there. So that's how you have to work with surface mount stuff, right? Now, the reason I brought that up, let's go back over to the blackboard, or back to the computer. So the reason I brought that up is right here, these are SMT surface mount to dip converter PCBs. And you can make these if you want. So if you really want to, you can make these. You can make 100 of them, and you can send them out to a low-cost manufacturer, Seed Studio or PCB Fab Express or Pentalogic or PCB Card or Golden Phoenix. There's lots of them. And you could actually make these yourself. There's no reason you couldn't. If you buy them, they're quite expensive. These boards are, this is like a $50 board probably. And you're like, oh, wow, that's expensive. Why is it $50? Well, how many people on earth do you think need these? Not a whole lot of people are building hardware, so they charge a little bit more for them. But they're really, really good. This company that makes this is called Belden Dynamic Systems, and it's beldinsys.com. All right, let's see if we can find this, because every time I go to this website, I end up someplace wrong. beldinsys.com. Let's see if I can spell right. Yeah, I can. All right, so the first thing you're going to notice when you get to this website is this looks like it was made in the 90s, right? It's a very old school engineering kind of website, but this is it. So we go here, prototyping products, click on that, and then you can start to see here's all these boards. And I have a bunch of these right over here, right behind me. There's a bunch of these. I have every single one of them, many of them. And so then you go through here and you say, you know, what do I need? You know, I'm working with certain things. I'm working with TSOP, I'm working with this, I'm working with that, or I just want kind of a hodgepodge. And if you keep scrolling through here, you can see there's like all these, you know, little guys here and just everything you can possibly imagine. So let's go back up here. All right, this one's here is kind of a small SMT and modules, and then this one's small SMT. So this might be a good one for some of the stuff that we're trying to do right now. So we click on this. And this one's good for all these different things here. So if we zoom in, it's got 10 each of the SC75 footprint, the SOT23 footprint. That's what we need, the SOT23. We're just looking at that, right here. If we go here, this is the SOT23 footprint right there, which TI calls the DBV. And don't try to remember all these things. It's literally impossible. Everybody makes up their own stuff, so you kind of have to look it up. This is kind of standardized, but DBV is a TI thing. Let's go back to, we just lost the page. I hate browsers. Okay. So there's SOT23, there's 323, 143, 336, all these different things, and it's saying, or they're called, or it's called, or it's called, and how many of each there are. So if we like this right here, then you just go ahead and buy this, and they're not cheap. So this B513, and again, I like doing things in real time. I don't like cheating you. Let's see if we can buy this off Mouser. So let me open that in a new tab, and I usually buy them from Mouser because I'm here in Austin, Texas, in the United States, and Mouser is literally a city away, so things get here the next day, even if you don't pay for it to get here the next day. Okay, so it looks like it found that part number, all search results, and okay, passive connectors, wire cable, electromechanical, prototyping products. Aha! And there it is. So that's what we want, and look at that price. $45 for one of these. Ooh. So you could potentially, if you wanted to, make a board similar to this, right? You could make a board similar to this with all these components on it, and then if you sent it to a Chinese manufacturer, you could make 10 of these, and maybe they're only going to be $10 each. So for $100, you could get, 10 times as much product, right? And then you could use them for a long time, or maybe sell them to your friends, right? Or give them away to your friends, whatever your level of entrepreneurship is. All right, but that's what you need to do surface mount stuff. All right, is you're going to need these surface mount to dip adapters. Okay, so keep that in mind. All right, and Belden Sys, and we'll put that inside the materials, of course, for the lecture. But Belden Sys is a great company that does this. And if you Google, there's not a lot of companies that make these adapters. There's one more I want to bring your attention to, though. Let's see, Smartboard. You know what? Let's just Google this. Smartboard. Yeah, this is it right here. And I think, now hold on, this may be Smartboard for Education. No, this is why I don't like Google. I think it's Smart. Let me see. Let me try Smart. And it's like SCH Mart prototyping board. Yeah, and this is what happens when you spell things with bizarre spellings. No one can find it, and here it is here. Okay, so it's called Smart board, like maybe school and Smart, and I have no idea. There's probably about where we could read about where this name came from. But anyway, these boards, and they make a lot of these boards, these SMT to dip adapters here, so we can go here, and then there you go. So you can buy them in one-offs, but now look how expensive these are. So just these two little guys right here, right? These two little guys for DFN with breadboard, etc., $15. Okay, so not cheap. Stuff is not cheap, and that's why a lot of people will end up building these things themselves or trying to do different tricky ways to mount them themselves, because this stuff is very expensive. So in fact, I even manufacture these myself. So let me show you something I've manufactured. So here on the zoomed camera, so let's take a look at the zoom camera. So here's a board that I make, and you can see how small this is. And I call this the Adaptatron BGA, and this is a 30-pin 6x5 0.4 millimeter pitch BGA. This component is tiny. I mean, super tiny. It's so small that most manufacturers can't even use it. So I'm going to zoom in here. I just want you to see what we're talking about here. Let me get the camera to lock in. So, here's like literally the tip of a needle right there. And now look at how small those leads are. And this is a BGA ball grid array. So it's a bunch of spheres that mount onto these little surface footprints, and then they're soldered on there. But you can see the tiny, look at my giant thumb here compared to this. So I couldn't even find a company that made something to mount a micro BGA, so I had to make these boards. So I made like 100 of each and variations of them. And if I had to buy them, it'd probably be thousands and thousands of dollars. I would have to buy these from somebody if I could even find them. But for very little, about $1 a piece or less, I was able to manufacture these boards, right? So, and you can see, and I believe this is a sound chip on here probably. And so now I wanted to experiment with that sound chip, right? So now I put it on my board and I can plug it into my solderless breadboard. Okay, so let's come back here and let's get back to our material. Okay, so we've got the surface mount stuff. We talked about that, and talking about the data sheet here. Now here's kind of the design for that 3.3 with that TPS regulator. And in this case, I omitted the input capacitor just to show you could if you wanted to. Again, these are just showing real simplified power supply designs. We're going to do much better when we go and design stuff. And again, it's got the output of 10, and then it's got a 0.1, and we've got these protections on here just to have them. And we could look and see if that particular part had those in there. And if it does, we don't need those. All right, and now multiple voltage systems. So a lot of times when you have a digital system, you're going to need like 5 volts, 3.3 volts, and maybe 12 volts if you're going to be controlling motors. So you need multiple voltage domains and power domains. And so that means that we're going to have multiple voltage regulators. And then what we want to do is we want to be real careful. So say if we've got a system that's 12 volt, 5 volt, and 3.3 volt. So the question is, so you get the 12 volts, so maybe we come in with a wall wart that's 24 volts. We drop that down to 12 volts, now we have a 12 volt supply. Then from the 12 volt supply, we go down to 5 volts, so we take the 12 and feed it into the 5. Then we take the 5 and feed it into 3. But here's the problem. As you do that, you're taking power from those supplies, so instead of taking it from the source, and if there's noise induced on the 12 volt supply, it's going to trickle down to the 5 and trickle down to the 3.3. So I'm going to show you that in a second, but let's just keep going through this. We'll draw something. So in this case, here is a 12, 5, and 3.3 volt system. So here we go, 18 to 24 volts on the input, just like I said. We got 1 microfarad, we got our regulator, we got a little protection, we got a couple output capacitors, and then we've got our 12 volts DC out here. Then we take that 12 and we put it into the 5. We let the 5 regulate that down. Same thing. Then we take that 5. We let the 3.3 regulate that. We take that 5 and we let the 3.3 regulator regulate it down. Now I've got 12, 5, and 3.3. All right, this is fine. This will work, but here's the problem. One, say that the 12 can output 1 amp. All right, so I'm expecting 1 amp out of the 12, but remember the 5 volt is pulling from that 1 amp. So let's say that we pull half an amp from the 12 with this 5 volt regulator. Okay, so now we're constantly pulling half an amp. So now that half amp is coming through here. We're using that half amp. And so now this is down to half an amp instead of an amp. Now we got that half amp right here, and then we use that to go and power the 3.3 volt and regulate it down. And then we only can pull half an amp total out of this thing. So say if this thing's pulling 200, 300, 400, 500 milliamps, we'll pull the entire supply and kill the supply here of the 5 volt supply. All right. But as long as these things are in range, this is one way to do it. And this is perfectly valid, and a lot of people do this. What you could do is instead of pulling from the 12, you could hook this directly up to the power source. You could hook this directly up to the power source. Two problems. Problem number one is, say we hook the 5 volt directly up to this 18 to 24. If it can tolerate the 18 to 24, it's got to regulate all the way from 18 to 24 volts all the way down to 5. There's going to be a lot of heat generated. It's going to get really, really, really hot because remember, whatever current goes through there, there's a virtual resistor in that 7805, in that 7812, in that whatever that 3.3 is, and that's going to be an I squared R drop, right? Power equals I squared R, or V times I. Drop inside of that's going to get real hot. So what we'd like is we'd like the input voltage to be very close to the regulated voltage so we don't have to burn off too much voltage. But if we hook it directly up to that 18 to 24, there's going to be a lot of burning. Even worse with the 3.3, that's going to really burn. Right, we're going all the way from 18 to 24 all the way down to 3.3. So wow, that's going to get super hot, right? So what you might do is this. You might say, I want this 12 volt by itself. It's going to be powering some motors. So let's just leave it alone. So we go 18 to 24, we do the 12. Then we take the hit and we connect the 5 directly to the 18 to 24 also. It's going to get pretty hot, but then we take the 5 volt and we connect that to the 3.3 because these are digital supplies maybe, and maybe this 12 is probably a motor supply. So they're separated at least, okay? All right, but again, you can figure all this out and kind of decide what you want to do. All right, so now the next section is transistor basics in the book, so we're going to ignore that. Now we're going to start designing power supplies. So now I'm super excited actually about this. I really do like designing power supplies. They're a lot of fun. And they're fun because you design the power supply and then you're like, this is pretty cool. It's like a little product. You just made something that does something. And what's cool about the power supply is it's a fun thing to experiment with because you can put different loads and see how well it regulates. And then you can put transient loads. Like one experiment that we're going to do is we're going to make a power supply and then everyone's going to be like, that's totally cool, awesome. And then I'm going to say, what happens though if we put a motor on this thing? And a lot of people try this. Put a motor on this thing and turn the motor on and watch what happens to the input and output voltages, and they just go crazy. So then the question is, can we clean this up and stabilize it a little bit so that if we were powering a motor, say a 5-volt motor, from a power supply and a digital system from the same 5-volt supply, which you wouldn't really want to do, but if you were to do that, is there a way to clean this up? So anyway, we're going to sit over here and we're going to design a 5-volt supply, a 3.3 volt supply. We are going to hook things up to a wall wart. We're also going to hook them up directly to a DC supply. So we'll do a DC supply because that's easy from the bench. Then we'll do something with a wall wart. Then we're going to go and connect it directly to AC. So we are going to get a transformer. Let's see if you can see this here. Here's a transformer, right? And we're going to get transformers, and we're going to hook these directly up to AC right to the power lines carefully. And then we're going to transform it down to 6 to 12 volts. Then we're going to use that with a rectifier, right? A full wave bridge rectifier and a big capacitor. And we're going to do that as well. So we're going to do all these different things and kind of build these power supplies. And then we're going to also talk about some other design issues as we design them. So anyway, this is a good place to stop. Let's stop here. In the next lecture, we're going to go right to the blackboard. We're going to start designing power supplies, and then we're going to build them each time we design them. So I don't know, we'll probably do that over 2 or 3 different lectures, but we'll do some design. We'll go build, design, build, and get through building some power supplies because it's really important. All right, so let's stop here, and I will see you in the next lecture. All right, welcome back, and we are on the next lecture. And if you take a look at the screen, we've been talking about power supplies, and here we have the last thing we were talking about, which was the multiple voltage design. And remember, this is just a guide. We're going to do things a lot differently when we build things. But this shows a 3.3, 5, and 12 volt system all in one. So anyway, now what we're going to do is we're actually going to build stuff on the bench, and we're going to start applying power and seeing what we see. Okay, so first what I'd like to do is let's just pick a power supply that we're going to make. So why don't we make a 5-volt power supply? It's one of the most common power supplies. Now remember, I've said that 5 volts has kind of seen its day, and most systems now, digital systems, run at 3.3 volts for their I/O or down to even 1.8 volts. So 3.3 is the more common voltage range now for digital systems. But you'll still see some 5-volt systems like the Arduino is a 5-volt typically, especially with the 8-bit version, the AVR 328P processor. But Let's do 5 volts since it's a good place to start. All right. So first thing let's get to the drawing program. Let's draw what we're going to make. All right. So we kind of already know what these things are supposed to look like. So let's get to our drawing program. All right. And this is the fun part. Uh, when you're doing electronics, a lot of it is research and reading data sheets and understanding what's going on. But once you can actually start building things, that's where the fun happens. So it's funny, these days, the majority of an engineer's time is spent just evaluating components, reading data sheets, planning what he's going to do or she's going to do, prototyping. And then finally you get to build the thing, and that's pretty quick. You just lay the parts down on your schematic editor, and you maybe simulate it, you prototype it, you test it, and it's like done. So a lot of it is this research that we're doing and looking at data sheets and understanding things. So it's actually a lot of work. If every data sheet's 50 pages or 100 pages, you got to read it. All right, you want to look at 10 different things. That's 10 times 100. That's 1,000 pages. So it's a lot of stuff. All right, so let's get right to it. So let's make a 5-volt regulator. All right, we're going to make a 5-volt regulated power supply. Okay, and we are going to use, let's say that we're going to use let's use the LM78, and I believe I have a CO5. Let's take a look here. Let me get one of these and see what we got. These little numbers are very small on here. So this one's a UA78MO5C. Okay, so we're going to use a UA78M05C. So that's what we're going to use. So let's erase this. All right. And so now let's go take a look at the data sheet. Let's go take a look at the data sheet for this UA78M05C. All right. So let's type it in here. UA78M05C. And this is just the version of the 7805. All right, and the one that I have is this version right here, which is the and the bigger kind of through-hole version, which of course is that TO220 package, right? So let's go and click on that. 83 cents for one, so at 1,000 or 37 cents, pretty cheap. And there's a whole series, 78M00 series, and this one is good for half an amp, 5 volts, and it's got a 2-volt dropout at 350 milliamps, so it's okay. So we're going to go there and get its data sheet. Remember, we're just picking out anything out of my parts here just for something to make. All right, so output up to half an amp. Here's what it looks like. So put a 0.33 in front of it, put a 0.1 on the output, and then common input output, and that's it. So it's very, very simple. All right, and let's see if there's anything else interesting in here. Okay, close your eyes if the scrolling bugs you. We'll get there in a second, and let me see if I can get some. Oh, this is great. So this is actually what's inside of it. This is the entire design. Remember what I was saying? We had block diagrams before, but this is nice because it's got the entire design. So you see all the passive resistors. You see the diodes here, right? So we've got a Schottky diode right there. Right? We got a normal diode, another Schottky diode. So you got, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 20 something resistors, and then it's probably the same amount of transistors here, and that's the entire design. So they even show it to you, right? So you could make one of these if you wanted to, right? If you knew the values of these. All right, so let's keep going down in the data sheet here, and we'll just put this here. Now, design requirements. Let's read this. A 0.33 microfarad decoupling capacitor on the input and a 0.1 decoupling on the output are recommended for the UA78MXX to behave as close to datasheet specifications as possible. All right, so we're going to put a little bit more on here. All right, so let's go to our drawing program and let's draw what we're actually going to do. All right, so what we are going to do is this. Why don't we use yellow here? So we're going to get our regulator here, and it's a 3-terminal device looking like this, and then we've got the heat sink here. All right, and that's typically connected to ground, so that's internally connected to ground. Sometimes it's not. All right, and then this is pin 1, pin 2, pin 3. All right, and this is V in. This is ground, and then this is V out. They go right in order, which is really nice. All right, so let's hook this thing up. So let's take this V in, and we're going to need some voltage in, and we're going to take ground here, and we're going to connect this to the system ground. We're going to call that ground, all right, and bring this in over here. We can do that if we want. Okay, and then same thing with V out. We're going to go here, V out. All right, so this is V out here, and then this is V in here. All right, and then again, we can run this ground rail if we like that. Okay, so now let's put some capacitors here. So on the input, what we're going to do is we're going to put a 10 microfarad right there, and we're going to put a 0.1 microfarad right there. We're going to do the same thing here. We're going to put a 10 microfarad here, and we're going to put a 0.1 microfarad here. All right, and this is a good solid way to build these things. All right, so now what's going to happen with V in here? What are we doing there? So we can get this in a number of ways. We could get it from, what could we do? We could have a wall wart or wall transformer, wall wart, people call it that, and that could put out a DC of, say, whatever, but we're going to need at least 7 volts. So we'll say a DC of 9 to 12 volts maybe. All right, we could do that. We could use a bench power supply, bench power, right? And we could just set it to whatever we want. That's another option that we have, right? The other thing is we could go AC, then we could go, through a transformer, right? AC to a transformer, and then to a bridge rectifier, right? So we could do all that and then power it like that. And so we're going to actually do that. So we're going to do all of these. But right now, let's just start off, and let's start off first with keeping this simple. Let's just use bench power. We'll set the voltage, and then we'll switch to a wall wart and do that. And then that way we can control this input voltage. Right, now we're going to assume we're getting DC in here, and we're going to set the DC at like someplace 9 to 12 volts, right? And remember, these devices, they'll operate as long as the voltage input is greater than whatever that dropout voltage is. In this, it's like about 2 volts. So we have to maintain at least 7 volts on that input. So that's why we'll set it for 9 to 12. And then remember that DC coming in from whatever the source is, it may be DC, it may be smoothed by a big capacitor, but it's still rough. So a lot of times, depending on what you're doing and the quality of things, if you are using a wall wart, you might look at it on the oscilloscope, and you might see that it's not really filtered very well. Maybe they've got a small filtering capacitor in there. Hey, if that's so, no big deal. We can go right here and we can put another 1,000 microfarad or 10,000 microfarad capacitor there if we want to smooth things out even more. All right, but for now, we'll just assume that it's pretty good. Okay, so here's our design. Now let's add a couple other things here. So here's this V out. So another thing let's do, let's put an LED. So let's put an LED. So here we go. So we're going to put a resistor, and then let's put an LED to ground like this. So there's an LED, and remember we put the little arrows on there representing that it outputs light, and then we'll have this resistor here. Remember we did these calculations, and if we have a voltage, and this is going to be V out, which is going to be 5 volts. All right, and then if we want a current limit of that, say we put like a, let's put, I think I have some 220 ohm resistors pretty close. So if we have 220 ohms, then we say what's the current? Current's going to equal V over R, so it's going to approximately equal 5 volts over the 200 ohms. Absolute worst case scenario, so let's do that. So that's 5 divided by 220. Excuse me, this should be 220 here. 220, and that equals 22 milliamperes. So approximately 22 milliamperes, all right? And then of course, when this diode is forward biased, this thing is gonna drop. Remember what happens here? When this thing gets forward biased and this current I flows, there's actually gonna be a drop over here of approximately anywhere from 2 to 3 volts, depending on what the diode is, the LED is, if it's green, if it's blue, if it's red. So let's just call it now, we'll call it 2 volts. So in fact, we've got 2 volts dropping over this. That means we've got 3 volts dropping over the resistor, which means the real current in the circuit is 3 volts divided by 220 ohms, which is 13 milliamperes. So 22 milliamperes is absolute worst case, and then more accurately, it's probably going to be about 13 milliamperes, because once the diode turns on, then it's going to have a voltage drop over it. Okay, so hopefully that all makes sense. So let's go ahead and let's build this. So let's get over to the bench and we're going to build this, and then we'll put a meter on here and we'll make sure, and then we'll do all this these different components and put them in and get this LED to light up and get it to work, right? So let's go over there. Okay, so we're over here on the bench and we're just going to build this thing. And so we're going to use the desktop or benchtop power supply to power it. So first we're just building the circuit, all right? So let's go ahead and build what we kind of drew on the board there. So the first thing is, take a look at the zoom camera here. We are going to be working with this guy right here. And this is the 78M05C, so it's a 5-volt regulator. And then now you can see I've got a large board. Let me back this out for a second so you can take a look. So since we're going to build multiple power supplies on here, I've got a larger board, right? So we'll start working with the top part here, I think, and then we'll work our way down as we add things. So I'm going to zoom in so you can see that. All right. Okay. So here we go. All right. So the first thing is, let's just go ahead and place our voltage regulator someplace so we can get a lot of wires to it. So what I think I'm going to do is I am going to I'm going to place it right. I'm going to place it right here. All right, and this will give me room to put some capacitors, and it'll also give me ground. And then if I want, I can bend it and flatten it out if I wanted to get it out of the way like that. And then also I can run wires behind it if I want to. So there's a lot of where do you put stuff when you do these things, right? Where do you put stuff, all right? Okay, so the first thing let's do, let's get the ground connected. So that's the center, and we're going to put that right down to ground. Now, another little comment I want to make you aware of is the wires that I'm using. These are about 22 to 24 gauge, these actual wires. So when you're doing power supply stuff, you can make them a little bit thicker and they'll still go inside the board. So you can go to 20 gauge. Remember, the lower the gauge, the thicker the diameter of the wire. And as a matter of fact, let me see here if I have, so like these wires, you can see there's 22 gauge. I've got it written on it, 22 gauge. And so I keep the thickness here. And then here's a 22 gauge. So this wire right here is, I believe, 22 gauge, and then 20 would be really thick. So power supplies, go ahead and use a thicker wire if you want. Okay, so now we want to put those, the input here. So let's put kind of where the input would be coming from. All right, so this is always a little bit tricky. It's like, where do you want the input to come from? But we're going to say the input is going to come right here. So here's where the input is. All right, and then let's get the output. All right, and here's the output, and we're going to just run it all the way over here. All right, and we're just prototyping this. No exact right way or wrong way to do everything. Okay, so that's good. So now if we were to put power in here and measure the voltage here, we'd have 5 volts, but it wouldn't be stabilized. Okay, so that's why we need to put those capacitors. So we're going to put 0.1 on both the input and output, and 10 microfarad on both the input and output. All right, so let me go ahead and get those. We're not going to use electrolytics. We're going to use monolithic capacitors or tantalum. So for the smaller 0.1s, we're going to use this guy right here. These are 0.1 microfarad. So I'm just going to strip a couple of these off here. All right, so there's one right there. Let me get another one. Now, the leads on these are important. We want to make them as short as possible. All right, so we're going to make them as short as possible. So what I'm going to do is I'm going to take these leads and just cut them just a little bit. I want to be able to put the components in and have room. So I'm not going to cut too much because once they're cut, you can't uncut them. All right, then I'm going to cut this one here. I've got glasses on and I always hold the wires so if they go shooting, they don't go shooting in my eye. All right, so there we've got those. Good. So now we need some 10 microfarad. Now we could use the monolithic like this, ceramic capacitors, but we can also use tantalum capacitors. They've got very low ESR. So let me see here. So right here, we'll use these. And these are tantalum 10 microfarad. They can withstand 25 volt. They are polarized, so you got to put them in the right direction. So let's take a look at that. So I'm just going to grab 2 of these out of here. Okay, good. All right, so they look like this, and they look like they're dipped in, molten chocolate or something. It's actually resin. All right, and oops, sorry, bumped the camera on you. So that's what they look like. And let's look at it on the zoom camera here. So on the zoom camera, I want you to take a look, and let's get that to focus for us. There we go. Let me back it out. See what that says? 10 micro, 25 voltage, and then see there's a little plus there, if you can see that. See that little tiny plus? That plus, that means that this side is plus and this side is ground. So let's cut these and keep an eye on that. We're just going to cut it and make it a little bit shorter, because remember we went short leads for capacitors. So I'm just going to cut this right here. Okay, cut, and then we'll cut the other one, and then make sure that you put these in right, keep them polarized properly, right? Okay. All right, so then now let's go ahead and put these in. So we want to put a 0.1 and a 10 on the input, and a 0.1 and a 10 on the output going to ground. See that? And this bottom blue rail, that's going to be my ground rail. All right, so here we go. All right, so first I'll put the 0.1 microfarad, and I'll put the other 0.1 microfarad on the other side, leaving myself room here. And this is, you know, you got to work around and stuff. Now I'm going to get this guy, and I'm going to make sure where the plus is. I'm going to bend these out. Careful when you're bending them. Do it slow. All right, and then there we go. There's that. That looks nice. Okay, let's get our other one. Maybe zoom in a little bit more so you can kind of see. There we go. Okay, I'm looking at the plus, make sure I got things oriented correctly. And the other thing I like to do is do everything the same, so there's consistency, right? So see how I put, you know, the capacitors, the small ones towards the ground, and I put the big ones on the outside, just some kind of consistency. All right, let's put that in there. Okay. So now we've got our input-output capacitors, which is what we needed. We've got our input is going to come here on the left. We've got our output right there. This is going to be the ground line, the blue line, so that'll always be ground. We're going to put our input voltage here, and then we're going to get our output voltage here. So what we could do is take that output, and we're also going to tie it to the blue rail here, which making that positive. All right, so we're going to tie that, and that's going to kind of be our positive. All right. All right, so now ultimately these two rails are going to have negative and positive 5 volts on it. We're going to specifically put the 9 to 12 in right here though, okay? All right, so what do we need now? We need an LED here. So let's find an LED. Okay, let's get this green one. All right, we've got this green LED, and hopefully this LED works. We'll see. Some of these we've been blowing them out as we've been playing. Now let me find a 220 ohm resistor. All right, here we go. All right, so I've got the 220 ohm. And so that's red, brown is 220. All right, so let's go ahead and put this someplace. Now, since we know that this rail is hot, it's going to be hot, we'll just put the LED off of this. So we'll do this real clean. So what we're going to do is let's put it right here. All right, so there's our resistor. And then we're going to put our LED with the negative to ground, which is like this. And there's a reason why I picked the blue line here and not up here, because then ground's up higher. I like just being able to bring things to ground. And then we need power, so let's get a red wire for power. I'm trying to do a modicum of color coding this time here. A lot of times I just do things with all the same color, but it's nice when you're doing power stuff so you can see power. And then if I have different voltages, I'll use red, orange, and another variant of orange or maybe yellow, because those are kind of power colors. All right. So let's put this wire in here. All right, so now let's see what we got here. So we've got exactly what we kind of drew. We've got our input capacitors, output capacitors, we got our input, we got our output. It's going to this bottom rail, it's going to power this LED, and we're all good to go. All right, next thing let's do is let's get ourselves a multimeter so that we can measure the voltage. All right, so I'm going to, just for now, I'm going to take this meter and I'm going to put it over here to the side. Put it over here to the side. Let's put our capacitors back. Keep things neat if possible. All right, and then we're going to use one of these connectors here, right, to plug the multimeter in. Remember that? Now this is kind of nice. If you notice, I can kind of go in diagonally right here, and I can get plus and minus. So I'm going to do that. So I'm actually going to put this at the end of the board, kind of out of my way. And I'm going to show you. All right, so I've got it plugged in right there. There's plus and there's minus. So now I can just plug this in to my multimeter probes and I can measure that voltage, which we'll do in a second. all right? Okay, now how are we going to get power in here? So remember, we like using these, there's a couple ways to do it. We're going to have some alligator clips. So one way we could do it is like this. We could take this little piece of wire right here. Now, these conductors are not big enough for power, right? So in real life, we would make them much thicker, much lower gauge, but they're fine for this. So we could say that yellow is going to be ground, and we could say that orange is going to be plus. And then now we have these two wires which we could alligator clip onto. All right, so we could just do that. And then the other thing that we do is we put these posts, right? And then we alligator clip onto the posts, all right? So what I'm going to do is I'm going to put these posts here too, and I'm going to use also this piece of wire. Okay, so now let's get our power supply. So we've got it at 1.5 volts, and then here's the output, which we haven't turned on yet, all right? So what I'm going to do is I'm going to turn the output on right now, and so let's, as a matter of fact, let's hook up our voltage monitoring. So I'm hooking up the clips. All right, that's done. All right, and so right now let's just keep this view like that, and then in a second I'll put this meter so you can kind of see it, but I'm going to keep it off screen for a second here. All right, so going back and forth here, so you look at the circuit, and I'm going to turn this thing on. Here we go. All right, so I turn it on. All right, and nothing happens. And right now we're at 1.5 volts, so let's start increasing the voltage. Here we go. 2, 3, coming up on 4 volts, coming up on 5 volts. Now notice we're starting to get output. It's starting to track to it. Now we're at 6 volts, and now we're at 7 volts, 8 volts, and let's bring it to 9 volts with the course adjustment, and put it at 9 volts. And we'll just kind of leave it right there. So, all right, we got 9 volts. This thing's on. Now let's take a look at our voltmeter here. And sure enough, it's saying it's at 5 volts, which is what we expect, even though we have 9 volts going in. All right, now what I'd like to do is we can put different loads here. All right, so we can put different loads. So now if we just go from this lead right here down to ground anywhere, right, we're going to get current through that. All right, and then we can kind of see what the load does. So why don't we do this? Why don't we put a switch so we can turn it on and off with a switch. We'll put a momentary switch, and then what we'll do is we will press the switch to push the load in to enable the load so that we don't have to put it in and out. So let's do that. So we're going to turn the power off. All right, so let's do this whole switch thing. So let me get a switch. I'll get a little blue switch. All right, and let's get some room here. So we can put the switch right here, up here, all right. And then we'll get a load here. So let's do the first one. We'll do it with 100 ohms. All right, and we could put a bunch of switches if we want, but let's start off with 100 ohms here. All right, so now what I want you to do is so let's be data scientists right now. So what I want you to do is I want you to mark down, I want you to make a table, and in that table, I want you to put voltage and current. So we're going to make a table, and we're going to call it load regulation. So we're going to do your table however you want, something like that, VIR. So what we're going to do is we're going to, for every R that we put in here, we're going to say what's the V on the output, and then we can compute the current as well. So we're going to start off, we're going to try a 100 ohm resistor for R, and then we'll do a 1K ohm, and we'll do a 10K ohm, and then we'll do maybe a 33. Yeah, let's just do this. We'll do 100, 1K, and 33 ohm. But first, let's do the 100 ohm. All right, so you can do that yourself, and I'm going to keep that off screen there. Okay, so here we go. So the first one we're going to do is the 100. And with the 100, how much current's going to flow? Roughly 5 divided by 100. So that's 50 milliamps, 50 milliamps, all right? So here we go. So I'm going to turn on the power supply. All right, we got the LED. Now, this is saying we're at 5 volts. So now what I'm going to do is I'm going to make this so you can kind of see everything here. So I'm going to zoom this out a little bit so you can see what's going on. All right, so let's get this in here someplace. Okay, there we go. I think that's nice. Okay, so right now we don't have the load in, but when I press this button, it's going to switch the load in, and there's the little load. We press the button, we're gonna get current through the switch, down through the resistor, down to ground, right? Does that make sense, everyone? All right, so here we go. We got nice 5 volts out. We press the load in, and look at that. Like it's not even there. So that changed, 0.01 volts, 0.01 volts. So, all right, so in my table here, we started off at 5.03 volts, all right, and then at 100 ohms, we just changed to 5.02, right? Or we just changed by 10 millivolts, a delta of 10 millivolts. And then we could compute the current because we know 5.02 divided by the 100 is the current. So it's going to be 50.2 milliamps. All right, now let's go and we'll pull out the resistor here. We'll just keep the power on because we're not switching in anything until we press the button. And let's get our 1K. So we're looking for a brown, black, red, our 1K, brown, black, red. So let me find that here someplace. Here we go. Brown, black, red. All right, so I'm going to put this in the circuit. Brown, black, red. Good. Let's get our meter back here. Maybe scooch this up a little bit so you can see it. There it is. All right, so ready? Let's go ahead and let's do this. And now in this case, it will be 5 milliamps roughly. 5 volts divided by 1K. Here we go. Watch the voltage. Does it change any? I turn it on. Nothing. Nada. So at 5 milliamps, at least with 2 decimal places of accuracy, nothing, all right? So it stays at the 5.03. Oh, let's come back here. So 5.03, yeah, 5.03. So it didn't change. We couldn't even see it, 5.03 volts. Okay, now let's go get a bigger resistor here. So let's see, can we find a 33 ohm resistor? And that'll give us a good amount of current if I can find one quickly. So let me find a 33. Here's one right here. Orange, orange, black. Orange, orange, black. So let's go ahead and let's put this into the circuit here. Orange, orange, black. We're going to pull out this load resistor. So what are we doing here? We're doing a load regulation test. So we're seeing, does this regulator regulate it? It's regulating really good. All right, so there we go. Okay, so we got our 33 in there. And let's compute how much current roughly should flow. It should be 5 volts divided by 33 equals 150 milliamps. So 150 milliamps are going to flow through here. Let's do a calculation. So 150 milliamps squared, let's do a power calculation, squared times the 33 ohms equals 3/4 of a watt. 0.75 roughly, right? 0.7425. So this resistor right here is a 1/4 watt. And so we're going to put 3 times as much power, so it's going to start heating up. It's not going to explode or anything, but it's going to, heat up very quickly, and that's why we need to do those calculations, know what we're doing. All right, here we go. 5.03, and I'm going to put the load in, right? We're going to get 150 milliamps through here. Here we go. And look at that. Wow. So we just did 150 milliamps, which is about 1/3 of what this regulator can regulate, half an amp, remember? And we're still only getting like 10 millivolts, if that, 10 millivolts, so that's great. So we'll put here, again, 5.02. So the whole point is we made this little table. So we made this little table, right? And if we had a more accurate voltmeter and we had more data, then we could draw a line to show the load regulation as a function of current, right? And we got to compute the current each time and write that in. But that way we could graph it and we could see how this thing works, okay? So, anyway, so that is this experiment. And that's really good. Now, the final thing that we can do is this. So what we can do is we can put a load inside of here, right? So this 150 milliamp load. So what we can do is this. We can pull the switch out, and then we can take this resistor. I don't want to burn myself. Take this resistor, and we're just going to plug it right in here right now. All right, it's going to start getting hot. All right. Now, it's at 5.02. Now, last thing that we're going to do is this. I'm going to go over to the power supply, and I'm going to start turning it up, all right? Now, notice, see that voltage is starting to change there a little bit, all right, because things are getting hot. If you see any smoke, you let me know, all right? But what I'm going to do is I'm going to go to the power supply, and I'm going to start playing around with the voltage. So take a look at the power supply here for a second. So now this is line regulation we're testing. So I put it down to 8 volts, let's say. Put it down to 8 volts. And notice this changed just a little teeny tiny bit, all right? Now I'll put it down to 7 volts, all right? And it's kind of hanging in there, but if I put it down to 6 volts, we may lose a little bit of that voltage because we're getting real close to that dropout. It just can't tolerate it. And you see that? It went all the way down to 4.32 because we went below that 2-volt dropout that we need. So let's go back up to 9. Let's go to 10 volts in the opposite direction, 10-ish. We're hanging there good. Let's go to 11 volts. Good. 12 volts. Good. So this is fine. So we've got really nice line regulation and load regulation. Now the last thing that we can do here is we can touch this with our little fingers. So let's be careful. I'm going to just touch it, and I'm going to tell you it's barely warm. Nothing. Just a little bit over room temperature. All right. So that's it. So let's go back to the screen and take a look at a couple things. Okay, so we're back here on the screen. So we built this. And it works great. So what we're going to do is we're going to stop here. This is a good place to stop. I'm going to break this one into chunks. And now we're going to change how we're getting the power into this. And we're going to use a wall wart, and we're going to use transformers. And we're going to do that experiment. And then after that, then we're going to build a couple more power supplies and put them all together so we have a big power supply system. All right. So anyway, this was a good one. So let's stop here, and I'll meet you in the next lecture. Bye. All right, welcome back, and we're on the next lecture here. We're just continuing in the series of power supply design lectures where we're actually building stuff on the bench. So where we left off, if you look at the screen here, we had built this 5-volt supply, and it worked great, and we checked load regulation and line regulation, and we stayed at 5 volts, dead on. So now let's go ahead and let's add a 3.3 volt regulator to this. So I've got a number of 3.3 volt regulators over here, linear and LDOs. We could use a 7833 like the 7805, but I found one here which is an MC33269. It's a surface mount. If you can see it there, surface mount device. So why don't we go on to a DigiKey and take a look at that. So here's the part here, MC33269. And this is from ON Semiconductor, and another company that makes a lot of analog parts. So let's go take a look at the specifications here. So it's 3.3 volts. It'll output 800 milliamps, so that's nice. It's got a dropout voltage of 1.1 volts, so that's nice. So to maintain 3.3 volts, we'll need to have 3.3 plus 1.1, 4.4 volts. And surface mount, and it's got this what's called DPAC3 package. It's a surface mount kind of package. So let's go ahead and take a look at the data sheet. All right, let's zoom in here. So here's the data sheet for this component, and the package that I have is this DPAC package here. And again, that's it right there. If you can see that, I don't know. We'll look at it on the other camera when we get to it. And again, go through the data sheet. And I want you to see this. There's our internal schematic for the component. So that's cool. And again, you can count up all these parts, a lot of interesting parts here. Here's an interesting part. So see this transistor right here. Notice how it has multiple collectors coming off of it, right? Now remember, this is custom silicon, right? So you can kind of do anything you want. So instead of making a standard transistor with one collector, you could put 2 collectors, 3 collectors, 4 collectors. You do whatever you want, right? So some of these things are, quite interesting, and here's some of the custom silicon. All right, and then a lot of these curves are like when we did the line and load regulation. So these curves kind of have things to do with that temperature versus dropout voltage, just anything you might want to know about it. But what I want to get to is this section, which are showing some of the reference designs for stability and whatnot. So we're going to do something like this right here on the left here. And so we got ground, a 10 microfarad, and then notice it has little stars here, little disclaimer saying an input bypass capacitor is recommended to improve transient response, or if the regulator is connected to the supply input filter with long wire lengths. So yes, we want to put these input filter capacitors on here. And then again, we've got a 10 microfarad on the output here, again with a star, which is wherever that star is. I'm not going to look for it. Oh, here it is. It's this paragraph right here. So the MC33269 requires an external output capacitor for stability. The capacitor should be at least 10 microfarads with an equivalent series resistance of less than 10 ohms but greater than 0.2 ohms over the anticipated operating temperature range. So we're going to stick with the 10 microfarad because it's just what we have in parallel with the 0.1. So we're going to do the same design right here. All right, so let's go to our schematic here. So now what we're going to do is we're going to have some fun with what we're doing right now. So what we're going to do is we're going to add, so let's move this V out here a little bit, and we're going to add this V out. We're going to add our new regulator to this regulator. Okay, so here's what we're going to do. So we've got this new 3.3, and this one kind of looks a little bit funky. It's got this little short tab because it's surface mount, and then we've got our 3 lines coming off of it again, very short. All right, and again, so this is the 7805, and then this one is going to be this 33269. 33269. Okay, so what we're going to do is we're going to take one and plug it into the other one. So first, let's go ahead and we've got pin 1, 2, and 3 here. Matter of fact, let's label them like we did the other one. 1, 2, and 3. They're the same pinouts as this, V in, ground, and V out. So here we go. So let's take this down to ground like that. And then we're going to have this ground rail here, which we're going to kind of connect to everything here, just like that. And then we're going to have our output right here, just like we had last time. So this is V out, but now this is kind of V out 5 volts, and this is going to be V out 3.3 volts. We could put some names on these. Here's our input right here. We're going to get that rail right there. And now what we're going to do is we're going to do the same thing. We're going to put these same capacitors there. So we're going to put a 10 microfarad there, and we're going to put a 0.1 microfarad there. Again, we're going to put a 10. We'll do it symmetrically here. We'll say 0.1. How'd I do it here? I put it in the drawing. I put 10 microfarad. We'll do the same thing. Keep the drawings the same. 0.1 microfarad. All right, and remember when you're drawing schematics, the position of things on a wire, it's more abstract. It doesn't mean that's the actual position, right? So the order here you could put in anything you want. So again, you could have a convention with yourself where wherever it is on the schematic, if it's closer to the pin, then you'll make it closer, and if it's farther, it could be farther or not. So, but remember, in reality, this node is all the exact same point. This node is all the same point. This node is all the same point because they're all wired together, right? Just with wire. Okay, now what are we going to do? We are going to connect this here. So let's use, we use orange for that. So we'll take this orange and we're just going to connect that right there. And then these grounds would be connected as well. All right, so now we've taken the output 5 volts and we still have that right here. So we'll just put a little arrow to signify that. That's our V out also. Same thing here. We just put a little arrow up here to signify this is also our V out. So this is our V out 3.3 volts, and then this is our V out 5.0 volts. Little arrows typically are used to show those, but we're going to connect them, and the grounds are connected and all that. So now the 5 volt supply is going to power the 3.3 volt regulator. Right? Now remember, we don't have to do that. What we could have done is take this and bring it all the way back to the input here. So we could do that too, and it'll work. But the question is, what's the maximum voltage this regulator can take, right? So can this regulator take this high 9 to 12 volts, right? So we can go back to the data sheet and check that. Now remember the problem, when we link these things together like this, 2 things happen. One, we pull current from this 5 volt supply. So if we want to pull a bunch of current on the 3.3 volt rail, we take it by taking it from the 5 volt. So that's not cool. If a 5 volt wants its full 500 milliamp supply, we're pulling it by this 3.3. So we want to put it back here. However, on the other hand, if we don't really care about that and we want to simplify it, and if this regulator requires a very a lower input voltage, instead of going from the 9 to 12 and burning a lot of current, we'll only go from the 5 volts, so we'll get less of a power waste on this regulator. So these are things you figure out and you decide what you want to do. Anyway, then we'll have the output. So let's we'll put those outputs kind of in blue here. Let's kind of circle them. So there's there's that output there, right? And then typically, here's this output here, and then here's the input right here, right? So those are kind of our 3 things. So here would be our input voltage, and then here would be our first 5 volts, and here would be our 3 volts. So we got this, and let's do another thing. Let's add another LED for this guy. All right, so we're just going to add another LED. So this is the 5-volt supply. So this is really V out 5 volt we're doing here. And we'll do the same thing for this one. So we'll have our V out 3.3 volts, and we'll go through a resistor, and then we'll go down to ground through our LED with little arrows. And now we'll just make this 100 ohms, right? And you can figure through that if you want to, because you've got a much smaller voltage. This will generate a smaller current and we'll be okay. So this will be another LED that we'll use for the indicator to show the 3-3 line is hot. All right, so we're going to build that. And then when we get done with that, then what we're going to do is, instead of using the power supply, so we have the bench power supply. So let me kind of draw that. So it's got a little thing there and a gauge and dials. And then this has a, ground here like this. So here's, plus and here's minus. And we're just connecting that directly to this. So instead of having that bench power supply, we'll do that first. But then what we're going to do is we are going to do this with the wall wart or wall power supply, whatever you want to call it. Okay, let's try not to make such a horrible drawing here. I can draw this a little bit better for you. Okay, and so let's say that this might be 9 volt, and then out of it are a couple wires, right? Or a wire, and then we're going to split them. But anyway, that's the plus and that's the minus, and this is 9 volts DC, and and this plugs right into the wall, right? So there's 2 prongs that plugs into the wall. And so this might be at 500 milliamps or an amp or whatever it is, right? So obviously we can't pull 800 milliamps or an amp from something that only puts out 500 milliamps, right? So we've got to talk about power just for a second here. But the bottom line is that whatever this thing sources, we're never going to be able to pull more than that out, all right? So with linear regulators. Okay, so this is kind of where we're going, right? So let's go ahead and let's add this other regulator, get our 3.3 volts, and then let's try and switch to the wall adapter from our desktop power supply. All right, so let's go over to the bench and go do all that. All right. Section 4, Lecture 14, Part 4. We're doing the experiment here where we're putting together the 3.3 volt regulator and the wall adapter. Okay, so let's get my glasses and get into this. All right, so we're here on the bench and we've got our previous design here, and I think I turned it off, and I did, so that's good. All right, let me turn it back on real quick. And let's see if we've got everything here hooked up. Did we undo something here? Yeah, we did. So we had our load here, and let's put our 220 ohm resistor. Let's see if we can find that again. Brown, red, brown. All right, let's get that back in there for our little LED. Okay, let's turn it on, and it looks good. Okay, so that's back to normal. All right, so now what we're going to do is we're going to add our 3.3 volt regulator, and we're going to kind of copy the same design here. So now what we have here is we had the output turning this bottom rail here to 5 volts. So why don't we turn this top rail to 3.3 volts? So that's kind of what we'll do. And then, so let's do this. Let's move our LED. All right, let's move our LED. Since this whole rail is going to be hot with 5 volts, why don't we'll move the LED back a little bit, and we'll just put it right here and put it a little bit closer to the device that it's supposed to be indicating. So we're going to go like this. All right, and here we go, and there we go. All right, so now we've got our power going through the resistor to the LED. So if I turn this thing on again, all right, it works. All right. Okay, so that's that. So now here's our output, okay, and going down to the rail. So let's go ahead and let's put our 3.3 volt regulator in. All right, and I'm going to give myself a little bit of room here. So I got my 3.3. It's set up the same way, input, ground, and output. So let's go ahead and do that, input, ground, and output. So let's get a ground wire. Let's use black for ground. And let's get that in there. Put that right there. Good. It's just a little bit crooked because that's the way that sometimes these pins get a little bit bent. That's okay. All right, and so now let's take this output and we're going to put it directly in here, but we're going to get it right from this rail right here. Well, actually, we could just go straight across there. That's fine. You know, the shortest paths a lot of times are the best way to do things here. All right, so let's see if we can get a wire here that fits. So I'm going to go right here, right to this, and this wire is a little bit short. So let's get another one. Here's one. All right, let's see how this one works for us. And again, we're just trying to keep this, you know, we're always rushing because these are long lectures, but we want to keep things neat. Okay, so that's nice. So we've got our input going into our 3.3. Let's get our output, and we'll just go with a fairly short wire on this output. Now you can see why I wanted to use this big board so we can add different things over time here. So here's the output, and I'm just going to put this right about here. Okay. There's our output, and we're just giving ourselves some room. Now, what do we need? We need a 0.1, 0.1, and a 10 and a 10 on input and output of capacitors, all right, microfarad, all right? So let's go back, and we're going to get these guys again. These are our 0.1s. Let's take a look on the zoom camera here. So there we go, and let it zoom in. That's nice. And yeah, you can see 104, so that's 0.1 microfarads. Those are in picofarads right there. All right, so we're just going to get a couple of these. All right, and we're going to cut these just a little bit, just shorten them up just a little bit. We want to have enough room, but we don't want them too long. So again, as I cut these, you know, kind of hold this, don't cut your finger off, and cut them. So there's one of them cut. Just take a little bit of this length off. They're just a little bit too long. Cut that. And I've got glasses on in case these things shoot. These things will shoot like 100 miles an hour in your eyes, so be careful. All right, we're done with that. And then we're going to use these tantalum again, these 10 microfarad, 25 volt tantalum. They are polarized, and they have a little plus on the plus side. Keep an eye on that. And the length of the leads is actually coded so that the plus side is long. So the plus side, so if you look at it like that, you can see one of the sides is longer. That's the plus on this particular manufacturer. So I'm going to cut these also, shorten these up just a little bit, so I can work with them. Again, leads have inductance, so we want to get rid of the inductance, take it out of the equation as much as possible. All right, so we're ready to go here. So we're going to do the same kind of design we did here. We're just going to put the small capacitors real close to that ground, and then we're going to put the larger capacitor right next to it. So here we go. All right. And you can see it's just a lot of fun. Once you have the rules down, right, then you just start building things like Lego blocks, on and on and on and on and on. And as long as you have enough current and voltage, and you take into consideration impedance, right, and all those things, you can just build anything you want, like literally. All right. And I'm being careful to look at the polarization. Tantalums are polarized. And remember that data sheet said that it had to have, it could be 10 microfarads, it needs to have an ESR, an equivalent series resistance of 10 ohms or less, or 0.2 ohms or greater. All right, I know that this part does, so we're okay, but if I didn't, we would look that up. We would find this particular part. We have the part number, and we could look that up on DigiKey or something for this particular part, and we could make sure so that we're okay. All right, but I know that it is, so we'll just stick with that. All right, make sure everything's okay. All right, so now this should work. So what I'm going to do is I'm just going to turn it on and see if anything shorts. No. All right, so that worked. Now, so this is indicating the 5 volt supply, but we don't know about this other supply here. So we're going to put the LED on this one. So first what we're going to do is we're going to take this 3.3 out and we're going to put it up to this top rail. So that's where we're going to have 3.3. So that now you can see where this concept of rails is starting to come from. We've got two rails. We got this rail, we got this rail, right? Well, and we got all these other rails. So I'm going to put this right here. Okay, that's a little bit too long. Again, I'm not going to sit here and cut too many wires and make things perfect, but we don't want to be, you know, just everything too long. Okay, that's good. That'll work. All right, we're going to bring that up there. And maybe we'll put this right like that. Okay, so now we've got this. Now we've got this rail hot with 3.3 volts, but we're missing a ground up here. So we've got to bring a ground. So what we can do is I can take a ground and put it here to up here, or I could put it at this end and put it up here, whichever one. So we'll just pick one. And there are reasons to do it in different ways. If we want the voltages to drop in the same way along the rails and that kind of thing, we want everything to be as even as possible. It's all about symmetry. So anytime you make a decision, if it's symmetrical and pretty, it's usually probably a good idea. All right. So let's go ahead and right when the ground comes in, let's just put that ground right over there. So basically, as current is kind of down, moving in this direction, this voltage will change in the same way, because if we have negative here and we couple it up here, basically there's a resistor here, right? Everything's got resistance. It's metal, so it's going to go da 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 da, and then it's going to come up here and go da 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 like that. So you've got this two different differential resistances going here. Better we just bring this over here, tie them together, so both of these rails kind of have the same ground. They won't have a different ground potential voltage. We're talking about micro or nanovolts here, but hey, why not make it perfect? All right, so I'm going to hook the grounds up right at this end, and hopefully this wire reaches. I think it will. Nice. Okay, so now we got that. So we got a ground coming here. So ground, this is going to be our 3.3 volt rail. Okay, quick turn on. Let's turn it on real quick. Still working, good. All right, now let's get a 100 ohm resistor and another LED. We got a green LED here, so why don't we use a red LED for the 3.3? So we're looking for 100 ohm, brown, black, brown, brown, black, brown, got one. So brown, black, brown right there. And why don't we put, this LED is here, so why don't we put this one here? So put it right here, and let's kind of use the same architecture where we took the 5 volts. So we'll do this kind of thing. So we'll take the 3.3 volts right here, and then we'll put our LED, we'll put our resistor next. Just trying to mimic what we did with the other LED. Put our resistor next, and now we're going to go to ground. And I'm looking at the orientation of this. All right, and here's, this will go this way. Remember, the flat side is usually ground. The pedestal is usually ground, but sometimes it's not. But the flat side is always ground, at least 99.9999% of the time. Okay, let's turn this on. We still haven't verified this voltage with the voltmeter, but we're just assuming it's correct for now. Okay, I'm putting this on 12 volts, and this LED did not turn on. All right, so I'm going to take a look at that, and okay, should have turned on. So now I'm going to try it again. Okay, I'm going to leave it on. I'm going to try a different LED here. Put this to ground. Not working. Put this to ground. Not working. All right, so, okay. And this regulator is really, really hot right now, and there's 0.4 something amps going through here. So something potentially got shorted. So we're trying to figure out where that is. Okay, so something's happening here, and what I think is we've got the pinout wrong. So we made an assumption. So let's go back to our data sheet here, and if we look at our data sheet, sure enough, we've got pin 1, 2, and 3. And when I read through this so fast, pin 1 is ground, pin 2 is out, pin 3 is VN. So these pinouts are different. So 1 is ground, 2 is out, 3 is VN. So if we go and we look at, so we've got ground, V out, and VN. So ground, so pin 1 is ground, all right, pin 2 is V out, and pin 3 is VN. Clearly, we do not have that here in this drawing. So what we need to do is we need to change what these are. So what I'm going to do is I'm just going to change what the actual pin numbers are here, and I'm going to keep the drawing the same. So ground is pin 1. So now this has got to be pin 1. Pin 2 is V out. So pin 2 has got to be V out, and then pin 3 is VN. All right, but on the actual component, the pins are labeled 1, 2, 3. So of course we got a little problem here. So what we're going to do is we got to kind of fix this here, right? So now let's just erase these, and now what we're going to do is this. We're going to erase this. Okay, and so so this is a common mistake, right? And I did this purposely for you. I wanted to show you how this happens. All right, so this is pin 1, this is pin 2, this is pin 3. So pin 1 is ground. So pin 1 is ground. That's got to go here, and like that. So there's pin 1 is ground. Pin 2 is V out. Okay, so that's got to go here, like that. There's V out. And then pin 3 is VN. Pin 3 is VN. And so this one, what I'm gonna do is I'm gonna draw, and then I'm gonna go like that, right? And then I'm gonna go like that, to kind of show it's going over that. So it's kind of this contrived thing. So there's no good way to really draw this with this nice 1, 2, 3 pin that the 7805 had. We got to kind of do like this. So let's carefully go back and let's fix this. All right. So we're going to fix this right now. Okay. So let's go back and fix it. We're going to go ahead and we're going to put we got our power off. Got to make sure of that. And it is. So we're going to put that back in there. Okay. So the first thing is pin 1 is ground. So all I'm going to do is I'm going to shift the component a little bit to the right. And now we've got pin 1 as ground. Now we've got pin 3 is the input. Pin 3 is the input. So now over here, we're going to take that out and we're going to run this input all the way to pin 3. So we need a slightly longer wire. So we're just going to use this wire. We'll pull this wire out and put this one back in. All right. So here is the input. Here is the input. Nice. All right. So pin 3 is the input. Okay. And the output now is pin 1. All right. Excuse me. Pin 2 is the output. So pin 2 is the output right here. And I'm going to very carefully put this wire right here for you. All right. So here's the output right there. All right. So tricky. Got to be careful. Okay. So now we're in good shape. Now let's put our LED back in here. We're going to put our LED back in here to ground. All right, then we're going to run our power rail back up top here, all right, and get our power going into the top rail there. All righty, so here we go. I'm going to put this right here. Okay. Okay, so now we got our circuit here again. Okay, now let's take a look. So, and this is a little bit hard to see here. I might be able to zoom in a little bit and it'll stay focused. But we've got all this stuff twisted around. So pin 1 is ground, and that is correct. Pin 2 is supposed to be output. Pin 2 is output. All right. Pin 3 is the input. All right. And then we have this little capacitor network here. And now we've got a little problem because we need this capacitor network on both of these pins here. So we need to basically move these capacitors over here to the right, unfortunately, but that's okay, we have room. So we're going to move these over here to the right, and we're going to put this one here, and we're going to put this one here, and we're going to be careful of polarity. All right. Okay, there. We don't want anything to short out. Okay, there we go. So now we should be good to go. So now when I turn this thing on, we should see both these LEDs, as long as this LED is good, and then we'll check the voltage. Okay, ready? Here we go. Turn it on. Oh, and all of a sudden it works. All right, so now let's take a look at the voltage measurements and make sure everything is correct. So I'm going to get the multimeter out. All right, so I got the multimeter. Let's go ahead and let's turn this on. And the sensor, the probe here, is still connected here to the 5-volt rail. So let's put it on there, and there you go. There's 5 volts coming out of that supply. Now let's just move this probe up to the top rail. So let me give you a little room here, and actually I'm going to pan out a little bit. All right, so we got our 5 volts there. I don't want to break anything. We've got our 5 volts right there. And then now I'm going to just pull out the sensor, and we should get 3 volts on this other rail. So here we go. Go up top. And there you go. We got 3.323 volts. Okay, so now the question is, if we put loads on this, does anything happen? And of course, it'll be fine. So we could go put a load on the 5-volt rail. We could go put a load on the 3-volt rail, and everything will be fine. Now here's something interesting. So now we have this 3.3-volt regulator. So if we put a load on this, you know, how will the 5-volt rail change? So just for fun, because it's being fed off of it. Right, and we already did this, right? We already did this, but I'm just going to do it real quick. So here's 5 volt, here's our 5-volt rail, right? And we're sitting at 5.02, and we've got very little current going into this regulator, but it is powering that LED. So it's like, you know, maybe 10 or 12 or 15 milliamps. So let's put a load. Let's put our 100 ohm load. No, actually, let's put our 33. Let's put our 33 ohm load. So I'm going to turn this off because it's going to get hot a little bit. All right, and what I'm going to do here is I'm going to go directly on this power line. So take a look. So I'm putting that 33 ohm right across plus and minus. So there's going to be current going right through there. When I turn this on, we're going to get, the 100, whatever it is, 5 volts divided by 33. Let's do it. 5 divided by 33 is 150 milliamps. We're going to pull 150 milliamps, and let's see how the voltage changes on everything. Okay, ready? And let's drop the input voltage down to 9 volts so we're not making everything so hot. Okay, and it's on. Okay, we're good to go. We see both. And now look, we're down to 5.01. Remember, it was about 5.03. And then if you remember, the 3.3 was about 3.323, I think. And look at that. So 3.32 and whatever change. So that's staying the same because that's regulating. So even though the 5 changed a teeny tiny bit, the 3.3 is staying exactly the same. Hey, and we can do the same thing with the 3.3, right? Let's go ahead and let's pull 150 milliamps out of that. Let me see if I can find another 33 ohm resistor. It's kind of a good one to get 150 out of, or somewhere thereabouts. Okay, so I've got another 33. So I'm going to put that right across this rail. So that's across the 3.3 rail. All right, let's turn it on. All right, so we got both going. And now with 150 milliamps, we barely changed that by 10 millivolts. And then if we look at the 5 rail, right, we look at the 5 rail, it's down to 5 volts. And remember, we're pulling the 150 plus the current we're pulling through the 3.3, and it dropped down to, so just a fraction, 10 millivolts this thing is changing, and that's it. All right. So everything is working good, and we've got total regulation here, and we got 2 supplies. So we got a 5-volt supply, we got a 3.3-volt supply, and we're looking really good, right? Okay. So let's do one final thing here. And let's go ahead and let's change this. So right now we're powering this. If you recall, we're powering this from the desktop power supply, and it's set for 9 volts right now. All right, and take a look at that. So it's set for 9 volts, and notice we're pulling at about 0.3 amps total, which is about right? 0.3 amps total we're pulling, and that's that display on the right, and there's the voltage. And so now what we said was let's switch to the wall wart and see what happens there. So here is the wall wart. Now this thing can only put out 300 milliamps at 9 volts DC, or a total of, if you multiply those numbers, 9 volts times 0.3, right? So 9 volts times 0.3, let's just do it, 9 times 0.3, 2.7 watts, 2.7 watts, all right, of power. All right, so if we want to use this wall wart, our problem is, so that gets us from AC to DC, right? And it's got this little connector on it. So, all right, well, what do we do about that? Well, we need the female version of this. So this is a 2.1 millimeter barrel connector, it's called, all right? And it's got a hole inside the middle. The outside is ground, the tip is positive. On this particular one, it can be the opposite of that. Okay, so so now how do we connect something to that, right? So we just need the kind of the female version of this. So you can see it right here, and this is a bare loose piece, and then I've soldered onto it and then put a connector. So let's take a look at that under the zoom camera. Okay, so we're under the zoom camera here. Let's get this to lock on. So there's our barrel connector, and we just want to connect to that. So here, this is a through-hole component, and then you can see I've also this stuff right here, this is called heat shrink tubing, and you apply heat and it shrinks. We've talked about this before, and I've soldered those wires on there and then heat shrink them, and then heat shrink this and made it real nice, and then I've marked this because these 2 wires are red, and I put a little black to remind myself that that's ground. And now take a look at this. So so you can see there's a post, and that'll go right in there. There we go. So that's how we can connect that, and now we can plug this into our board, okay? All right, so we're looking at our board here, and so now we've got this connector right here. So what we could do is a number of things. And remember, this is all about fabrication. It's just about getting the job done so you can hook things up in a clean way. So one way we could do this is you can take a look here. This little device, right? It's just a bent, pair of this just some posts, right? And it's just bent at 90 degrees. And so what I can do is I can take this and I can plug it into this board, and then I can then plug this into it like that, and I could do that kind of thing. So that's one option. That's option 1. Option 2 is what we could do is we can just undo these wires right here, and we could plug them directly into here. These are female right here. let's try that. So let's be careful here. So this is plus orange. Orange is plus, so that'll go there. And then the yellow here is connected to ground, so that'll go in the other one, which has this little black stripe on it to let me know that that's ground, okay? All right, so, and I make a lot of these little cables, all kinds of them, and you should too. And that way you just have something to work with so you don't have to refabricate everything when you're prototyping. Okay, now we need to kind of put this here somewhere so it doesn't pull all over the place. So I'm just going to wrap it through there, all right? And then I'm going to plug this in. So when I plug this in, we're going to get, 9 volts at 300 milliamps, up to 300 milliamps. Okay, so let's go ahead and let's plug this thing in and see what happens, all right? So I'm going to plug it in, and sure enough, it's turned on and it's working, all right? Now, here's the thing. That's just the transformer. There's no regulation. So at 300 milliamps, it'll actually drop down to 9 volts. But if you don't pull 300 milliamps, it won't be 9 volts. It'll be a higher voltage. It's not regulated. So let's measure what the voltage is. So first, let's get our meter back here. And I'm going to zoom out just a little bit for this. So we've got our meter, and obviously I'm looking at the 5-volt rail. It's sitting at 4.98, 4.99, okay? And we've still got our loads in there. And let's take a look at our 3.3 rail. And it's at 3.3, looks good, so we're happy about that. The question is, what's that input voltage at, I wonder, right? So what's the input voltage at? So let's do this. We're just going to pull the probe out, okay? We'll keep this right here. And then what we're going to do is we're going to just connect one of these to ground, like this, just touch it on that post, and then I'm going to touch the other one right to this input right here, and hopefully I can do this so you can see. Yeah, there it is. So there's the input. So it's at 8.48 volts. So right now, because we're pulling a lot of current, right, the voltage has dropped down to 8.48. Now, if we pull less current, so watch this. Let me see if I can do this simultaneously while holding these things. This is when I wish I was an octopus. All right, so I'm going to hold these two cables. Whoa, 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 whoa. I'm going to hold these two cables, these two probes. Okay, I got them both. All right, so we got the 8.46. Now watch this. So first thing I'm going to do, how hot is this? Is this hot? I'm going to pull this top one out. So that's going to lose 3.3 divided by 100 milliamps, right? Excuse me, 3.3 divided by 33. All right, milliamps. So we're going to pull that and watch this voltage. It'll go up. Look at that. It went up to 9.96. This is actually quite hot now that I have it in my hand. And now we're going to pull out the other one that was pulling another 5 volts divided by 33, which is 150 milliamps. I'm going to pull this one. Again, I'm going to touch it, make sure it's not too hot. So we're at 9.96 volts, and here we go. I'm going to pull it. Ah, woo! That was hot. And that's at 0.06 volts now. So see, this is a 9-volt supply, so what is it doing with this 13 volts? The reason why is it's not regulated. It's just a transformer and a bridge rectifier and a capacitor, and when you're at about 300 milliamps, it will be at about 9 volts. But as you go lower current or higher current, that voltage will change. So be careful. So what this means is this. So check this out. We've also got these two LEDs right here, right? And they're pulling like 10, 15, 20 milliamps, whatever they are. So we're probably pulling, 20, 30, 40 milliamps with those, plus what's called quiescent current to keep these regulators working, or their operating current. Well, they're putting out something, so they're not in quiescent mode. They're actually operating whatever the amount we're burning there. So we're burning a good amount of current here. And but if we didn't have these LEDs, this voltage would go up even higher. Here's the problem. Say that we were using this 9-volt wall wart to power a 3.3 volt regulator. And we look at the wall wart and it says, oh, 9 volts to 300 milliamps. But we think that means it's actually going to always be 9 volts. But you can see right now it's 13 volts because there's very little load on it. What if the regulator says that it can't take more than 12 volts? So say it can take up to 12 volts and it's a 3.3 volt regulator. We just blew it up. Now watch this. I'll pull out this LED, this green LED. I'll pull it out, right? Boom. Now we went up to 13.4 and I'll pull out the red one. Look at that. We're at 14 volts. We definitely blew this thing up now, right? So we definitely blew this thing up. So you got to be careful and you got to understand what all these devices are so nothing goes wrong. So that's 14 volts you might be putting into this regulator. So remember I said, why not just connect the regulator directly to the input there, right? This is why, because a lot of times you're going to go all the way down from 14 volts all the way down to 3.3. That's a lot of burn in one place, and it just might not be able to tolerate it. So let's put these LEDs back in. Let's go back to the data sheet. Let's see what the data sheet says about the maximum voltage. Then for kicks, instead of powering this thing from the 5 volt, we'll just run this all the way back to the input just for fun. So let's go back to the data sheet on the computer. Let's take a look. All right. All right, so we're back here on the computer, and what are we doing? We are looking at the data sheet. All right, so we got the data sheet for this 3.3 volt regulator. So let's see here. Let's see. Here's the different versions. So we're looking what the maximum VIN is. All right, and output voltage. So we could type in, let me type in input here. Here we go. All right, power supply input voltage. VIN, so 20 volts, and then it's saying what the maximum thing. These are the thermal values. So let's see if there's another little table here. And sometimes this is a challenge to find these tables. All right, so power supply, this is absolute minimum, maximum is 20 volts. I was looking for another table, but 20 volts is our maximum, and that's it. So that means you can't go over 20 volts or this thing is just going to burn up. So the 14 should be okay, but it's still a little bit high, right? Anyway, so we know it's okay, so we could hook it up directly to the power input. Now, so what does that look like? So that looks like this. And remember, we already talked about this. So what we would do is we would break this open. Now our 3.3 volt does not siphon current from our, let's make this a different color so we can see the thing. Let's make it cyan. It's not going to siphon power from the 5 volt supply. So basically we're going to take this and we're going to go and we're going to connect this all the way up like this here. All right, so now we've got two separate supplies here. And they're both being fed from the source. But the source now, this 9 volt, really is not 9 volt. It's like 9 to 14 volts, isn't it? It's a lot higher when it's got no load on it. So remember, that rating that you see, that 9 volts or 12 volts or whatever it is at so many milliamps, that's at that load milliamps, and it's still not accurate. It's probably still 10, 20% off, right? So be careful, measure it. So basically put no load on that wall wart, and then see what the voltage is, and can that regulator tolerate that at boot up? So like, for example, say we had a 12 volt a wall adapter, right? 12 volt, but say with no load, it's like 24 volts. Wait a minute, so we think, oh, 12 volts is okay because it's under the 20 volt limit of this, but when it powers up with no load on it, goes to 24 or more voltage, it'll burn that up. All right, so be careful. That's it. And remember, we don't like high voltages. We want the regulated voltage to be, just a little bit less than the input voltage, so we don't have a lot of burn up because these are linear regulators. All right. So anyway, let's go build this. All right. So we're back here over on the bench. So first, let's put back our LEDs here that we've ripped out, and I'm trying to see which way we had them. All right. So there's our green one. The power is clearly still on. And this one goes this way, I believe. Okay, that's good. And we removed our loads. All right. So okay. So now what I'm going to do is I'm going to turn off the power, and then I'm going to move the power input. Let's zoom in here a little bit, and I'll let that camera stop shaking. All right. We're going to take off the input and put it directly over here. All right, all the way to the power itself from the wall wart. All right. So give me a second here. All right, let's turn off the power. So I got to unplug it, right? Or I could disconnect it here, but let's just unplug it. Okay, so it's unplugged now, and so now everything is cold. So now I'm just going to run this a wire. So I'm going to find a nice wire to do that with. Here we go. And why don't we use a yellow just to signify this is kind of a different power feed. And so what about this length right here? A little bit long, but it'll do. Okay, so the input is here on pin 3. All right, so let's be careful here. It's all the way over on the right on pin 3, and that was our input. So I'm going to carefully take that out, and then I'm going to go over here to pin 3, and then I'm going to run it all the way back here. All right, and we got that wire. Okay, so that's it. So now this thing should work again, and everything should be fine. So I'm going to rehook up the multimeter to ground and power. All right. And now we'll be able to measure the 3.3 and the 5 volt with this situation right here. Okay, so here we go. I'm going to plug the thing back in. Okay, we see we got both power supplies working. All right, there's our voltage on the 3.3, so that looks good. We got 3.3 volts, all right? And let me zoom out just a little bit here. Okay, so we got our 3.3 volts, that looks good. And now let's switch it to the 5-volt rail. 5-volt rail, and there's our 5 volts. So what did we gain here? What we gained was that now the 3.3 is not siphoning current and power off of the 5-volt. It's getting it directly from the source. The downside is we've got to go from 9 or 12 volts all the way down to this 3.3 volts in here. So depending on how much current we're pulling through here, we're going to burn a lot of heat. So this is going to get pretty hot. Right? So right now, that's only 10 or 20 milliamps. So if I put that load on there, that 33 ohm load, let's see if we can find that again. It's got to be here someplace. All right, here it is here. I'm going to put this in. All right, so I'm putting that in right there. And so again, what is that? That's 3.3 divided by 33 equals 100 milliamps, right? So that's 100 milliamps. So 100 milliamps is going through there. And what's the power dissipation? So it's I squared R, right? So 100 milliamps, right, squared times 33 ohms is 1/3 of a watt. And this is a 1/4 watt. It's gonna get pretty hot, but it's gonna survive it. It'll be okay, all right? Okay, so now we have that going on, and now we're pulling 100 milliamps here, but now this regulator, which has a 500 milliamp max output, this one has an 800 milliamp max output. This regulator has got no current being pulled by this one, so it's still nice and independent, all right? And that's what's good about it. It's independent. We're not messing with it here. Another thing is, if this 5 volts, say, went to some motors and we started pulling on those motors, right, the 5-volt output might get all destabilized, but we're getting the power from the source here, so this 3.3 will stay nice and clean, all right? So anyway, we got a lot to do. We got a lot more stuff to do. So now we could go and we could add another regulator for a 1.8 if we wanted. So I've got another one right here. And let's see, what do we got here? So here's another one. And this is a 1.8 volt. So we could just add this exactly like that. We could have 5.5, we could have 3.3, we could have 1.8. But we're not going to do that because literally it's the exact same thing. But what we are going to do is we are going to try some experiments now where we're going to, so we've been using these DC power supply, right? We've been using the wall adapter now, and then the desktop power supply. Now what I want to get into is the use of transformers. So we are going to go straight from AC like crazy people, and we're going to hook transformers and a bridge rectifier and a smoothing capacitor and kind of build what's inside the wall wart. Now I know we've already sort of done this in the diode stuff, but I want to do the whole thing in the power supply. And what we're going to do is we're going to put it right here, right in this area. Then we're going to use it to power this subsection right here. All right. And then when we get done with that, I got some other cool things planned where we're going to play with some motors and we're going to look at noise on the oscilloscopes. Okay. All right. So anyway, so that's about it. And so let's stop here and we'll come back in the next lecture and start playing with the transformers. Okay. I'll see you then. Bye. All right, welcome back, and we're on the next lecture. And so last time we built our power supply, we did our 5-volt, we did our 3-volt, we did some regulation tests. And so this time what we're going to do is we are now going to add a transformer to the system. So if you recall, last time we had the wall wart over here to the left, and we plugged that into the wall. And we had a 9 or 12 volt, I believe this one was a 9 volt wall wart or wall adapter. And if you're wondering why people call it a wall wart, it's because it sticks in the flat wall and it's this black thing that kind of sticks out. It looks like a wart, so kind of gross, but that's where that little phrase comes from. Little fun fact. Okay, so what we want to do is now, let's say that we are designing a printed circuit board, and we want to put the power supply, the whole thing, into the circuit board ourselves. And we do not want to have a wall adapter at all. So we want to plug this directly into AC, like we're making a appliance, a TV or something. So you plug it into the wall, and inside of that TV or appliance, it has to have a power supply that takes that offline. It's called offline. When you talk about plugging things into AC, you call it an offline power supply, and it's kind of interesting because we say the word online to mean on internet, but when you talk about AC power, you say it's an offline power supply. It doesn't mean that it's actually off, right? Like its power is off, it means it's off the line. You're taking it off the line. All right, so again, just some conventions of the way people say things. When I first heard that, I'm like, offline, does it mean it's off? But it doesn't. It means it's off the AC power line. All right, so if we want to make an offline power supply, we need to go from AC to DC, and that means we need a transformer. So what we need to do here is we need to look inside the wall adapter and what was inside of the wall adapter. So let's take a look, and let's remember that. So the wall adapter, all it really has, and I'm going to put it right here, we'll just say wall adapter. And inside the wall adapter is just a transformer, right? And the transformer is here. And on the input, which is called the primary, remember that, primary. All right, that's where you put your 120 volts AC, okay, at your 60 hertz. In the United States, in other countries, it's a slightly different voltage, might be higher, might be at 50 hertz. All right, but in the United States, it's 120 AC at 60 hertz. Then the secondary, which is over here, secondary, that's where we have the step down. So this might be, we might get out to 12 volts at 500 milliamps, or we might get out 6.3 volts at 400 milliamps, whatever the design of the transformer is. And then you remember there's a little convention, it's kind of a dot convention. And the dot means that as current is flowing this direction, then current's flowing this direction. So they flow in the same, so the dot's a little convention to orient the coils, because this is kind of an abstract symbolism of it. And then if there was another coil, which can also be the fact, you can have multiple secondary windings, you have multiple primary windings, and then there's that dot right there, okay? All right, so we have the wall adapter, and part of it here. We have the transformer. And then, so now the question is what kind of comes next? So remember, the next thing that we put inside here, and we'll draw that in a different color. I'm going to draw that in yellow. So then this goes into our bridge rectifier, right? So let me just see if I can draw this bridge rectifier here. Let's see. We'll kind of start it like this and go like this. All right, and we'll do that. And then we'll draw these diodes, so we could have this diode would go this way, all right, that diode would go that way, and then this diode here would go this way, all right, and then this diode here would go this way, and then this diode here would go this way, and then off of here, this would be the output, all right. All right, so so as AC comes, comes through here, we get a voltage, we get a positive voltage, a forward bias is this is reverse bias, and then likewise over here, when we get positive, it goes through here, and then negative will go through here. So that would be plus and minus. That's how that bridge rectifier would look, all right, if I've drawn those correctly. All right, and then let's just erase some of this over here. Okay, and all right, so now we've got our bridge rectifier. So now we have DC. Okay, so we've got DC here. So we had AC here. Now we have still AC here, but lower. And it's lower because in this case, let's say that this was a 12 volt, right? 12 volt transformer with primary. So so basically this would be like a 10-to-1 ratio. So we're dropping down 10 times to this 12 volts here. Now we've got our DC. All right, so then we could just stuff this right into this regulator up here, right? But now what we do is we put a big smoothing capacitor, remember that? And this thing is, something like, 10,000, microfarads or more. We do some calculations, right? So do some calculations, and we did in the documentation in the book, I think I calculated as needing something around 20,000 microfarads, depending on the amount of ripple, and you need to read that to see how that works, but like 10,000. So typically in our toolbox here, we might have some nice 4,700 microfarad, so we might put one or two of those in parallel, right, to get that 10,000 for that particular smoothing and ripple that we had in the book. Either way, put a big smoothing capacitor, and then here we go. Now we're ready. We got plus to minus. We're going to have DC, and we're going to have some voltage here. So now if this is a 12 volt secondary with no load on it, you're going to get anywhere from you know, honestly, probably 14 to 18 volts. All right, you get 14 to 18 volts with no load. Then as you put the load on, this voltage will decrease until it'll hit 12 volts at the rated current, roughly. So if they rate it and say it's 12 volts at 500 milliamps, when you finally pull 500 milliamps out of this thing and you're getting 12 volts out of it, uh, uh, or excuse me, when you're pulling 500 milliamps out, you'll finally get the voltage, it'll drop down to 12 volts. But before that, it'll be very high. So you got to be careful, because remember, if we put this into one of our regulators, you know, like this one or this one, and it can't tolerate that high of a voltage, it'll blow out, right? Okay, so we've got our DC. So all we're going to do now is we're going to build this stuff to the left, and then we're going to plug plus and minus right over here, right? So now what we're going to do is we're going to get rid of this wall wart, or wall adapter, right? Got rid of it, it's done. Alrighty. Okay, and we are going to directly, so you know, this is our plus and this is our minus, this is our DC in. Now this plus and minus, we're going to connect to, you know, this plus and minus right here, and that's what's going to power this entire chain here. Okay, so what we're going to do is, so I've got a lot of stuff in store, and I'm really excited actually, because this is kind of another one of these examples where we know enough where we can start building things and experimenting. We're going to play with motors, we're going to do a bunch of stuff. We're going to play with AC out of the wall and do a bunch of different little experiments and learn a lot of hands-on stuff as we go. So we're just about to do that. We're going to probably break this up into 2 or 3 lectures, I think. But the first thing is, we are going to work with a couple different transformers, all right? So I'll show you the transformers up close when we get to the bench, but before that, what I want to do is I just want to grab the transformers and kind of show them to you here. So there's a couple ways that we can do this. So this, let me get it right here in front of the camera here. Here is a transformer. That is a big transformer. Now, again, I'll show this to you a little bit later, but I can see the primary says it's 120 volts at 60 hertz. So this is the primary right here, all right? And then the 2 wires, that's going to go directly to AC. Then we've got these 3 wires here. This is the secondary. Now, here's the center tap of the secondary, all right? And so basically there's a coil in here, and what the coil looks like is just like our coil right here, except there's a center tap right in the middle. All right, and so there's a center tap, there's a top, and there's a bottom. So it's almost like there's 2 coils in here. All right, so basically the way that these things are wound in this case is this is like plus 6.3 volts. This is like a ground, and the bottom is like minus 6.3 volts. So if we take these 2 outside leads, that'll give us 12 volts output. Yeah, this one's 6.3, 0, and 6.3. So that'll give us 12. If we take these 2, we'll get 6.3. If we take these 2, we'll get 6.3, 180 degrees out of phase. So that's what these are. So when you see secondaries, you're going to see these more than one output because it may be center tapped or multiply tapped. Hopefully on the primary, you've just got 1 input, okay? All right, so there's a big one, and this one right here is a 3 amp transformer. So that's good. Now you can see how big transformers are, and that's why power supplies are so big unless they're switching power supplies. Okay, here's another one right here, all right, and I don't know if you can see that. That's secondary and that's primary. And again, I'll read this. It says primary 120 volts. There's our 2 black leads. And then on secondary, it says 12.6 volts, center tapped at 1.5 amp. Now, where did I get this from? You know, who knows where I pulled this from. The center tap got cut at some point. Now I could have rewired that if I want, but it's 12 volts across the whole thing and it's center tap. So again, this would be 6.3 and over here would be 6.3, but we're just going to use it here and here. All right, and again, you see I've done some special stuff to these leads so we can plug them into our solderless breadboard. All right, so again, these are open frame transformers. They bolt right to the housing of some big appliance. You know, I could have got this out of a coffee machine for all I know. And then here's another one, a little baby one. Little baby transformer. Again, open frame, you kind of screw these. Now this has no information on it, so we would have to measure this and test it to see what we're doing. But this is an AC transformer, I can tell you that. Okay, so we will use these in an experiment, and that'll be fun. Now, the other thing that I want to show you is here, and we're going to look at these right now before we get to the bench. So again, we'll look at these up close, but So here are a couple transformers, right? And these, and here's another one, all right? And these are PCB mount. So you can see they've got pins on it, and this like plugs right into a PCB. So this goes right into your PCB, so it's not this kind of like open frame one where you're kind of connecting it and screwing it into some enclosure. This goes directly on your PCB. Now when you read these, there's a couple things. These two manufacturers are Tamura, and we're going to look at that, and Triad. TRIAD. And I like both of these manufacturers. They make really good transformers, very high quality. They have all kinds of variation, and then they've got their little part numbers on them. All right, so looking at this one right here, so this is a 3FD 312. And again, you may or may not be able to see it, but 3FD 312, right? 3FD 312. So let's go to internet here, and let's go here. And let's see which one. So 3FD312. So I've already searched for it, 3FD312, and it came up with the manufacturer part number. And so here is this transformer. So this one right here, this transformer right here is what is on the screen on DigiKey. So let's take a look at this information. All right. So the first thing it says voltage primary is 115 or 230. It's a secondary at full load puts out in parallel mode 6.3 volts or in series mode 12.6 volts. Current output max in parallel mode is 400 milliamps, in series is 200 milliamps. All right, primary windings dual, secondary windings dual, center tap no, power max is 2.4 volt amperes. All right, so that just means the product of volt amperes is 2.4. And then it says some of its dimensions and so forth and all that. All right, so now a little bit confusing. So what are they talking about? Well, let's take a look at this. This is how this thing looks internally. All right, so again, if you can see this, it's got multiple pins. So there's 4 pins on the input and 4 pins on the output. So 4 pins on the primary, 4 pins on the secondary. And so the whole point is you buy this transformer and you want it to have a little bit of flexibility. The reason why is because in the United States, for example, we've got 110 and 220, or you can call it 120 and 240. Bottom line is we've got these 2 different voltages. And so this can handle either of those. And see here it's saying 115 or 230. But the point is, if you're dealing with 110 voltages, 115, 120 voltages, you just use one of these primaries or this primary, or you put them in parallel. If you're doing 230 volts, then what you do is you tie these primaries together. You tie 3 and 2. Then on these outer contacts, you put the 230 volts. Same thing on the secondaries. So one of these secondaries, right? One of these secondaries will put out the 6.3 volts. The other one will put out 6.3 volts. If you series them up, if you tie 6 and 7 together, right, then you'll get 12 volts from 5 to 8. If you parallel them up, you'll still get 6.3 volts, but you'll double your current, right? So remember, with transformers, you gain and lose nothing, all right? You don't get anything for free. If you step up voltage, you step down current. If you step up current, you step down voltage, right? Ultimately, they're not magical devices, and they are lossy. And so the energy put in is not going to be equal to the energy put out. It'll be 95, 99, 99.9% because there's heat losses inside of the coils and so forth. They have resistance, right? And then there are other things called eddy currents that are generated in the magnetic cores. So they're definitely they're lossy. They're not perfect, but they're close to perfect. They're actually not bad. So transformers are fairly ideal. Okay, so we're going to hook this thing up. And what we're going to do is we're going to use these, we're plugging into 115 volts, 120 volts, 110 volts, right? It varies. So what we're going to do is we're going to connect the primaries together in parallel. So we're going to connect 4 to 2 and 3 to 1. Then we're going to connect the secondaries in both parallel and series so you can see it. So if we connect them in parallel, we'll get 6.3 volts out. If we connect them in series, we'll get the 12.6 volts out and half the current. So that's what we're going to do with that when we get to it. But first we're going to use this kind of transformer. But I wanted to show you this transformer and how you look it up. And again, you know, it's showing the different pinouts and stuff here and all that. Now, you want to be really, really, really careful when you're playing with these transformers, all right? So again, I'm going to talk about it more when we go on the bench, but we are going to be messing with AC voltage. I'm going to wear my gloves. I've got rubber boots on. I'm going to have my protection glasses on, and you're going to be very careful. So many times I have like said I wanted to connect 1 to 3 and 2 to 4 to put these things in parallel or whatever, and I accidentally connected, I shorted 1 to 2, and that shorted a coil winding, or I thought that this was the secondary side when it was the primary side or whatever. So I want you to quadruple, sextuple, decimal check these things many times, right? Deca check them. You need to make sure that you hook things up right because you don't want anything blowing up or shorting out. The worst that can happen is you can get shocked or start a fire, and at least you might throw a circuit breaker or blow a fuse, if you're lucky, but bad things can happen. So be very careful. And then we're going to talk about some other things about putting these things together on solderless breadboard. These pins are rather large. These pins of these transformers are not small, so they're really hard to plug in the solderless breadboard. We're going to talk about that. Okay, now I want to look at a couple others while we're here. I've got a couple other small ones here. I've got a triad, and I've got a triad, and this one is so small I can't see it. So let me look with some magnifying glasses. This one is FS12-090. So this one right here is FS12-090, and I believe I've already got it up here. Yeah. All right. Now, one thing I wanted to tell you. So here's Triad's website. So this is Triad Magnetics, and the other one is Tamura. This website, if you do not put the exact part number, see up here, FS112-090. So when I look at the part, I'm like, FS12-090, and I just put 90, and it couldn't find it, right? You got to put the 090. So remember, search never works really good in these things. So anyway, we click on that, check stock. And then it says it's all these different places, Mauser, Future, Newark, etc. And then, so I went to one of those and then found the actual part, and here it is. Okay, so again, the FS12-90 is a dual primary, dual secondary, split bobbin design. The bobbin is this thing right here that the wire's around. All right, and then this metal thing is called the core. In this case, it's laminated iron. And then it tells you all about it. It gives you all the information. And then again, you can see it shows you these schematics of 1, 2, 3, 4, 5, 6, 7, 8. It's using the dot convention to show you the directions currents are going in. Here's if you want to set it up in parallel. Here's if you want to set it up in series, and so forth. All right. And these two manufacturers make very similar components. So if you can't find one at one manufacturer or it's too expensive, you can swap it with the other manufacturer. All right. Now this particular guy only puts out parallel is 6.3 volts at 180 milliamperes, or 12.6 volts if we put them in series, but at only 90 milliamperes. And it's really little. And so that's what you expect. So that's just not getting us much. And then here's a Tamura part, which is very similar, and that's why I wanted to show you these. So they're almost identical. And the Tamura part, if I look at this, it actually has it on here. So the Tamura part, for the same size, instead of putting out 12 volts, it puts out 10 volts in series or 5 volts in parallel and a little bit more current. So we didn't gain anything, but we gained a little bit more current, a little less voltage if we can tolerate that. Say if we used an LDO regulator instead of the linear 7805, where we require a 2 volt over the voltage we're regulating, we could probably get away with this 5 volt because it probably puts out 5.1, 5.2 volts, and with an LDO we only need a couple hundred millivolts above regulated voltage, and this transformer would work. But because we're using this kind of primitive linear 7805 and we know we need that 2 volts of headroom, we kind of need the 6.3 volts or higher, so we can't really use that one. So we would use the Triad. All right. But in our case, we're only going to do one experiment with the transformer, the PCB transformer. We're going to use this big Tamura one, the 3FD 312 that we put up there, and play with that one. All right. So here's what we're going to do for the experiment. We're going to first play with these transformers here, right? And we're going to put it right back on our circuit. Then we're going to do the printed circuit board version that would plug into a circuit board, and then we'll probably wrap that up, and then we're going to go and do some experiments with some motors and some loads, and I want to show you some stuff. So this is it. So let's stop here, and then let's start back up on the bench. Okay, so let's take a look. What we're going to do, we're just going to basically build this section here, and then we're going to put different transformers in here and kind of see what happens. So let's stop here, and let's meet back at the bench. All right, bye. All right, so welcome to the next lecture, and we just took a quick pause to catch our breath, and what we're going to do now is we're going to go to the bench and we're going to take the power supply that we already built, which is the section up above here, right? And now we're going to add in a transformer, and we're going to either do it with one of these kind of open frame big transformers that mount onto an enclosure, or one of these PCB transformers. So we're going to do it in both cases. We're going to add a bridge rectifier, but we're going to use a bridge rectifier component that has these diodes in it. We're going to have this capacitor here, smoothing capacitor. Then we're going to take the power and we're going to put it into our already existing voltage regulator pair, 5 volts and 3.3 volts. So let's go over to the bench and let's do it. Okay, so we're back here on the bench, and we've got our design here. And now you can see I've already added some components here. So what I want to do is let's zoom in. And the reason I did this because it's kind of time consuming to do this, and I did not want to sit here and waste too much of your time doing it. So what we're going to do is we're going to do 2 experiments. And the first experiment we're going to use the open frame big transformer, like one of these right here. And you can see this. So this is the one with 120 volts primary, and then secondary, we've got these 2 leads, or we can do it with this one. All right, and I'm going to show you how would you even hook that up. Okay, so how would you even hook that up? All right, then we are going to use our PCB transformer. All right, and here is what that looks like. So we're finally going to take a good look at this under the camera here. Let's see if that can focus. There you go. So there's Tamura 3FD312, and you can see the numbers are 1, 2, 3, 4. All right, so this is the primary winding 1, 2, 3, 4, and then the secondary windings are here. 5, 6, 7, 8. Notice they go backwards. So in this case, it went left to right, 1, 2, 3, 4. In this case, it went backwards, 5, 6, 7, 8. So you got to be careful with that. All right. And then we got to plug this into this board. All right. And then connect these things together. So what we're going to do is we're going to connect the primaries in parallel and the secondaries in parallel. And we're going to be working with the 115, 120 volt primaries, and then we're going to take the secondaries, and those are in parallel as well, and that's going to give us the lower voltage but the higher current. Okay, now the problem is that, okay, a couple things here, so let's just take your time and bear with me here, and I'm going to go over a number of different things. One, these are really big pins, and they do not want to go into this board very easily. All right, let me see if I can get the camera to cooperate there. Yeah, so they don't want to go into that very easily. We've got to push really hard and jiggle them around, and you end up stretching these pins out in here, these sockets, but that's just life. All right, so what we need is we want to put this thing right here, but it's like so big, so look at a top-down view. If I try and put it right here, right, if I try and put it right there, like you would an IC, there's no room for it. So what you end up doing is you straddle 2 different boards, and that's why we had to use this big board. So what we're going to do is we're going to end up putting it like right here. All right, we're going to put it right there, and then there's still not enough room, so we're going to put, some of the primaries we're going to connect together here with these wires, but then we don't have room over here, so then what we do is under the transformer, I connect these secondaries together and then bend these wires down. Then I take the secondary output and I put it into this, which is our bridge rectifier. So let's take a look at that. So I'll just turn it up here. So you see in the center, that's where you put an AC, and then on the outside you get plus, on the other side you get minus. So then I've got the plus and the minus ran to this big capacitor, which is 16 volt at 4,700 microfarad. So we want to be careful that whatever voltage we get out of here is not greater than 16 volts. Now in reality, when you do good design, I'd want that to be twice the voltage I would ever get, maybe even 3 times. So if we're thinking we're going to get out 12 volts, I wouldn't feel comfortable unless this capacitor was like a 25 or 35 volt, because for one, it's going to age. 2, it's derated. 3, there could be spikes, all kinds of things. You don't want to damage that electrolytic capacitor. Okay, so this just smooths this out, and then the capacitor is just kind of sitting there, and then we've got the 2 outputs. Here's the negative, and then here's the positive, which then goes and feeds our 5, and then here's our 3.3 volt feeder line directly to our 3.3 regulator. All right, so that's what we're going to do. So now I already hooked this up because this took a little time. Now, a couple things I want to bring your attention to that are very important. One, these are pretty thick wires right here. These are thick wires. So these are 20 gauge. The wires on most of this other stuff are 24 gauge, all right? So they're thinner. So I use these thick 20 gauge wires. So because I'm doing power supply stuff, I really want to have thick wires, especially because on the primary, this is, here's AC coming in here, 120 volts. So I want to have some big wires. Now, your wall wiring is like 14 or 16 gauge, or even 12 or 10 gauge near your mains. But typically it's about 14 to 16 gauge, and these are 20 gauge. So these are pretty thin compared to AC wall wiring that's in your home. But on here, we can get away with this because we're not going to use a lot of current. But again, this is a smaller diameter wire, and you got to be careful. But it's the biggest wire we can get to fit inside of here. Okay, so in one case, we're going to put this down and experiment with it. But first, we're going to start off with one of these transformers right here, and we're going to plug one of these guys in. All right, so now let me show you what we've kind of done to make this happen. Okay, so we got our transformer here, and again, let's let the camera do its thing. So there's a primary of 120 volts. So the first thing that I did was there's the primary, and I've stripped these wires and I've tinned them. And let me put my hand here maybe so the camera will kind of cooperate with us. Let's see if it will. There we go. I've tinned them so they don't fray, all right? So these are stranded wires, so I've tinned them, all right? And that's where we're going to connect to our AC power. How are we going to do that? We'll get to that in a minute. Now, here's the secondary of the yellow wires, and you can see right here it says secondary. Give the camera a second here to cooperate with us. 12.6 volts at 1.5 amps. So 12.6 here, and then here's the center tap, but we're not using it. That would be like 0 volts, then this would be plus 6.3, this would be minus 6.3, but we're just going to use the two outside ones, which will give us a 12.6, and someone cut that before I even got it. At some point I probably should add a wire there. But this is going to be our output, and then you can see what I've done here is this. I've soldered on these little posts, all right? I've soldered on the posts. And then I've used heat shrinking to heat shrink these so I don't touch them, make contact with them. And remember what heat shrinking is, just a rubber kind of tubing that when you apply heat, its diameter usually goes to 50 or 30% of what's original diameter, and that's how you make nice cables and protectors and that kind of thing, all right? Okay, so we've got our transformer, all right, so now what else do we need? All right, we need a way to get AC in and make a connection to these two wires right here, right, without killing ourselves. Now, you could just be crazy and plug this right into the socket, right? A crazy person would do that. You could literally plug these two things right into a socket. That's crazy. So what we're going to do is we're going to, well, I already did, we're going to fabricate a cable. So let me show you this cable that I fabricated. All right, so I've zoomed out a little bit. So here is a cable that I fabricated. So the first thing is, this is like 14 gauge wire. And so this is a connector that you can get at a hardware store, and it actually opens up. There's a screw, and then inside of it there's a ground, a hot, and a neutral wire, which then I connect the ground, hot, and neutral. So ground is green, hot is black, neutral is white, okay? And then if you look at the plug like this is neutral, this is hot, this is ground. So that's kind of the orientation that they go into the United States. So if you were to open this up, you'd see that I'd screwed those in there. All right, and then there's some more heat shrink tubing just to make that nice so it can bite onto it good and not pull out. All right, so then at the other end of this, now what do we do? So at the other end of this, we got three wires, right? So now we know here's hot, right? So that's one of our AC lines. Here's neutral, and then here's a ground, which would go to the metal and the frame and that kind of thing. Now, ground and neutral are actually electrically connected at the junction box. So we would connect this to metal if we had metal, but in this case we don't really have a metal enclosure. So I just protected it, again, say I protected it with some heat shrink tubing for now. All right, and then what are these little things on here? Okay, so these are really, really cool. So now I'm sure you've seen little wire nut connectors for AC if you've ever messed with hooking up any lights or sockets or whatever, and you put your wires together, you get your wire, you go like this, right? And you tie them together and you twist this little thing on it, and you tape it. It's just horrible, horrible. So these things right here, these are really a wonderful invention. So what you do is you just plug the wire in there and you click it, and these stay shut. This company is called Wago, W-A-G-O, all right? And these little connectors are a little bit expensive, but they're totally worth it because they're reusable. So now here's our AC lines, right? And I can show you, here's how they come. You buy a kit, and these kits aren't cheap. So here's a kit of them, and there's different sizes here. Wago, W-A-G-O. You can find them on Amazon.com or hardware store or whatever. And they're, like here's one that's, a 2, here's a 3 connector, so you could have one and then you could split it out. And then, here's a 5, right? So this is, I think, $40 or $50 or maybe $80, but definitely worth it. All right. So now what we're going to do is to connect our transformer, we are just going to take our little connectors here. We've got our hot and neutral. Now, obviously, I've got this unplugged, all right? So we're going to connect it up just like this, and we're going to put one wire in here. We're going to put the other one in here, like this, just like that, and then we're going to close it, all right? And believe me, you couldn't pull those out if your life depended on it, all right? And that's the primary. So now this thing is good to go. And then here on our secondary, we got our 2 wires. So we're going to go back to our design here. So here's our secondary. So here's our stepped down AC. So that's going to go right here. This is where the stepped down AC goes, and then it goes into the bridge rectifier, and then it gets smoothed by the capacitor, then it powers the system. Okay, now, what's the other thing that we're going to do? So we got this hooked up. We're going to be very, very careful with this. All right, so now what I'm going to do is I'm going to unravel this wire, and I've got a socket down here. Okay, I've got a socket down here with a power strip, and the power strip has a switch on it, so I can turn the thing on and I can turn the thing off. All right, so now what I'm going to do is I'm going to get everything kind of ready for you here. So first, let's get everything positioned. I'm not plugging anything in yet, not doing anything. All right, and as a matter of fact, before I plug this in, I want to do an experiment with you, and I want to show you some stuff. So let's just take our time here. So plug this in, get this over here, get this all situated. All right, so we got that, and I'm going to put that right like that, put this up here so you can kind of see it, moving things around a little bit. Okay, so we got that. Now, what I'm going to do is, we don't want these things to touch. All right, so I've got the AC over here to the left. All right, I've got the wire, the AC wire. It's going to go down into this power strip, which has also got a fuse in it. All right, and I'm getting ready to plug this in. Okay, so what I'm going to do is I'm going to put on my gloves. I've got my glasses already on. So I'm putting on my rubber gloves here that can take, I don't know, 600 or 1,000 volts, something very high. And so if something happens, if I have to grab it, I'm not going to shock myself or overheats or whatever. I got my glasses on in case anything explodes. Okay, so now what we're going to do is we are going to power this thing up. We're going to put AC in the primary. So we're looking for 12.6 volts out here on the secondary. And that's the first experiment. So let's do that. Let's see what happens. All right, so I'm plugging it in. All right, so we're plugged in right now. Now we're not on, so nothing's going to happen. All right, now another thing I want to do is I'm going to bring this meter into the situation here. Let me see, can I get this so you can see it? Not really. So what I'm going to do is I'm going to move this over just a little bit. All right, move that over just a little bit. There's never enough room, so sorry everybody. There we go. So I've got the meter, and I'm going to put the meter on voltage, and then I'm going to put it on AC. I'm going to put the range on 3 digits, even though we only need 2, all right? So we're going to put it on that, and then what I'm going to do is I'm going to measure what's coming out of these 2 lines here, okay? So first I'm going to turn this thing on and do that. All right, so here we go. And we're always waiting for an explosion. So everything looks good, everything's safe, nothing's touching. These aren't touching, so we put those there. Be very careful. And here I go, I'm turning it on. Okay, so it's turned on, and nothing's exploded, so we're nice and safe. So again, now remember, the AC hot is coming in over here on the left side, right? So I don't want to mess with this. Over here on the right is a secondary. We're isolated from the primaries. That's one thing, so that's good. And now we've got the secondary. So now I'm going to touch this here and here to the multimeter. I'm looking at the multimeter. Looks good. Okay, so now I'm going to bring this over here so you can see it. All right, and here we go. And I'm going to touch this while you're looking at it. All right, we've got 13.5 volts. Okay, now, does anyone remember why we got 13.5 volts? It's supposed to be 12.6 volts. Why is it 13.5 volts? There's no load on it. Only when the load hits the 1.5 amps will it be drop down to 12.6 volts, all right? roughly. All right, so that's good. So everything's looking good, so I'm happy with that. Now let's play with the oscilloscope a little bit. All right, so this is on right now. Okay, so it's hot, it's running, and so let's get a camera on the oscilloscope. Okay, so we've got a camera on the oscilloscope, so I want you to take a look here. So we got our two channels. So here is one channel, yellow, and the other channel is blue. All right, so what we're going to do is we're going to start looking at things with these two channels. All right, now, what's the first problem that we are going to come into when we start measuring things with the oscilloscope? The oscilloscope is being powered off the mains. Therefore, its ground is grounded with the mains. And if we try to hook this probe up, we could short something out. We could blow the oscilloscope or something else. But the transformer has inductively, magnetically coupled, right? So we've transformer isolated through induction the secondary. So now this is no longer connected to anything. This is not connected to the house. These are just basically, it's a coil in here generating a voltage. So we can safely connect our oscilloscope to that. But if we were to try to measure these mains, we would potentially blow out the oscilloscope and short it out. So if we wanted to do that, measure these mains, we'd have to do it either with a multimeter because it's isolated, or we could do it with that, remember that standalone oscilloscope that I have? Right, so we'd have to do one of those things, but we're measuring the secondary, so we're okay. All right, so here we go. And so what I'm going to do here is I'm going to connect ground to either one, and let's see what channel this is, channel 1. All right, now, so I've got it on channel 1, so we should be seeing about 13.5 volts RMS. Let's remember, RMS, right? It's not peak to peak, it's RMS on the oscilloscope. So let's go to the oscilloscope. Here we are, and so let's scroll this down a little bit here. All right, we got it centered. And now if you look, what does it say? Cyclic RMS is 15.6 volts, and then it's showing this, rather large peak to peak, and we're on 5 volts per division. The frequency is, let's see if we can see the frequency here with this current display, and I don't believe I've got frequency on here, so let me see if I can get frequency on one of these displays. All right, frequency, there we go, okay. And did that show up someplace? There it is. There's frequency up top. It's 60 hertz. Hopefully you can see that. Yep. So we got 60 hertz there. So that is the signal coming out, and that's exactly what we, expected. All right. Okay. Now, so that's that transformer right there. Now, what I want to show you now is, now remember, this transformer is not center tapped. Okay. So we only can see this one voltage, right? So let's get the center tapped transformer. Then let's look at the voltage on the top tap and then on the bottom tap, and let's see how those relate to each other. So let's do that. So first what we're going to do is we're going to turn this thing off. So I'm powering off the AC line, and I'm unplugging it, all right? I'm not completely, right? Unplug the thing. There it is, all right, to prove it. It's unplugged. Okay, now we're going to come over here and we're going to undo it. Okay, and we're going to undo the oscilloscope. We're going to undo this. It never hurts to be extra safe, all right? Because when you're hurrying up or something, you make a mistake and can really hurt yourself. Okay, so we're going to get our center tapped version here. All right, so here's our other transformer. There's the primary, 120 volts at 60 hertz, and then here's the secondary, which is supposedly 6.3 volts on each tap, okay? But I want to show you that so you can see exactly what's going on, all right? So here we go. So I'm connecting these AC lines. So there's one of them. You see how easy this is? If you do AC installs, if you're an electrician, most electricians have discovered these things. If they haven't, if you haven't, you want to get on these things. These would make life so much easier and cleaner. Okay, so we got that hooked up. I'm going to put this back right here so you can see it again. Okay, so now we got 3 lines here. All right, now this one, the black one, is kind of going to be in the center. We can call that the ground. Remember, there's no such thing as ground now because this is inductively coupled, but this can be a reference. This will be going on a rising voltage. This one will be going on a dropping voltage, or vice versa, this other one. All right, and so this one's going up 6.3, this one's going down 6.3, so we'll see 6.3 here, we'll see minus 6.3 here, or vice versa. But if we look at just these two, we'll see 12 volts going back and forth. So let's just start analyzing this, all right? So what I'm going to do is I'm going to put the ground of channel 1, and I'm going to put the top tap up here on channel 1. Then on the bottom tap, we're going to get our other lead. We're going to connect the ground here, that's its reference. Then we're going to go to the bottom one here. All right. So now I want you to think what you think the oscilloscope is going to look like. So channel 1 is the top, channel 2 is the bottom. All right, so what's the oscilloscope going to look like? All right, so here we go. I'm going to go plug this thing in, check it out, and make sure there's nothing touching. All right, so we're going to plug it in. All right, I double check again. Let's turn it on. It's on. All right, and there we go. And you can see we got our two waveforms here. Let's line them up. So channel 1 is the yellow one, and channel 2 is the blue one, clearly. Okay, so now look at that. So what do we see? Let me slow it down just a little bit. They're out of phase 180 degrees, right? They're out of phase 180 degrees. So if we just use the yellow signal, right, that will give us 6.3 volts. And if we look at, let's go look at the RMS values of these things. Okay, so let's go back and try and modify this thing. So on channel 1 here, we'll put this back on cyclic RMS. Okay, so there's cyclic RMS, and it's saying 7.8 volts. But wait a minute, it's supposed to be 6.3 volts. No, it's only 6.3 when it's at load, and whatever the load, whatever the printed current is, it says it's 3 amps. So only when we start pulling like 3 amps or 1.5 amps are we going to get that voltage to drop down. So that's going to stay up there like that. All right, and that's the yellow signal, right? And clearly you can see that the blue signal's the same. All right, now, so they're 180 degrees out of phase, right? So now what if we were to add them together? So now instead of going from the center tap, if we go from the top tap to the bottom tap, so go back to the overhead here, we go to the top tap to the bottom tap here, right? We're going to get a total of the 12.6 volts, right? But again, it'll be larger because we're not loaded, right? So what I'm going to do is I'm going to undo the grounds, and we only need to use one probe here. So now we're going to go from top to bottom, and I use the yellow, and lo and behold, look at that. Look at our giant signal. Now we got 16 volts RMS, which is right, because it's 8 volts-ish when it's unloaded. So now we doubled that, so we got 16 volts. So this is like our 12.6 volt output. So it's at 16 volts. So now if we come back to our regulators here, right? And we got that 16 volts coming in. So we're going to get 16 volts out of this, right? 16 volts. Or we could start it off with that 8 volts, right? If we put the 16 volts in here, that's going to make this regulator pretty hot, and it's going to make this one really hot because this is a 3.3, right? 3.3 volt. And then the question is, are we going to go too high? I think we looked up that this could tolerate 20 volts, right? So that 16 is pretty close to the mark. So what we can do is we can just use one of these taps if we want, all right? So we can just use half of it, or we can use the double of it. So we're just going to use half. So we're only going to use half of the transformer, and we're going to run it at like 8 volts into this regulator right here. So let's do that, okay? So now let's turn off the power. So we're going to turn the power off, all right? All right, so power's off. I'm not going to unplug it this time. I'm going to throw caution to the wind a little bit. All right, so let's move this into position, okay? Now let's kind of zoom in here so you can kind of see what's going on. All right, we're not messing with this. Here is where the DC, here's where the AC goes in, right there. Let me point, my fingers are kind of getting in the way. So this is where we need to put our AC in. You can see it says AC. So that's where we're going to put our AC in from our transformer, okay? Simple as that. So let's get our transformer, and if we take the 2 red leads, that'll give us 12 volts. If we just take one of these, that'll get us 6 volts. Now, why not put these in parallel? Can't we put these in parallel, the 2 reds? No, we can't, because they're out of phase 180 degrees. That's why we would need 4 leads to put them in parallel. So right now, they're out of phase, so you can only use one of them, all right? So it doesn't matter the polarity of this. There's no sense of ground or plus. They're just relative to each other. Okay, so now I'm going to put the transformer on this metal here. I'm going to move this here. So there's some metal here, and I'm just going to kind of set it on that. I'm going to get this so you can see, and then we're going to leave that like that. Okay, so now, and let's zoom out a little bit here. Let's zoom out a little bit so you can see the board. Okay, so what do we got? So we got our transformer, we got our AC. We're going to get about 8 volts out of here, right? Unloaded. It's supposed to be 6.3 if it's loaded. It'll start up at about 8 volts. That'll get our regulators going. Now, let's take our multimeter. So I'm going to move these cables out of our way a little bit. Everything's always in the way. Never fails. All right, so don't get frustrated. Everything is always in the way. Okay, So I've got my multimeter here, all right, and there's never enough room, so you got to take your time. I'm going to plug it into our little sensing socket here. There we go. So our multimeter, and make sure I put it back to DC because I want to measure the voltages. So the top rail should go at, what should it go at? This is 3.3 and this rail is going to be 5 volts, right? Okay, so it all looks good. So what do we got? We got AC, low voltage coming into the center. It's going to be bridge rectified by this bridge rectifier. We're going to get plus and minus out of that. That's going to be smoothed by this big capacitor here, 4,700 microfarad, right? And notice it's only 16 volts. So if we use this transformer and we did the series configuration, we would definitely blow that capacitor or overheat it. Now, we got this wire. Hold on here. I want you to see this. I got this wire hanging out here. I don't like that. So I'm just going to put it right here. It goes nowhere. It's just safe and in a column here that we're not using. Okay, so just remember that. All right, I look at it. Everything looks good. Okay. I'm happy with it. Now I'm going to go and turn the power back on, and we should get both our regulators. There we go. Power's on. Notice we got our LEDs on here. So that's our 3.3, and here's our 5. Let's check. So the top rail is 3.3, and sure enough it is. Okay. The bottom rail is supposed to be 5. And sure enough, it is. Okay, now let's try some of our experiments with our loads, right? And see if any weird things happen there. So we got our 5 rail, and let me put this so you can see it. So we got our 5 rail, and as a matter of fact, I'm going to zoom out again. Zooming out. Okay, give myself a little bit of room here, and put this right here. All right, and I think you can see that. Yeah, you can see that, and I got some glare. Okay, never happy with the way anything fits, I'll tell you that right now. Okay, there we go. So we got our 5 volts right there. So let's put a load on the 5 volt rail. So let's get our 33 ohm resistor. All right, so I've got our 33 ohm resistor, which is orange, orange, black, right? And I'm going to plug this in real time into the 5 rail. Now watch that. So if you take 5 divided by 33, it's what, 150 milliamps. So watch this. So see, this voltage it's fluctuating by itself a little bit, right? Just because the inaccuracy of the meter. So watch when I plug this in to the rail here, and I just plug it right into the rail, plus to minus, and we dropped 0.01 volt. That was it. And now we'll do the same thing on the 3.3 rail. So let's go ahead, and that got hot that quick. It's hot in my fingers, I can feel it. So we got 3.3 and some change, and now I'm going to plug this in, and there we go. We barely changed it all, okay? Very, very nice. Now, something else I want you to look at. So what do we got? We got our transformer, we got our AC, we got our bridge rectifier, we got our smoothing capacitor, we got our 5 volt regulator, we got a 3.3 volt regulator, we got smoothing, we've got noise capacitors, we've got these things all hooked up. It's a decent power supply, right? We could use this. A little more cleanup and stuff, we could use this. Now I want to do something. What I want you to see is I want you to see what the actual lines look like, okay? The DC lines. So what we're going to do is we're going to take our oscilloscope, and we're going to plug it into the 5 and 3 volt line. So we're going to do this right now. So we're going to hook this into the 5 and 3 volt line. All right. So what I'm going to do is I'm going to get a couple posts here. So I'm putting posts into the board so that I can get these signals out. A lot of ways to do it, but we'll do it like this. All right, so now we've got a post for ground, we got one for 5, we've got one for 3.3. Okay, so I'm going to zoom back in here for you a little bit, zooming in. All right, so you can kind of see what's going on here. All right, I'll turn this up sideways, and there's our post, ground, 5, 3.3, and 5. All right, now what I'm going to do is I'm going to actually put the oscilloscope on this, and we're going to look at DC. So you're like, well, why would we look at DC on an oscilloscope? Well, because there's noise riding on the DC, okay? So here's channel 2. So I'm going to put channel 2 on the 3.3. So that's going to be the smaller voltage. And then channel 1 will be the bigger voltage, all right? The 5 volt supply, which is the bottom supply. Okay, so now I want you to go over, and we're going to look at the zoomed in camera here, which is on the oscilloscope. So here's channel 1, so that's our 5 volt signal. All right, and here's channel 2, which is our 3.3 volt signal. Now, let me show you something here. I'm going to go channel 1 and I'm going to put this on DC coupling. All right, then I'm going to go to channel 2 and I'm going to put this on DC coupling to prove, in fact, that these voltages are right. Now, see, this is at 5 volts and 5 volts per division, so I'm going to put it at 2 volts per division and 2 volts per division. Scroll this down a little, scroll this down. All right, so now you see at 2 volts per division, the yellow trace is 1, 2.5 divisions. That's 5 volts. The blue trace is 1, 1, and a little bit more here, almost 2, and that's at 3.3 volts. So that's correct. So we're getting this DC out. But I want to bring your attention to the lines. See those lines? They look flat, yeah? So now let's measure AC. So now what we're going to do is we're going to get rid of the DC component. So we get rid of the DC component like that. We get rid of the DC component like that. So now we're just seeing the AC modulation of the DC. So we're seeing the AC that's riding on the DC, or the noise. Now, watch this. So we've got 2 volts per division and 2 volts per division. Well, let's change that. Let's go 1 volt. Let's go 500 millivolts, 200 millivolts, 100 millivolts. Okay, 100 millivolts. So now you see what we're seeing here? You see that stuff moving up and down? That is the noise on those DC lines. All right, so even though this line is representing 5 volts and this one's 3.3, there's a teeny tiny bit of noise, and we can zoom into this, right? This is 100 millivolts per vertical division. So at any time you can see there's some noise here, right? And it looks like it's about, half of a division, or 50 millivolts. Well, we can go even higher. I can go 50 millivolts, 50 millivolts. Now you can start to really see it. And we can see that this noise is pretty high frequency, so I can change this sweep rate like this, okay? And now watch this. As I can sweep at these different sweep rates until we can kind of see the noise good. There we go. So there's the noise that we're seeing. All right, so there's some noise on there, and this is 50 millivolts, 50 millivolts, and so we've got about 100 millivolts of noise in the worst case here. All right. So is that tolerable? Well, it depends what kind of electronics we're dealing with. So say we're doing stuff where we're amplifying things thousands of times and we have millivolt signals, that's not gonna work for us, because if we're trying to amplify millivolt signals and our power supplies are modulating all over the place like this, that noise, we won't be able to differentiate it. So that's why filtering of these power supplies is very, very important. And we can add more capacitors, we can add inductors and things like that. And we'll talk a little about that when we go back to the blackboard on the computer. But I just wanted you to see some of this noise. Now, what I want to do now is let's slow this back down here. All right, so we can kind of see the noise in these kind of impulses. And we're going to lower the we're going to change it to 100 millivolts. And now what we're going to do is we're going to put a load in here, and we're going to switch the load in and out of just the 100 of the 5.5 volt line. All right, so we're going to put our switch. Remember, we had our switch with our load. So I'm going to get our 33 ohm resistor. I'm going to get a switch, and then with a push of a button, we're going to put that load into the system. All right, so let me put that together now. Okay, so we've got power here on this rail. I'm just going to move this probe down here. All right, so here's our 33. So we're going to put our 33. As a matter of fact, let's do this. We'll put our 33 to ground, like that. All right. Then we're going to put our switch right here, just like this. Good. And then we need a wire to close the circuit back to +5. So we'll put that right in there. All right. Now, I'm doing this hot. It's low voltage, so I'm okay. But it's not easy to work with these gloves, and you want to be careful. So ideally turn the thing off and then do it. But again, we're always against time. Okay, so now when I press this button, we're going to see some noise generated on the oscilloscope. So I'm going to press the button here, and as I do that, we're going to watch the oscilloscope. Okay, so take a look at the oscilloscope. Take a look at the yellow trace. The yellow trace is the one we're interested in. I'm just going to turn off the blue trace for now, just so you can focus on the yellow trace. All right, and I'm going to change it back to 50 millivolts per vertical division. All right, And so now what we're trying to do here is we're trying to see noise. Okay, so we're trying to see the noise. So here I go. So I'm going to start pressing the button. Press, 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 press. Something is happening there, right? So let me change this. All right, press, 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 press. Okay, do you see those little events? Let me scale it up a little bit more, and let me change its speed a little bit more. So that's just the standard noise on the DC line that's writing on it. So you can see it 20 millivolts per division. And again, we're pulling 150. So do you see that little spike right there every time? Right there, right there, right there. You can see those. That's me pressing the button. So when that button press happens, right, and I can just sit here and do it, right? And as a matter of fact, what I'm going to do is I'm going to stop there. So here's one here, here's one here. So when I pull that 150 milliamps, just for a fraction of a second, so we're at 8 milliseconds per division in time. So, for a few milliseconds, maybe 10 milliseconds, we're getting a little bit, see how the voltage jumps up and then it jumps down and then it adjusts and then it kind of stabilizes again. So that's it adapting to the load. That is the voltage regulator. So coming back here, that's that voltage regulator adapting to the load, and it adapts pretty quick, right? And so it's okay, all right? So that's good. Now, if we can do the same thing with the 3.3, but it's going to do the same kind of thing, right? And so again, that is what we were calling the load regulation, but now we're looking at it with a fine-tooth comb. We're looking at it on the oscilloscope, so there's no lies. We're not just looking at it with the multimeter, which is kind of averaging this out and giving us a blurry number. We're looking at it in real time, and we can see it's not bad at all. So let me turn this back on. So that's just the standard noise on it, right? And there's a number of things causing that noise. So that's not bad at all. And then, there's me putting that load in. So very, very small. And if we take this from 20 millivolts and we put it to 100 millivolts, 200 millivolts, you probably won't even notice it. You can barely notice those little discontinuities if we're looking at this at 200 millivolts. So if we do a design and we say, hey, we can tolerate plus or minus 200 millivolts of noise on the DC lines, oh, we're totally fine. Then if we say we can tolerate 100 millivolts, we're still fine. And then if we say 50 millivolts, now we're getting to that point where this little discontinuity is probably around 50 millivolts. That might cause us to have a problem. And then if we put it to 20 millivolts, we can see that just our noise is around 50, and we can definitely see these peaks sometimes exceed 50 millivolts if you were to measure them. All right, and I'm going to stop pushing the button and let it flatten back out. Okay, now, so that is using the transformer. All right, the separate transformer. So now what we're going to do is we're going to remove this big transformer we have here. So let me zoom back out here, see what I'm talking about again. So remember, we got our big transformer right here. So what we're going to do is we're going to turn the power off. We're going to unplug everything. We're going to switch to the printed circuit board version, which I'm going to plug into this board, and I'm going to do that kind of offline and just get it in there and adjust it and all that, because it's a little bit scary and dangerous. I want to make sure it's okay. Then we're going to come back with a cleaner, so that'll be a little bit cleaner. Then instead of having all these wires, we'll just have something plugged in nice here, and we don't have this big dangling power supply, which I'm not too thrilled about having next to me here. And then we're going to do some more experiments, but instead of doing this simple little resistive load, right, this little boring resistive load, we are going to play with some motors. So I've got some motors here. Let me show them to you real quick. And these motors, all right, so take a look at that. This is a pump. This is a pump motor, and this thing pulls a lot of current. It's a big inductive load, right? So there's one there, and then I've got a nice bag here of some more. These are all pump motors, and they say right on them what they are. And this one here is a 3 volts DC, and it pulls half an amp, 460 milliamps. And these are from Smart Motors, I believe, Smart Pumps. These motors, can you believe this? They're $80 each. $80, because they don't sell that many of them. All right, and you can find them on eBay for like $8. Anyway, we're going to play with some motors. We're just going to use these pump motors as an inductive load, and I'm going to show you what an inductive load does to these power rails. It makes it go crazy, cuckoo for Cocoa Puffs. And then what can we do to kind of fix that? So let's stop here. Let's do this in kind of the little chunks here, and let's come back, and then we will switch the transformer out, and we will play with some inductive loads. Okay, so I'll see you in the next lecture. Okay, welcome back. And if you take a look at the screen here, we're doing the next lecture. We stopped on the last one. It was a kind of a good stopping point. We had our transformer. So we had kind of the standalone or open frame transformer that we had plugged into our system. And then we decided we're going to switch that to a PCB transformer that could solder into a PCB. And one of those looked like this right here. Hopefully you can see that. There we go. So we're going to use that Tamura part, which is already in the circuit. All right. So now what we're going to do is we're going to look at that, and we are now going to experiment around with inductive loads, a motor. And so what this lecture is going to be about, which is a lot of fun, is so say you design something and you've got a digital power supply. You got a couple of them like the 7805 and this MC33269. So you got 5 volts, you got 3.3 volts, and you decide to hook a motor up to one of these supplies. All right. So it seems reasonable, but then all of a sudden you hook it up to the supply, and maybe you've got the motor hooked up to the 5-volt supply or the 3.3-volt supply, and then maybe you've got your digital electronics to the 5 or the 3.3. Either way, the motor turns on, and then over a period of time, the processor keeps locking up, or the digital electronics fail. And the reason why is because you're inducing noise, that inductive load, that motor. As that motor is turning around, it's generating all kinds of noise and back EMF, which then gets pumped back into the voltage supply mains and dirties up everything. And those spikes can cause the processor to fail or the electronics to do something wrong. So what we're going to look at is how to clean that up. So we're going to analyze it on the oscilloscope. This is a lot of fun. And what our goal is when we're done, is when we turn that motor on and power it up, power it down really, really quick, rapidly, the power supplies stay nice and clean, or as clean as they can be. All right. So that's kind of what we're going to experiment on. Okay. So let's go directly to the bench and just get right into it and go from there. And we're just going to, in real time, kind of play with these different components and see what we can do to create noise and then get rid of noise. And we'll go back to the blackboard here and kind of show where we would add these components and so forth. All right. So I'll meet you at the bench. All right. And so as you can see, I've already plugged in this Tamura transformer. So because it's a little bit tricky to connect and push in there, I already did it and kind of made sure everything was good. So just to reiterate what we're doing here. So we've got AC is coming in here off this line right here, which this, let me show you this. So this is basically connected to our AC lines, and everything's off and unplugged. That's why I don't have gloves on right now. So this is our AC line coming in, and then I've made this cable. This is 14 gauge stranded wire, very, very good wire, and then brought that in, and then those AC lines go directly into the primary of this Tamura, right? And then I've got the primaries in parallel, and we've got it in the 115 voltage mode, 115 volts. Then the output, I've got the outputs in parallel as well, and I've got them connected under the transformers, so you can't really see them. And then the AC output, which is in this case going to be 6.3 volts, is then going to our bridge rectifier, and everything else is the same from there. All right. Now, some other stuff that I want you to look at is this. So I've kind of fabricated this cable here that you see, and this plugs in our AC lines here. Now, if this wire pops out while I'm doing something, I could possibly get touched here and hit my wrist or something like that. So what I wanted to show you, and again, you know, building things is all about fabrication, and you got to fabricate things cleanly and all that. So I wanted to show you some stuff here. So these little cable management clips, they come in all kinds of different sizes. And so what these do is basically they hold cables in place. So this one right here is a little bit too small to hold this cable, but this one will do. So the whole thing is I could just use a piece of tape, and I could just tape this down here like that. I could do that, right? But you know, the tape is, you know, not very reliable. So maybe I'll do some cable management. This is an AC line. I don't want to get shocked. So what I'm going to do is I'm just going to pull this double-sided tape off the back here. Throw that away, and then I'm going to kind of place this where I think would be a good position, maybe right about here. All right, push it down, and then I'm going to put this cable in here, and I am going to pinch it down in there. So now what's nice is this cable is nicely and cleanly tucked away here. It's managed. You know, this is not going to come up into me, and then these hot AC lines, which over here in the corner of the camera, are going to stay where they're going to stay, which is what we want. All right. So just a little trick there. Don't be afraid to put some cable management when you're doing these experiments to keep your wires away and all that. You can tape them or do these. Now, obviously, this is going to be really hard to get off of here, but you know, I'll probably use that again. So that's fine. I'll leave that there. All right. So let me get rid of these. Okay. So we've got our transformer here. And again, what I've done here is I put our probe leads for our oscilloscope. Here's the 3.3 volt supply, and here's the 5 volt supply on channel 1 and channel 2, so we can look at those voltages. So I got that. And then what else do we have here? Anything else interesting? Oh yeah. So here's the really cool thing that we're going to play with is, you know, I showed you some motors. And so these are a couple pump motors. And let's zoom in a little bit and let's take a look at these. So I don't have to bring them up to the camera. I can bring the camera down so that we can see things. Okay, so here's one of these pump motors right here, and hopefully you can see that. Yeah, I think you can. And so this is a micro air pump AP2P01 from Smart Pumps Inc. 3 volts DC at 480 milliamperes. All right, 480, or is it 460? 460 milliamperes, 3 volts. So we only need 3 volts to drive this, but it's going to pull a lot of current. I mean, 460 milliamps, that's half an amp. But if you recall, our 3.3 supply can go up to 800 milliamperes. But our 5 volt supply, I believe, goes up to 500 milliamperes. All right, now, so, and then I've got another motor. And this one right here is, I believe this is not from the same company. And this one does not say what the voltage is on here, but it's roughly the same. It's a 3 volt supply, and this one probably pulls about 300 milliamperes, all right? So, but it'll run faster because it's smaller, right? So, okay, so the whole thing is these motors, as they run, are going to create a cyclic noise, all right? Because they're an inductive load. You're powering up an inductor, you're creating a magnetic field, the magnetic field's collapsing. That's what a motor does, right? And so we're going to have this noise generated, right? So the first thing that I want to do is I want to turn on the system, and I want to make sure the thing works, okay? So I'm going to go ahead and I'm going to plug this in. And because I'm going to be working and trying to get these components in here, I'm not going to put the gloves on, but the AC is over there pretty safe, and it's out of the way. So I'm not going to touch that, and I'm not going to get near these hot leads, all right? So I'm just going to be careful, but it would be better to wear the gloves, but it's just too hard to get parts in here. All right, so I'm going to go ahead and turn this on. And I turn it on, and we see we've got both of our supplies, the 3.3 and the 5 volt supply are good to go. All right, and so now we've got our system here, and so let's start doing a couple things. So let's confirm stuff. So the first thing that I want to do is, why don't we get one of our little probes, and I'm going to get our multimeter. And the first thing we're going to do is we're going to measure our voltages here, and we're going to see if everything is what we think it is. And we already know it is, but so I've got the multimeter here. And this gets really, really tough because you got cables everywhere, you got parts everywhere, and things just get smushed and crunched and slid off, and it's tough. So just bear with me here. But I like you to see things in real time. So I'm just going to go right here, and we're going to put this up here. And we're going to look at the 3.3 volt line. All right, so I plug that into the 3.3 volt line, and let's see if you can see that meter. There it is, 3.3. Okay, good. Let's do the 5 volt line. It's right under here. Put that in there. Okay, push that in. Looks good. Let me show it to you. 5 volts. Okay, and then over here on the left, I've got this line right here. And this is looking at the DC that's coming directly in from our wall transformer here, our bridge rectifier, and our smoothing capacitor, because I want to monitor that voltage there. And that's the only voltage we're going to monitor right now with the multimeter. So I'm going to kind of try and get this out of the way here so I can see it. And the reason why we want to see that is as we pull current from that transformer, that voltage is going to keep dropping and dropping and dropping. Now, remember that the 7805 requires a 2 volt voltage above the regulation voltage. So it requires 7 volts to maintain regulation. Remember that? At high current or whatever. So as we drop voltage by pulling current from the transformer here to power this 3.3 volt supply, we're going to start messing up the 5 volts, all right? So it is going to start having trouble regulating. So that's one little thing to note there. Okay, so here we go. Let's have some fun. So what we're going to do is we are just going to connect a motor to this little switch right here. So I've got plus 3.3 coming into the switch, and then right from the switch, I'm going to take that 3.3, and then I'm going to connect another wire here to ground. So now this motor is basically going to get powered when I press this button. Okay, so let's see if it is. And it's a pump, so it pushes or it pulls. It's pushing. All right, so that's a pump, and it's very high frequency, very high RPM. All right, now let me put the other one in so you can see the difference. Here's the other one, same thing. These are color coded for polarity. So red is plus and there's minus. Okay, here we go. Here's this one. Much slower, right? Okay. All right, so let's go back to the fast one because it's more noisy. Okay, so we got this noisy motor. All right, so that's great. You hook that up and you're making some piece of hardware and you got a motor in there and everything's great. The 3.3 is also powering some digital electronics, and the 5 is, all right? And so you got the motor in there, you turn the motor on and something goes wrong. What goes wrong? So let's go take a look at the oscilloscope. All right, so over here on the oscilloscope, we've got channel 1, and let's turn on channel 2. All right, and the first thing I want to do is let's make sure both of these are on DC coupling. So we want to see DC on both of these, and then we got to change the vertical gain here so that we're 2 volts on the 5 volt supply. So it's 2 volts per division on the 5 volt supply. So you can see here's ground and then 1, 2.5 divisions. So there's our 5 volts. And let's get rid of that display. But our 3.3 is off the screen. So let's drop this down. There it is. So there's our 3.3. And it's 1 volt per vertical division. So 1, 2, 3, and about 3.5. So that looks good. So we're seeing the DC signals, which are staying there, and then you see this little noise on here. This is little AC noise riding on top of the DC signal. Okay, so now the question is, what happens if I turn that motor on? So I want you to think about it for a second. What do we think is going to happen here? So this motor is going to generate a lot of inductive noise on that 3.3 line. All right, so let's turn it on and see what happens. You see those little spikes on the yellow line? That's the 3.3 volt. And then look at the 5 volt line. See how it's wavering? We're not getting noise too much on the 5 volt line, right? We're not seeing that noise. All right, and this is the noise I'm talking about, these spikes. All right, we're not getting noise on the 5 volt, but we're seeing some wavering. So something's happening there. So let's speed this up. And again, this is going to be noisy. So what I'm going to do is maybe I'll cover this a little bit in something. All right, so now I'm going to change its frequency. And, okay, so now look at that 5 volt line. See that noise getting induced on there? So that's a waveform. That waveform is the motor waveform. So that is the motor cycling, and if we were to look at that frequency there, right, if we were to look at that, it would be the RPM rate of the motor. Now, here's another thing. Right when I power this thing up, the moment I power it up, I want you to watch both the signals. Watch how they dip and they gyrate. All right, look, did you see that? Look at the blue signal. See it dropping? All right, let me speed this up a little bit more. There we go. Or slow it down so you can see the event. There, look at that. So right when I power it up, boom. See that spike? Boom. All right, so the 5 volt for a second there really drops like a whole 2 volts, doesn't it? And then we just get constant noise on the 3.3 volt line, okay, which we do not like. All right, so first, what's going on with the 5 volt line? We're going to deal with that a little bit later, all right? But what I'm going to do now is I'm going to put the both traces in AC mode. So we're going to get rid of the DC offset. All right, there we go. So now all we're seeing is the AC signals. So the DC component is now gone, all right? And so now we'll just look at the noise on both of these signals here, okay? So now let's turn the motor on again, all right? So the 5-volt line has that sinusoidal noise on there, which you can't see because of the scale. So now what I'm going to do is I'm going to turn the scale way down to 200 millivolts and 200 millivolts. Okay, so now we're going to really start to see this noise, and you're going to be quite surprised. Okay, all right, so here we go. There we go. All right, so again, the 5-volt line is 200 millivolts per division, so I'm seeing about 400 millivolts of sinusoidal noise getting put on that. And I can, let me slow this down a little bit more. Now you can see, look at that. Wow. All right. And then we're getting noise, just pure random noise and spikes on the 3.3. All right, now there we go. And I want you to see this there. So the 5-volt line has got about 400 millivolts of sinusoidal noise, and that sounds like it's the motor itself, right? So that looks like that's the motor frequency that the RPM is going at, giving us that noise. So that's something's happening there. We're causing something to happen there. But we're getting all kinds of spiky inductive noise onto the 3.3 rail. Now, let's get rid of the second channel. Okay, so that's the 5-volt channel. Let's just turn that off. We don't need to look at that right now. Okay, let's focus on the 3.3. All right, so 3.3, here we go. Okay, wow, scary. Now let's change the scale here so we can see what's going on. All right, so now let's look, what kind of noise are we talking about? So we got 500 millivolts per division here, 500 millivolts. So every division is a volt. So if we go up and down, that's a whole volt. If we go up and down 2 of them, that's 2 volts, all right? So look at this noise. All right, now I'm going to stop this someplace in here, and we're just going to look at some of these. So look at some of these pulses. All right, so there's a pulse. That went up 1.5 volts. That went down, 7.75 volts. So we're talking about, 2 volts, maybe 3 volts up and down here of noise is getting modulated on that signal. And this is only a 3.3 volt supply. So we're spiking noise up and down, and the noise is going below ground. So the noise can go below ground. So this is really, 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 really bad. All right, so again, let's turn the oscilloscope on. Let's look at this noise. All right, so the question is, can we get rid of this noise? And there's more noise. This is continuous running, and then this is even worse when we fire this thing up. All right, so let's try and see. We can't really see it there, so we're gonna speed this up. And give me a second here. We'll put it about that. Now watch. Boom, boom. All right, so that's not too bad actually. But let's look at the DC. So let's also look at the DC here. I want to see this. There's the DC, and we're gonna. There we go. Okay. So now let's turn the motor on. Let's see what happens. So the AC noise is on top of it, but we got it at 1 volt, so we're not going to see it that well. But I want to see if there's DC we're losing here. Not too bad. So it looks like we're just getting AC noise on top of the line. All right. So let's go back to AC. Let's put this back so we can see it here. Okay, and all right, so there's our signal, all right, and there's our noise, and let's change the scan rate here, and let's change the scale so we can really see the noise. There's 200 millivolt scale, and you can see the noise is just horrible. All right, so can we get rid of this noise? Let's go back to the bench and let's see if we can add a couple parts here and fix this thing up, okay? So let's go, let's go back to the blackboard and try and see if we can add. What we really have here is this. This is what we have. So, and I'm just gonna draw it right here. So we've got 3.3 volts here coming in, and we got that 3.3 volts, and then we've got a switch, a momentary switch, right? So those, how do those look like? They look like this. And then that momentary switch is coming down here, and it's going into this motor here, all right? And that's a horrible motor. Let me make that motor better. Make it a little bit bigger so you can see it. Okay. So here's this motor right here that this is going into, whatever symbol, there's different symbols for motors. And this is going directly to ground, all right? We flip the switch, current flows, right? The motor runs, and then what's happening is, as this motor, which is generating the current's generating a magnetic field, it's switching, doing all this, it's inducing noise, back on the 3.3 volt rail and pushing this back into the system. Okay, so what we want to do is, can we smooth this out? All right, so let's try a couple things. So first, let's do this. So right now, one thing, the moment we turn this motor on, it pulls a lot of current to start up. So motors have what's called their initial startup current, and then after that the current decreases because it's already running, right? So there's inertia already. But when the motor's at rest, right, it wants to stay at rest, so it needs more current to get going. So that's kind of the starting current, and then there's the running current, all right? And where is it going to get that current from? Well, it's got to go all the way back to the regulator. So first thing we're going to do is we're going to think about putting a big capacitor here, a storage capacitor. So this thing is charged, so when we turn this motor on, it pulls it from this capacitor. So maybe we make this 2200 microfarad. Then let's do another thing. Right over the motor, right here to ground, let's put a small capacitor, let's say 0.1 microfarad. All right, and that's going to get rid of some of the noise also that's being generated. So we're going to put this big capacitor here, and we'll put this little capacitor right here. Then let's turn the motor on. Let's see what kind of noise we get. All right, so let's go actually put those parts in and see what happens. All right, so we're back here on the bench, and what we're going to do is we're just going to do exactly what we just said that we were going to kind of model here. All right, so here's the motor where the motor leads are, right? So what I'm going to do, first I'm going to put that 0.1 microfarad right across those motor leads, all right? So here is a 0.1 microfarad. And another thing I did, I've turned off the power here because as I'm moving my arm around, I don't want to touch the AC line. So here's a 0.1 microfarad. I'm going to put that right across our little power lead here. And this is all going to get a little bit small. There's not a whole lot of room here. All right, so I'll move the switch here like this for a second, and I'm going to put this right across here. Okay, good. Okay, and then here's the 3.3 feeder line that feeds the switch. So what I'm saying is, let's put a capacitor right here to ground so that when we feed, we don't have to go back through the rail all the way back to the regulator. We'll have a big 2200 microfarad to give us that initial startup current. Okay, so let's look here, and I think, yep, so this one is a 2200 microfarad 10 volt. 10 volts, okay, we're running at 3.3 volt, but those spikes are pretty high, got to be careful, but they're smaller than 10. All right, this is polarized, so we're going to put ground to here, and let's see, we're going to have to bend this down a little bit, so we can kind of get this in here. So we're going to go ground to here. All right, there we go. I don't know if you just saw that LED flash for a second, because there was some charge on there, because I was experimenting, obviously. Okay, so now we've added our two things in here. So we got a big capacitor for our startup current to get this thing going. Then once it's rolling, we're going to basically have a noise filter, this little 0.1 microfarad, which is going to filter the noise, hopefully, and we're going to get some better results. Okay, so let's go ahead, let's turn this thing on. All right, okay, good, it's on. All right, let's go ahead and let's press this power button, make sure it works. Okay, it's working. Okay, great. Now I want you to look at the oscilloscope, all right, and check this out. Okay, so we're at the oscilloscope here, and we're at 200 millivolts per division, okay? Let's go ahead and let's put that down to 100 millivolts. So let's really look at that noise. So there's nothing happening, and we can see there's a little teeny tiny bit of noise, but we got it at 100. So we're really gonna scale and see any noise that we're generating, all right? So I'm gonna turn the motor on and let it run in continuous mode. All right, now look how small our noise went down to. All right, so basically we're getting 25 millivolt spikes, if that. So now if I put it back down to 200 millivolts that we're looking at it before, we're not getting those big spikes anymore. They're gone. All right, now let's pulse this thing on and off, and let's see if we can get some big spikes that way. But now that big storage capacitor is going to save us. So here we go. All right, so look at that. We're still getting nice performance there, and you see that little dip a second every time we turn it on, right? It's dipping just a couple hundred millivolts, but it's getting that current it's getting that charge from that capacitor, and then we got almost no noise, all right? Very, very little. So we could go, and let's look at this. Let's go to 50 millivolts. Now just sitting here, just the ambient noise. Now here's one little thing. Electronics in general, they generate just picking stuff up like 20 to 50 millivolts of noise. It's like you can't get rid of noise. So the noise that you're seeing right here is just a function of there's wires hanging out everywhere, these cables, this and that. It's almost impossible to get rid of that. So just keep that in mind. Now, here we go. I'm going to turn it on and let it continuous mode. And the amplitude, I'm seeing some spikes right now, probably 25 millivolts up and down. And now we'll hold that on. And now we can see the envelope, we're staying within a good plus and minus 50 millivolts. No more volts. Remember before we're like at a volt and a half. So we're at 50 millivolts now. And again, if I hit it and spike it, all right, we get that little spike there. That was 50 millivolts. And again, everything looks bad zoomed in, but we'll zoom out of this just a little bit. All right, there. There's like 1 volt scale. And now you can't even see it, right? So as we zoom in, 200 millivolt scale, you see a teeny tiny bit of noise. Let's get that noise so that we can see it a little bit better. We'll put it at 50 millivolts. All right, there we go. Let's go ahead, let's switch motors. So does our solution, we decide, hey, let's switch motors to this bigger motor. It's a little bit slower, and how does that look? So let's do that. And I'm going to switch this motor and get it in here. There we go. All right, here we go. Look at that. Barely anything out of that motor. So there's motor not on, there's motor on. Nothing. Looks great. Okay, so let's go back to the other motor because it's more noisy and we want a noisy source. Okay. All right. So let's go back to this other motor. Let's plug it in here. Okay. All right. Okay, so it looks like we've got the noise down to 50 millivolts plus and minus, and a couple times there it gets a little bit higher. All right, can we do better? Is there anything else we can do? All right, so again, we can keep working with capacitors and doing this and doing that. There's other things you can do, but let's go back to the blackboard on the computer here, and I'll show you something else we can add. Okay, so we're back here on the computer, and so there's something else we can do. So let's just erase some stuff up here to give ourselves some room. We don't need all this anymore, do we? All right, and matter of fact, we don't need this. Let's get rid of all this. Just give ourselves a little bit of room here. I'll keep all the circuitry so we can refer to it. Okay, so here's an inductor L, right? Now, what was the inductive reactance? Remember that? So what was the inductive reactance? So X sub L, what was that? Do you remember? It was 2 pi FL. And remember what X sub C was? If we had that, it would be 1 over 2 pi FC. Okay? But we don't need that. We just need this one. So this says that its impedance goes up proportional to the frequency. So remember, an inductor is basically a frequency-dependent resistor. So the higher the frequency, the more resistance or impedance, right? So we are trying to get rid of high-frequency noise. That noise is very high frequency. So what if we put an inductor in line with the power? So let's take a look over here. So our power's coming in through the 3.3 rail right here, right? So why don't we try this? So right where it's coming in, let's so here's the power coming in right here. Let's put an inductor right here. All right, and then this point right here will be 3.3 volts. So we're going to put an inductor L here. And so now what's going to happen is this inductor for DC, it's just going to pass it, but for AC, it's going to impede it. All right, so what's nice is that as this motor generates noise and it puts that noise, let's draw that noise here. So here comes this noise and it's all noisy coming through the system, right? And it gets to that inductor, and as a matter of fact, let's draw it bigger. Here's this noise, and it's happy, it hits that inductor, impedance, and that noise gets smaller. All right, so this right here, we could use like a 1 microhenry, a 2 microhenry. We could do math and we could model this, and we know how to do this. We know how to do complex impedance and compute for various frequencies, what the impedance is and so forth and all that. And we could do a bunch of calculations, but when you do real electronics, that is extremely time consuming. Now you can model it in the computer with simulation, but instead what you do is you use intuition a lot, and that's what you want to get here. You want to get some intuition, right? Just like when you fix a car, you're going to bolt something on, right? You take off the tires, take off the lug nuts, right? And you kind of have this feel for how much torque you need to apply those lug nuts to put that tire back on and keep that tire from falling off, right? You don't go get a torque wrench. I don't think anyone has ever got a torque wrench other than Indy pit crews to check how much torque they're putting on things. And they just use a tool that when it hits the right torque, it stops turning it, all right? Those impact wrenches, all right? Impact drivers. So same thing here. Let's use intuition. So what we want is we're going to use what's called a ferrite bead. And I told you about these before. And ferrite beads are inductors. All right, they've got a little piece of ferrite and they've got wire and they've got some coils through it. And they're an inductor. And they have different sizes and they're spec'd at like maybe at 1 megahertz, they're a 1 kilo ohm of resistance. All right. And we know that noise is pretty fast. All right. So it's up there in kilohertz and megahertz range, that noise that we're inducing. And so we're just going to put off the shelf little ferrite bead that I have a couple of right where we're looking at it right here, right into the feeder of this whole system, and we're going to see if that helps. So that's the first thing that we're going to do. And then there's one more idea we can try to get even less noise out, all right? But first let's try this. So let's go put a ferrite bead in here and see how that helps. All right, we're back here on the bench, and I've got a couple of ferrite beads, and here they are here. Here's what they look like. So that's ferrite, which is, it's basically, you know, powdered iron, right? And then there's some wires. So we can get the camera to cooperate. There's some wires, okay, and that's it. And they're coiled in. Let's look at this on the zoom camera. All right, and let me see if it'll focus for us. Let me see if I can get it to focus. And it's not going to cooperate. It just likes that image in the back too much. Oh, there we go. So you can see. So see that? So it's coiled through there. Looks like 3 times. All right. So that's a ferrite bead. That's a big one. Then I got another one right here, and that's a real simple one. So it just has that ferrite going right around it. So obviously the other one's got more inductance, okay? All right, so let's go ahead and let's put this ferrite bead into the power lane there, all right? So I'm gonna turn this off, system's off. Now look at that, what's happening there? Oh, we had a bunch of charge inside that capacitor. That's why you saw that slow decrease. All right, so we wanna put this right in front of everything. So I want everything to go in through that ferrite bead. So we got to be careful here. So we're going to pull this down so we can see it a little bit better. All right. So I'm just going to kind of undo this a little bit and see what I'm doing here. All right. So let's do this. So what we're going to do is we're going to pull this out, and we are going to put the ferrite bead right here like this. All right, and then that's going to give us trouble. So I'm going to try, what I'm going to try and do is I'm going to put the ferrite bead right here. I don't want to bend it or break it. Okay, so there's a ferrite bead right there. Now what I'm going to do is I'm going to connect power to the ferrite bead right here. So there's our 3-3 going through the ferrite bead because the ferrite bead is just too flimsy. Okay, all right. And so here's power going to the ferrite bead. Now I want to put the capacitor. I don't want to put it upstream. I could put it upstream, but we're not trying that. Let's put it downstream here. All right, so we're going to put it here. So here's ground, and then the other end of this is right here. Okay, make sure everything is good. Okay, so power goes into the ferrite bead, and then the capacitor as well. Capacitor charges to ground, and then when we flip the switch, we turn the system on. All right, let's connect our motor again. Let's get our small motor. All right, tricky. We get our small motor here and make sure it's the correct polarity. And I'm going to put the motor right here. All right, and we still got our capacitor there. And remember, that's only one capacitor, that 0.1 microfarad, and that's one big frequency band of noise it's taking care of. We could try a 0.01, we could try a 0.001, we could try a 1 microfarad, right? We could play around, and you know you do. If you're going to do this professionally, you're going to sit here a couple hours, try things out, model it on the computer and all that, but these are some good tricks to try that should work. All right, and they already did. Okay, so I just turned the system on. You can see the lights are on. All right, so again, take a look at the oscilloscope. So this is just standard noise on that line. We're not even doing anything, and we're getting, you know, 25 millivolts of noise in each direction. Okay, so we're already getting that noise. Now, here we go. So we're going to try turning this on. We're going to see if this helps a little bit. Now, we don't have anything to compare to right now, unfortunately. We just have to remember kind of what it was, but I remember, so I'll let you know. All right, so here we go. Wow, so look at that. So almost nothing. Every now and then I see a little spike. Every now and then I see a little spike, a couple big ones, but that's pretty good. Pretty good. All right, and then we could try switching the position of the ferrite bead and putting the capacitor, upstream. We could put the capacitor upstream here, so the capacitor is at the beginning of the ferrite bead, all right, instead of at the end of it. So let's give that a try, all right? So again, what I'm going to do is I'm going to power it down because the capacitor is going to be charged. I want to let it discharge. Okay, so it's discharged. So now what we're going to do is we're going to put the capacitor right here. So we don't have room here. So what I'm going to do is I'm going to have to move a couple things around. Being very careful here. I don't want to break this. This is just asking to be broken. All right. Okay. And then we're going to put our capacitor here right there. Okay. Now, capacitor and the ferrite bead. So the capacitor is upstream. Okay. So let's turn it on. Okay. Everything didn't explode, so we're good. All right. So I'm going to turn it on again, and we're going to look at our oscilloscope. So we look at the oscilloscope and nothing's on. You see the amount of noise, and now we turn it on. It's almost the same. Maybe a little spike once in a blue moon. So not much difference there, right? And again, if we lower the vertical division back down to 200 millivolts, you turn this on, it is clean as a whistle. Clean as a whistle. All right. Now let's finish off. Right now, I'm going to disconnect all this. So there it is. You can see it's very, very clean. All right. And then we get that little quick jump when it turns on sometimes. Very, very, very little noise. Okay. Very happy with that. Okay. So remember what that looks like. Now I'm going to turn it off, and we're going to really quick, we're going to pull this thing all apart. Okay. We're going to pull it apart. We're going to take this off. We're going to pull this capacitor out of here. All right. And then we're going to connect this thing up. We're going to put this like this. And because I just want you to see, I want you to remember. All right, and then here's plus, and here's ground. All right, ready? So now we got no filtering. Let's see what it looks like. And what did we do? What did we do? Well, we got to turn it on. Okay, here we go. Whoa! So we did indeed make a really nice filter system, and we cleaned that up. And that's great. That's what we want to do. All right. So now the problem with the 5 volt is we're pulling so much current. What we're doing is we're taking that regulator out of regulation. So we're just drawing too much current. Now, if we had a LDO, a low dropout regulator for the 5 volt, then we could look and see, are we inducing noise enough where the 5 volt supply is seeing noise, and then we could address that the same way we did this. We would put filters on it. We would put capacitor, we put inductor, and so forth. All right. Now, I want to go back to the computer, and I think we've got everything we wanted to do here. I think we did, a lot of cool stuff. So I think we're done here. Let's go to the computer, and I want to draw a couple things for you, a couple ideas that I want you to try when you're building power supplies, and to give them a try to reduce noise and just make good power supplies. All right. Oh, and one last thing that I want to talk about. We bring the power in. Let's get this on the screen here so you can see. So we bring the power in, and we'll draw this on the computer when we talk in a moment. But we've got the power coming in, through the AC line. All right. So if you make a real power supply and it's an AC power supply offline that plugs in, you are going to have a fuse here. And this is hot right now. Let's do this. I'm going to zoom out a little bit more here. All right. I'm going to zoom out. So here's the hot line right there in the corner. So well, these hot lines are going to come in here. We're going to have a fuse on this, some kind of fuse, right? And there's different kinds of fuses. They're what are called PTC, positive thermal coefficient, and when they break, they basically they get hot and then they melt and then they re-solidify. So they're really nice. And then there's little glass fuses, normal glass fuses you've probably seen. I don't think I have any here, but you're going to want to fuse that AC line. Now, if you're going to build AC power supplies that are offline with transformers and all that, there's a lot more you need to do. It's beyond the scope of this course right now. Maybe we'll do a scope on AC power supplies one of these days, but we'd want to put protection. We'd want to put those XY capacitors on there for filtering. We'd want to put a fuse and a bunch of other stuff. Now, let's assume that all this is from a wall adapter, something like that. So we don't mess with it. We just get a DC unregulated voltage, which we plug in to our regulators, all right? Even still, in those places, we can put fuses. We can put these what are called PTC fuses to protect things. Also, hey, what if there's a lightning strike or something and we get a big voltage spike coming through the transformer and all that? Well, we can put clamping diodes and what are called transient voltage suppressors, TVSs, V is in Victor, S is in Sam, T is in Terry, TVS, we can put those in front of those regulators as well. And I'll show you that when we go on the board. But what those do is clamp the voltage. So if we ever get a really high spike voltage because of a transient due to a lightning strike or something, it won't damage our power supply and, of course, damage our computer downstream that our power supply is powering, all right? So anyway, let's go back to the blackboard on the computer there, and let's look at some of these other things, and we're going to kind of wrap it up with that. So anyway, so that was a lot of fun. So I will meet you back at the computer. Okay, so we're back here on the computer, and the first thing is, all right, we got this. Let's just erase this, and let's kind of summarize what we're talking about here. So, let's do this. All right. So we've got a 3-pin regulator we've been talking about here. Here's our 3-pin regulator. All right, and we can draw that. Let's just draw that in a little bit of a different color here for fun. Here is our regulator, and we don't know what voltage this is regulating, right? It could be anything, but we'll just say it's like a 5-volt regulator. All right, and it could be just a standard linear regulator, or it could be an LDO. And I'm going to tell you I want you to use LDOs, okay? They're just better, more efficient, less heat, all that, and only a little bit more expensive. So you're going to use an LDO, and that means that we can probably maintain regulation if this thing is like 5.2 volts or 5.3 volts, but it surely doesn't need to be 7 or 8 volts or something like that. So the whole point is we can have that low dropout, okay? All right, so this is kind of what we're talking about. And over here, we've got our V in. And if this is a 5-volt, maybe this is, anywhere from 6 to 12 volts typically, right? And that's a wall wart. I don't know where that's coming from. It's coming from someplace, and it's DC. It's unregulated. Unregulated, all right? It's just DC. It's maybe a smoothing capacitor, a bridge rectifier, all that, but it's DC unregulated. Out here, we've got V out, and we've got 5 volts regulated. Right? It's regulated. That's the whole point. That's what this is, regulated. Okay? Okay, so that's kind of what we have. And then bare minimum, we want to have a couple capacitors here. All right? That's what the bare minimum is in many of these designs, and they say whatever they are. But what I'm telling you is I want to see, in general, I want to see like a 10 to 47 microfarad big one. I want to see a 10 to 47 microfarad big capacitor. Then I want to see also a smaller one for noise like this, and I want to see this is going to be 0.01 to 0.1 microfarad. You can play with that. And again, over here for noise, again, 0.01 to 0.1 microfarad. All right, so we got these 4 capacitors, all right, between V in and V out. All right. Now, what else do we want to put in here? So let's add some other stuff, okay? So the other thing that we're going to add here is this. We are going to add some ferrite beads, all right? And all kinds of analysis has been done, and this really helps. So we're going to put a ferrite bead there, and we're going to put a ferrite bead right there. So these are ferrite beads and ferrite bead. Okay, and here's our V out again. So now what these are going to do is these are going to reduce noise coming into the system, coming into the regulator, and then also, so whatever noise comes in is now going to get dampened by this ferrite bead, so that the output is going to be real clean. We're going to hit it again with another one, and moreover, if noise comes in this direction, right, this will dampen it, right, and then if it tries to get back through the regulator and back out here, because maybe here this is also going to another supply. So I want to make sure any noise getting injected into this is getting dampened, all right? So we'll put ferrite beads on both of them, all right? And so that's what we want to do there. Now, what are these other things that I was talking about? So I was talking about transient voltage suppressors and whatnot, right? Okay. So let's talk about what that is. So a TVS, transient voltage suppressor. So what that is, and we'll draw that in another color too. Let's just be colorful today. So right here on the input, we're going to put a TVS, and there are many, many of these. All right, and they basically are diodes that are put in this opposite direction here. And these diodes are very similar to Zener diodes, so they'll have this kind of symbol. And this is a TVS, all right? And so what does that stand for? It stands for transient voltage suppressor. All right, TVS. And so what this does is, so normally we're expecting 6 to 12 volts in here. We're all happy, right? We got our 6 to 12 volts, yada, yada, yada. Here it is. Then all of a sudden there's lightning strike. Lightning strike finds its way through everything, the transformers, the power strips and all that, and then it goes boom, goes crazy, right? And you got this big, transient voltage spike. This TVS is like a Zener diode, except this thing works in like nano or picoseconds. So it works super, super fast and shunts that voltage and clips it and clamps it so that your system doesn't see that. So it works super, super, super fast. This thing, an enormous amount of energy it can shunt for nanoseconds or picoseconds. So you put these TVSs on this input here to these DC lines, and that protects your entire system. So now it's kind of protected against voltage strikes and so forth, and transient voltage, right? Now, this isn't going to help you against shorts and overcurrent situations. So now, say down at this end, here's our V out, right? Let's say that, this thing is rated at, say it's rated at 1 amp, okay? And you put a resistance on here that's so low that we pull an amp out, then maybe try and pull 1.25 amps out, something like that, right? And so what's going to happen is very quickly this thing is going to overheat, right? And it's going to shut down. Now, a lot of these will have automatic shutdowns and that kind of thing, right? But if it doesn't react fast enough or it doesn't have that feature, and you were to short this, you could potentially very quickly pull, like 5 to 10 amps through this, or more, 20 amps, something like that, who knows. And so in that case, what we might want is we might want to have some protection on the input, right, so that we don't pull all that current through here, all right? And so basically, if whatever's connected over here, I don't want to drag so much current through it that I cause damage to that as well. So then what we can put over here is something else, right? We can put a little fuse, and let me do this here. So now we can put and go here, and we can put a little fuse, and these things have different symbols. These little things here, these little fuses, but PTC fuse, positive thermal coefficient. And so what this means is as more and more current runs through here, this thing gets hotter and hotter and hotter. And when a certain amount of current surges through it, it gets so hot it melts and opens up, and then no more current flows. Then it re-solidifies and allows the circuit to run. So if the circuit pulls too much current for too long, it basically shuts the thing down, all right, and opens up. And that event might be 100 milliseconds to 10 seconds. So you can get these in different currents and different time constants. So basically you can say, hey, you can pull 5 amps, but you better not pull it for more than a couple seconds. You pull it for 5 or 10 seconds, and then this PTC is shutting you down, and it'll shut it off, right? So here's kind of, one version of a pretty full-featured power supply. So assuming this was an LDO regulator, we've got nice filtering on the input, we got nice filtering on the output, we got some ferrite beads on the input and output, we got high noise, we got noise protection, we got a TVS for transient voltage, and we got a PTC fuse so that we don't pull too much current. Now you build this on a board, you put a switch on it, you put an indicator LED, you got yourself a decent power supply. And when you look at other people's power supplies, you'll see, hey, they won't have, let's use a different color here. They won't have these other capacitors for noise. And these capacitors will be very small, like 1 microfarad, right? They won't have these ferrite beads, right? They won't have this transient voltage suppression. They surely won't have this fuse. They'll basically have the bare minimum, just a couple caps, a regulator, and then, throw caution to the wind. That's not what you want to do. You want to build a little bit better stuff. And so here is how you want to do your linear and LDO regulators. And now, of course, these parts, you have to play with them and stuff and experiment and get some intuition. Again, we know how to model all this if we want to. We know the math now, right? But we don't really want to do all that. And you can also get on the bench and experiment. I took a motor, and maybe that's the exact motor I'm going to use in a product, right? So I sat there and I turned the thing on, boom, 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 and I look at the noise, and I put a couple parts in. I don't have any noise anymore, so I'm happy about that. So I'm done. Then I could go back and I could simulate it also if I wanted to. But anyway, so that's it. So that hopefully you had a lot of fun. And power supplies is an interest of mine. And it's always nice because if you know how to make a good power supply, then your hardware will work very well. And when transient events happen, motors, high current, etc., you're not going to mess everything else up because it's really hard to debug. Because if something happens from your power supply, you're like, you don't really know that it happens because it's a little transient event. And if you don't look and see those transient events, you might go look in the wrong direction and think your software is not working or firmware is not working, right? But really what's happening is your power supply is spiking all over the place and creating negative voltages, which tripped out your microcontroller and it went nuts, right? So anyway, so that's it. I think we're done with all this voltage regulation stuff. I'm pretty sure we are. So in the next lecture, we're going to swing back to transistors again. We're going to talk a little bit more about them. We already did a lot of material on them at the semiconductor level, and we did some experiments. We're just going to do a little bit more, just kind of go back to it again, and then after that, that'll wrap that up. All right. So anyway, I will see you in the next lecture, and that's it. Bye. All right, welcome back everybody, and we are on the next lecture. So let's see, what were we talking about last time? We were talking about power supply. So we did a lot of power supply stuff, and that was a lot of fun. So hopefully you enjoyed that. It was long, but now we know how to build power supplies. So now what we're going to do is we are going to talk about transistors again. Now we've already talked about transistors many lectures ago when we were doing the semiconductor theory discussions and material. We learned about how they worked at a semiconductor level, the PN, P and the NPN transistors. We actually did some experiments. We went onto the bench and built things. We primarily worked with switches though, transistor switches, and then we even did MOSFET switches as well. Now what we're going to do is, now that we have more material under our belts here, we're going to kind of swing back to transistors, and we're going to do more applications of transistors, especially with respect to amplifiers. Now, when we are going to build electronics, or when you build electronics, typically you're never going to use a transistor or a FET as an amplifier itself. You just wouldn't do it anymore. What you would do is use a thing called an op-amp, an operational amplifier. And an op-amp is a little black box. And inside the black box are many, many, many transistors and different components. And what it does is it creates an ideal amplifier, or close to ideal. So if you were to design your own transistor-based amplifier, by the time you got done, you would just have all kinds of components to compensate for this and compensate for that and this and that. And people got tired of doing that. And because we can put billions, if not trillions, of transistors on an IC now, we came up with these things called op-amps, or operational amplifiers, and they're just black boxes. And they allow you to amplify things, multiply, divide, subtract, and do all kinds of really interesting things with analog signals. So you use those, and they're so cheap. They're just a little bit more expensive than a transistor. So you can use those as building blocks for analog building blocks instead of trying to make your own amplifier. However, knowing how to build a very simple amplifier with a transistor is still useful if you have to do it or just understand how to do it. So what we're going to do is we're going to kind of look through the book here, and then we're going to do some Blackboard work. We're going to build some different models and whatnot, and then we're going to go to the bench. All right, so this all happened over a few lectures. All right, so let's just get right into it. Okay. So we're in, what are we in? Section 3.9, chapter 3.9, page 57 here of the of the book that goes with the class, which again is just a rough guideline, just something I'm giving you so you can go through it. There's many, many books you can read on this material, and I suggest you always have extra resources and references. All right, so let's kind of refresh our memories here. So we've got two different kinds of transistors. One is called an NPN, and the other is called a PNP. The NPN and PNP stand for nothing other than N-type and P-type material. All right, the symbols for the two different devices are here, NPN and PNP. And how you tell them apart is where this arrow is. So in the NPN, the arrow is pointing outward, and this is called the emitter. The other one is called the collector, and this one's called the base. And over here, same thing, base, collector, and emitter, except the emitter arrow is pointing inward. And this can be thought of as the direction that current flows, is one way to think of it. And so in the NPN transistor, we have a current that'll flow into the base to turn it on, and then current flows from the collector through the emitter down to ground. In the PNP, it's opposite. So one other thing is the NPN and PNP are just opposites. So if something is a plus voltage, it's a minus voltage. If current flows up, then it's going to flow down in the PNP or NPN respectively. All right, so in the PNP, to turn the transistor on, we make the base negative. All right, and then current flows from the emitter through the collector. All right, so it's backwards. So the bottom line is they're both the same, and if we understand one, we understand the other just by flipping voltages in directions of current. So we're going to talk about the NPN, and the reason why is it's more applicable to digital circuits. And the reason why is because when we apply a positive voltage to the base, it turns on, and we like that. That sounds digital rather than putting a negative voltage or a zero. All right, so the packaging for the transistor can be a myriad of things, right? There's all kinds of different packaging. One of the most common packages, which we've already looked at, is the TO92, which is shown here. And it's basically got a cylinder cut in half, and then it's got a flat side, and then there's three leads coming out of it, emitter, base, and collector. And they can either be in this orientation, emitter, base, collector, or they could be reversed, and it could be collector, base, emitter. And it doesn't matter if it's NPN or PNP, it's just where the manufacturer decided to put the leads. Now, 99.9999% of the time, I've never seen one that didn't, but the base is always in the middle. But the emitter or collector, relative to this flat spot on the transistor, could be reversed. And they can be reversed even from the same part manufacturer to manufacturer. So if you have say a 3904, which is an NPN transistor from Texas Instruments, and it's emitter base collector, Fairchild could have a 3904 where it's collector base emitter. So make sure you look at the data sheet. All right, look at the data sheet and confirm for the part you're using that emitter base collector is correct, because you may go soldering a bunch of these in and all of a sudden it doesn't work. You got to desolder them and flip them around. It is a pain, and I've done it many times. All right, so that's kind of what they look like. And let's go again through some of the rules about transistors. So you can sort of think of transistors as having two diodes back to back. So in the NPN, they're facing in this direction. In the PNP, they're facing this direction. And again, the base current flows this way, and the collector current flows this way. Base current flows in the opposite direction. Collector current flows in this opposite direction. All right. So when we turn the transistor on, we're going to forward bias this diode right here. Now, forget about this diode. We forward bias this diode, so current flows through this and then ends up coming out the emitter and then combining with the collector current. All right. So this collector current here comes out of the emitter, and it's called emitter current. So the emitter current is really the sum of the base current and the collector current. All right, we're going to talk about that some more. But the bottom line is this acts as a diode. And when that diode is forward biased, what do we know? It's going to drop about 0.6 to 0.7 volts over a large dynamic range of currents. All right, so that's nice. So we always know what this voltage drop is if the transistor is on. It's about 0.6 to 0.7. Pick one and stick with it, and that'll be fine to make your calculations with. All right, now the collector, now here's the other thing, the collector voltage for this transistor to be on is typically about 0.2 volts over the emitter. It can actually be like 0.01 to 0.2 volts depending on the manufacturer and the properties of the transistor. But so just think it's definitely got to be above, and it's got to be above a little bit, and it's usually 0.2 volts, but it can be smaller. All right. All right. Let's see. Okay. So we've talked about rule number 2. All right. Rule number 3, all transistors have maximum ratings. So these things are not magical. So you can only apply so much voltage to the base. You can only apply so much current can flow into the base. There can only be so much collector current. So there are maximum values. Also, since this is a diode, you can blow this diode out pretty quick. So if you reverse bias this, so in other words, if you put a very low voltage on the base and a very high voltage on the emitter, you'll reverse bias this diode, and depending on the manufacturer of the transistor, you'll blow it up. All right, so you got to be careful of that. All right, so that's kind of rule 3. All right, and we're going to do this on the board. So I'm going to skip this right here, all this current gain and all this. I want you to read this stuff, right? And we're going to, again, talk about all these things. I don't want to just read the text here too. You can read the text yourself. But there's some things I want you to see here. I like the pictures. All right, here's an example right here where what we're showing is a transistor acting as a switch, and so we have a resistor here, and then we say, all right, here's this resistor, we've got this voltage here, we're going to get a current flow, I sub B, into the base. We know that if the transistor is on, then the emitter here is going to drop about 0.6, 0.7 volts. In this case, I assumed it was 0.6 volts. Therefore, there would be 4 volts here, 5 volts there, and then we can compute what the current is here, multiply by 100, and figure out what the current is in the collector. We're going to do this again on the blackboard. But the point is that this calculation that we do may be incorrect, right? We're making assumptions here, and maybe the transistor can't even flow more than 100 milliamperes, right? So your calculations can conflict or contradict the specifications of the transistor. So that's why you have to be very careful. And that's why we don't like designing things with transistors and FETs for amplifiers, because you have to go through this it's kind of an iterative process to figure things out, whereas if we use the op amps, it's much easier. But again, this is an example. I want you to read through that. Transistor switching, we're going to talk about this, and this is just where we turn the transistor on and we turn the transistor off by driving current into the base. So you're going to read that. And then, okay, so this is a concept called impedance reflection. And so what we're going to do this on the blackboard, what we're going to learn about is this. So say you have a transistor and you hook something up to it here at the base, and the question is, I hook some circuit up to drive the base, but what does this look like as far as a resistor? So if there was just this resistor R connected right here and there's no transistor, the resistance is just R. But what is the resistance through this transistor? So if we were to look into the transistor from the base, what does it look like as far as an impedance, right? And so that's called impedance reflection. And actually what it looks like is beta, the current amplification of the transistor, times whatever resistance is over here in the emitter, all right? And we may even derive this, but so looking into the transistor, whatever resistance you have in the emitter, from the base's point of view, is beta times that resistance. All right, so it's very, very large. So if you have 1K here looking in here, it'll be about 100K, assuming beta is 100. If you have 10K, right, and beta is 100, right, then it's going to be a meg ohm, right? So very, very large. So what's good about that is whenever you hook up a different part of the circuit into a transistor, you see a very large impedance. So the transistor circuit doesn't affect your driver circuit as much. All right, so that's very important. On the same token, what if we look this direction into the circuit? So if we were to look at the emitter right here, so one thing I'll tell you is looking up into the collector looks like infinity. So there's a very large impedance there, so you can't see that. But you can see the base. Now here's the tricky part. So here's this resistance right here. When you look into the emitter, so if you connect something to this emitter, right, you see this resistance right here in parallel with whatever you see through the base. Whatever you see through the base is now divided by the beta. So if there was a 100K resistor here, it would be 100K divided by 100, the beta 100, and you'd end up with a 1K. So you'd be looking in here seeing a 1K in parallel with this. All right, so it's tricky, but that's what we want. So we want very low output impedance and very high input impedance. So that's why it makes a good amplifier. All right, so again, read through this. All right, and this is talking about this impedance reflection and kind of going through this. All right, all right, here's an amplifier. We're actually going to design this and go through this in length, but again, I just want to kind of go through this material right here first. All right, so in this case, what's happening is we've got the transistor and we want to set the base voltage someplace in the middle of the voltage rails, all right? So that's what this R1 and R2 do. So this is kind of called voltage divider biasing. And then we've got this capacitor here. So now that we've set the transistor like that, and then we have this load or this emitter resistor right here. All right, and then we've got this capacitor here and this capacitor here. And what is going on here is this sets a DC operating point. So these resistors, and this resistor set a DC operating point for this transistor. Then we bring in a very small AC signal through C1 and it wiggles the base here. And then that causes something to happen over here. In this case, there's no voltage amplification, but there's current amplification, and we get the signal out here. So this kind of circuit here acts as a current driver. All right, so you can increase current with this. So a little wiggle here, right, gets through the capacitor, right? Remember, it passes AC, and then it causes amplification. Something's going on here, current amplification, and then we get that little wiggle out here. And so we get AC in and AC out. All right, so this is one kind of amplifier. All right, and this is called an emitter follower or common collector. And again, we're going to talk about this when we get on the blackboard. All right, and let's see here, and this is talking about some of the filtering. All right, and then this is going to talk about using transistors for logic. All right, so what we're going to do is we're going to stop here, and we're going to start back up, and we're going to go to the blackboard, and we're going to start working through some of these things. All right, so that's what we're going to do, and then when we get done with all those lectures, then we'll get back to using these transistors as the basis for logic, transistor logic, right? And so that'll be kind of wrap everything up, right? So let's stop here. So this is kind of a quick lecture just to kind of give you some basis and kind of refresh your memory. Now let's in the next lecture, we'll actually start working these things out, do simulation and stuff, and move on with the material. All right, so I'll see you in the next lecture. Bye. All right, welcome back, and we're on the next lecture. So now what we're going to do is start doing the blackboard work here and kind of work through the transistor models and just kind of do some math and different little configurations of transistors and kind of work through how to analyze those, all right? So this will probably, I don't know, take 2 or 3 lectures, we'll see. And then we may or may not build something in this lecture. We'll see how it goes, all right? So let's get right to it here. All right, so the first thing is, let's go ahead and let's talk about some of these rules with the transistor, all right, so that we have been discussing. All right, so the first thing is, let's give ourselves some room here. So we've got our transistor here, and we're going to be dealing with NPN transistors, all right? So that means there's this arrow going down here, all right? And then we've got these 3 nodes right here. All right, so I'm just going to kind of put a dot here, and I'll put a dot here, and I'll put a dot here. All right, and obviously this is the collector here, this is the emitter here, all right, and then this is the base. These voltages at these 3 points, we can kind of come out here and we'll just put little probes on there. We can call this V sub C, we can call this V sub E, and then we can call this one V sub B. All right, so we've got these 3 voltages, we've got these 3 points, and then here is our transistor. And of course, this is an NPN transistor, right? So this is an NPN transistor, all right? And remember, PNP is the same, but everything is just reversed. So we're only going to analyze one of these. Okay. So let's start playing with this. So the first thing is one thing that we have here is, let's look at these currents, what they're called. So the current that goes into this base here. So when this thing is on, in one way or another, we've got a current into the base that's called I sub B. Then there's a current that's flowing through the collector here. This is I sub C. All right, and then a current that's going out the emitter here, and that's called I sub E. All right, so we have these 3 kind of currents here. All right, now, so let's try and relate these things together. All right, so to relate these things together, one of the rules is that I sub c equals what's called h sub fe times I sub b. So this h sub fe is called the beta, or the gain of the transistor, beta. And there are two versions of it.